Okay, good morning, everyone. Good morning, everyone. I think it's time we need to start get going with the session. I hope you've all recovered from last night's excitement of the football. As a Liverpool fan, I'm actually quite happy to play against Real Madrid rather than Manchester once more. So, okay. So in the past couple of days, we've heard a lot about our scientific program, our strategy, and yesterday we heard about important topics such as education. It's up to them to say louder. We've heard important topics about education and the need for our technologies to be taken more for societal benefit. And of course, all of these things require resources, which means funding in the end. And of course, we're extremely happy that not only do we have representatives from 3 communities here, but also that we have representatives from the funding agencies who are ultimately responsible for our use of these resources in the correct way and serving society and also our science. So this morning, our respective chairs have been in discussion with the funding agency members, and those discussions will continue today. And this morning, the aim of the session is to try and help give a basis for those discussions, facilitate those discussions, and see how we can build the future together. So our first speaker is Jürgen de Hunt from Brussels University, and he's going to tell us, at least in the first talk, as you see from the title, how we can build the future together.
Thank you, Paul, and good morning, everybody. Let me start this presentation by congratulating Real Madrid. I think that was a fascinating game yesterday evening. We've seen the fascination people in Spain and especially in Madrid have for football. We've seen that in the pubs, we've seen that in the streets. So congratulations to reach the final. Obviously, people in Spain are not only fascinated by football. People in Spain are also fascinated by, like we all are, what we find at the extremes or at the frontiers of knowledge. And this is nicely depicted by a very nice painting of Salvador Dali. That painting is almost 100 years old. It gives you a seascape of, I think, one of the Mediterranean coasts in Spain, and these famous melting clocks. Dali was saying in some interviews that these are basically molten camembert cheeses, although I tend to believe that he was also inspired by the fact that there's relativity between space and time, and he tried to depict that in his fascinating painting. 20 years later, he came along with the same seascape, and he was fascinated once more with parts of science. In that case, the emergence of quantum physics, that everything is built out of small quanta all around us. Obviously, as you see as well, there are some bombs in there that came along shortly after the Second World War. So that fascination for what is out there in the vast spaces and the vast times is something which is fascinating us as well. This fascination, this curiosity is driving us to the larger scales in the universe. On one side, the observable universe, and the smaller scales around us in the matter, the quarks as we know it today, which build up the protons, the neutrons, and the atoms. Obviously, what we can see with our own eyes, well, we maybe can see a few kilometers in the distance, and maybe we can separate 1 millimeter from another, but in order to go beyond there, to zoom out, to zoom in, we need dedicated tools. We need research infrastructures humanity has never seen before. We built on the Earth, or in the Earth, observatories to capture of whatever comes to us from universe. On the other side, we built powerful accelerators to zoom in into the fine structures of matter, and we came a long way. Also on the time axis, the dimension is huge. On one side, you have the age of the universe. On the other side, if you want, the lifetime of a top quark. Vastly different. Also, if you look in this corner, the lifetime of a star is huge, but it dies very fast. So also there, the time dimension is fascinating. We are out there to develop a model to understand how objects behave in this space and this time, and that is not trivial. And we have based ourselves, first of all, on some basic principles. These basic principles come as well from our intuition. The intuition that all the matter around us is built from the same constituents. The intuition that the future only depends on the present. It also is relying on some long-standing observations. Observations, for example, that the speed of light is constant, that everything is quantized, that there is a particle-wave duality. And honestly, there's no obvious reason why we have to take these observations for being true. But from these basic principles, we build up mathematical frameworks such that we can describe and calculate how objects behave in the presence of a force. For example, for gravity, general relativity came along. For the other forces, quantum field theories came along. And with these, we can calculate how objects behave. Obviously, we still have to tell these mathematical frameworks on which objects they have to act. We have to tell general relativity it has to act on whatever is there present in the universe. And came along with that is a standard model of cosmology. We have to tell quantum field theory on what small particles it has to act. Came along from that the standard model of particle physics. And these are the models we can confront with data, with observations. These are the models that have to be valid everywhere, in the tiniest cracks of space and time, at high energies, at low energies, and at the extremes. And we went out to the small scales. We built fascinating accelerators to zoom in into the smallest structures of matter, and came along from that is a standard model of particle physics. A kind of a formula, if you want, you can write on a cup of tea. On the other side, we went out and we measured what is out there in the universe. And by observing that came along is a standard model of cosmology. As you can see, different from particle physicists, cosmologists like to write their stuff on big things. And obviously, it has to connect also with the building blocks of life. We have to understand how quarks and gluons build up the nuclei into an atom, and how all the different chemical elements came along in the evolution of the universe. And that would close the loop to have an understanding of the building blocks of life. We have gone through a century of fascinating discoveries. A testimony of that are also the applications. The fact that you came here probably by plane is due to some very, very advanced navigation tools. The fact that some of you are now looking on your touchscreens, browsing the internet, is also like an application that came along from our endeavor. And not to forget, now you can buy machines and instruments that can provide you with radiation, with particles, for the benefit of our health. A previous Director General of CERN stated, "This is scientific curiosity that ends up in your pocket." But do not make a mistake. It's not because we can describe what is out there at the large and the small scales that we understand everything what we see. There are some mysteries and problems we try to address. For example, why is there so much dark matter? Why is there so much matter above antimatter? What is the origin of high-energy cosmic particles? What caused inflation? Maybe more important, what stopped the inflation in the early universe? The scale of things. Why do the numbers in our equations match so precisely that we can tell the tale? And how, from the quarks and the gluons, do we build up the complexity of nuclei? We know by now that we have to observe new physics. We have to observe new phenomena in order to address these problems and mysteries. Or, if you want, we have to find cracks in these standard models that will guide us on a way to address these puzzles. That means we have to go beyond these standard models. We have to go to higher energies in the lab, to higher energies in the universe, to an earlier universe, to rarer processes, to more precision, and even to observe one particular phenomena with different eyes, with different observations. And in order to do that, we have to innovate technology. Innovating technology is intrinsic to our field. Without that, we cannot make progress. We have to make what is invisible visible. That means we have to advance on one side accelerator technologies. We have to advance on the computing and the software front in order to deal with the huge data challenges we have. We have to develop new fast electronics to read out our detectors, and even we have to beat quantum physics to build better gravitational wave detectors. And if we find that new physics, of course we have to try to encapsulate that and capture that in our formula of the standard models. This is a formula of the standard model of particle physics. If we find new physics, it will appear at a different mass scale. And in one way or another, it will have to couple with the physics we do know. So in these two dimensions of mass and coupling, which you see in this plot, the new physics is out there somewhere. But there's not one single detector, there's not one single research infrastructure that can cover that full parameter space. The complementarity within a whole portfolio of experiments will cover that space. Complementarity is the name of the game as well in our field. And in order to make sure that we are doing well on that side, we have to develop strategies. Strategies to get the best eyes on the large structures, strategies to get the best eyes on the small structures, and obviously what connects in between to the building blocks of life, to the nuclei and the atoms. These strategies came along from in-depth discussions, bottom-up discussions within our communities. They express the best way of addressing our ambition to address these open questions. And of course now they are there as guidance for authorities to develop real resource-loaded research programs. Let me give you some view on some of these major facilities. First of all, what are the future eyes we will have on the sky? We have been looking very deep in the universe and captured the cosmic microwave background that is out there with great experiments that revolutionized the way we look at the universe. Came along was a picture on how the dark universe looks like. The next big experiment that comes along is Euclid, which will be launched soon. It will map the universe with more than 30 million objects with great precision, and from that map we will learn more about the properties of dark energy, dark matter and gravity at large. A fascinating endeavor. As well comes from our universe are high energy particles. Very different high energy particles. That might be photons, that might be neutrinos, that might be charged particles. And by now, we have some understanding on the energy spectrum of these particles. Some of them are coming from nearby in our galaxy, some of them at high energies come from outside of our galaxies, extragalactic. And what you can see if you zoom in into that picture is something special emerges. On the y-axis, you have the energy density, and what you can see is that the gamma rays, the neutrinos and the cosmic rays that come to us, apparently they come with the same or from the same energy density. That basically opens the question, would they come from the same origin? And this is opening a new realm of multi-messenger astronomy, a way to look at the same high-energy features in the universe with different eyes, with different experiments. And we have a portfolio, a very good portfolio of future and current facilities that have eyes, different eyes on the sky. We have experiments in orbit that measure the antimatter in cosmic rays. We have emerging large telescope arrays that will capture the high energy gamma rays coming to us. And as well in the volume of the Earth, we have large neutrino detectors which try to capture high energy neutrinos. These will be our current and future eyes in the multi-messenger astronomy realm. As well, the new kid on the block are gravitational waves. The current flagships of gravitational waves came along with a milestone discovery a few years ago. Fantastic. But we are preparing already for the next generation of gravitational wave experiments. The Einstein Telescope will be built underground, will be cryogenically cooled, and with doing so, we will have an increased precision of what is out there in the universe. We will see much more with an increased statistics, and therefore we will have an increased scientific reach. Depicted on this slide, as you can see what you can do deep in the universe with the current gravitational wave experiments. With the Einstein Telescope, you can go very deep into the early universe, into what we call the dark age, the time before large structures came along. And the big question is, will our basic principles, will our theoretical and mathematical frameworks hold throughout the cosmic history? We have to have eyes on the invisible. And if you want to have eyes on the invisible, you first have to shield yourself from whatever is visible. That means you have to go deep underground. And in Europe, we have a variety of deep underground laboratories. And in there, one of the main enterprises that is being built there is the ultimate low background astroparticle physics observatory. That might be with argon, that might be with xenon, or might be both. And these are huge detectors where we try to capture the signals of dark matter the very faint signals of dark matter. And again, in that plane of coupling and mass to new physics, we are zooming in step by step to reach the ultimate precision with these experiments. And at some moment in time, we will hit what is called the neutrino floor, where basically the rate of these dark matter particles are predicted to be equal to the rate of, well, simple neutrinos we'll see. There's one place in the standard model where we know we are not complete, and that's the neutrino sector. Neutrinos come in three species. They oscillate among each other while they live. That means they have a mass. They have a mass, but they don't have a mass in our equation of the standard model. That means we have to extend the standard model. But how? Is the neutrino its own antiparticle? What about matter versus antimatter in the leptonic sector? What about the absolute mass scale of neutrinos? We do not know. And for that, we have to go to the ultimate precision of measuring how neutrinos oscillate and antineutrinos oscillate. And we will do so with powerful accelerators that will create a neutrino beam, starting with one particular speed of neutrino, and 1,300 kilometers further away, we try to capture these neutrinos to verify what flavors have emerged during their oscillation. That means we have to build large, new detectors to capture these neutrinos. With the CERN's neutrino platform, we are innovating the technologies to make happen these experiments. We are preparing for experiments at long neutrino baselines in the US as well as in Japan. So within the next decade or so, we will know much more how we have to write down and complete the equation of the standard model to add the complete neutrino sector. We have to have eyes on direct discoveries. The current flagship for that is a Large Hadron Collider at CERN, a fantastic enterprise, and it will be upgraded. It will have a high luminosity phase, which means the accelerator is being upgraded, the experiments are being upgraded to run for another 20 years or so. That's an impressive program. But do not make a mistake, this is not business as usual at these experiments. As an example, in 2013, a year after the Higgs discovery, we made an estimate how precise we will be able to measure the interaction between a top quark and a Higgs particle. Came along was 7 to 10% precision. 6 years later, with all of the innovations we reached in only 6 years, we improved to 4%. And yet the high luminosity phase is to start. It goes without saying, talented researchers really make the difference at these experiments. We think about future high-energy particle colliders. How we think along these lines? Well, we know we have that very unique Higgs particle. And by now we know that basically all of the problems and the mysteries in our standard model, in one way or another, relate to that unique Higgs boson. That means we have to produce a lot of these Higgs bosons, put it on a zoom, and see where the cracks might be. So the next high priority collider is an electron-positron Higgs factory, with a view to zoom in into that yellow part of the equation. What we have discovered as well over the years is that there's a great deal of complementarity between all types of colliders with a view to search for new physics. And I give you one example. If you would like to measure the interaction between a W boson and a Higgs boson, you can do that with a Higgs factory with a precision of, let's say, 0.9%. If you add on top of that all the information coming along with a new high-energy proton collider, you improve with a factor of 3. If on top of that you include all of the information coming along from a new electron-proton collider, again a factor of 3 improvement. So this is a plea for a coherent program allowing for the full variety of future colliders. And this brings us to the future circular collider. The main ambition in particle physics and the big sister future ambition relative to what we had and have at CERN, the LEP and the LHC collider. It will start as a Higgs factory, and then it will roll out the whole program at the highest energies in proton collisions and electron-proton collisions. This is a program that spans the rest of the century. So you better make sure you can plan for success. And accordingly, we do a feasibility study to verify the technical aspects, the administrative aspects, financial aspects, and obviously the global governance issues. Soon, hopefully, we will get all the elements together in our hands to make this happen. We have to have as well eyes on the structure of things, on the very small structure of things. We know we have quarks and gluons, and these quarks and gluons in the early stages of the universe, they were a bit everywhere. At the high energies or the high temperatures in the universe, they were acting as roughly free particles. When the universe cooled down, well, these quarks and gluons were not everywhere. They were confined in the tiny, tiny spaces of hadrons and ions, for example, of protons. And we have to understand how this structure came along, from first principles in our equations to the protons, the ions, the elements we use in our experiments, we use in our application. We do that, for example, by colliding electrons with protons, proton as being a hadron, and if we do that with higher and higher energy, we see more and more structure within the proton. And with that, we learn how the structure of matter is being built. The next in line phenomenal collider will appear in Brookhaven. The electron-ion collider will be the first electron-ion collider in the world. It will use polarized beams. It will appear, it will come online, let's say, a decade from now, and with that, we will get to know how the properties of the big structures like protons and neutrons are emerging from the smaller constituents within. We will have a full 3D image of what is out there deep into the proton. And it goes without saying that there are many other running and emerging low-energy scattering facilities that are as well very key to understand the structure of hadrons. On the other side, we also have to understand how these quarks and gluons end up in the end in ions, the nuclei of atoms. In the early phases of the universe, you have a very large temperature and a high density. That means you were somewhere here in this plot. And quarks and gluons were living at that time in a kind of a plasma. When the universe evolved and cooled down, well, these quarks and gluons were confined in the end into nuclei. We are developing experiments where we recreate the situation of a quark-gluon plasma, try to understand its properties and how in the end nuclei have emerged. Next in line, large facilities for that is the NICA facility at JNR, and surely here closer to home, the 600, the 300 colliders at FAIR. At FAIR and also at NICA, there is a large amount of experiments that come alive to study these heavy ion interactions with great precision. And although I show you here a kind of a drawing, I can also show you a picture. The civil engineering is coming around, and later in this decade, these experiments will come online, take data, and learn how the complexity of matter arises, how in the evolution of the universe all the chemical elements came along. And this closes the loop. This closes the loop. We will have better eyes to the large scales, we will have better eyes to the smaller scales in the universe, and above all, we will also understand how they come together, how they have to come together in a complementary way to understand the building blocks of life. So clearly, this is a plea to build the future together. There's a great amount of complementarity among all our experiments, and that complementarity is not there by design, it's because we need that complementarity. We have to sustain, obviously, the capital investments in these future facilities. We know that there must be new physics out there for us to be discovered. New physics that we can add in our equations of the Standard Model. And that would be a milestone for our field. If we would not discover that new physics, we might be putting ourselves in a position where we have to revisit the underlying theoretical frameworks, the underlying basic principles. And that, dear friends, would be nothing less than the scientific revolution of our generation. Thank you for your attention.
Thank you very much, Jürgen, for this very inspiring and fantastic overview. There's certainly a lot for us still to do in our future together. Questions, please, and comments.
Okay, first, thank you for this very inspiring overview, which just maps our field. And something struck me while listening at you is that for some of the part of the fields, mainly particle physics, nuclear physics, facilities seems to be driven by big centers like CERN, which is a provider, acts as a provider of beam, which in turn provides the data. On the other hand, for astroparticle physics, the situation is quite different, because it's the universe which provides the data, and experiments, when they are actually finished taking their data, the game is not over. And I have the impression that there is a missing facility that would be post-data acquisition. So you cited, for instance, Euclid. There is this big Rubin Observatory, which also would provide a lot of data. And combining this data is actually a challenge as big as just collecting the data. And I don't have the impression that it's addressed as an issue, while at the same time in Europe, I guess, being part of so many experiments will be very good placed to address this kind of issue.
Thank you very much for this question, and the rightful question. Yes, nuclear physics, particle physics, astroparticle physics, I don't even mention it during this presentation because I think there is complementarity in the physics we do. We differ somewhere in the methodologies we deploy and the governance we have in order to make it happen. But you're completely right. If we collect data, we have to share the data and make it combinable. That's a major challenge. First, collecting the data, making it available. There are projects, and I think you will have a presentation later today, on the ESCAPE project in Horizon 2020 that tries to connect all these data pieces and tries to make it available not only for the researchers, but also in an open access situation for the whole of the society. And I'm sure you will be inspired by that presentation on ESCAPE, where we try to connect data in order to connect the science, connect the people, and break maybe the standard model and maybe find new physics. And it is a challenge, I fully agree.
So just have a couple more minutes.
Yes, thank you for this very nice overview. And since you bring actually the three communities together by giving this very nice overview of the challenges, I just wanted to add that one of the challenges, I guess, that was probably missing in your talk is the quantum many-body system, which is a major challenge, I think, in several fields, and it's not quite addressed yet. Do you have any comments on that?
Thank you again. Yes, if you give me not 25 minutes, but 25 days, we can have a very large workshop on these things. I have to try to speak for everybody, of course, in a language that is adequate. Calculating in quantum physics is not easy. Quantum physics is governed in some sense by a Schrödinger equation, which we can solve. It's not a very difficult equation to solve if you think about two particles. But from the moment you start thinking about many more particles, that equation becomes very difficult to solve. And it is, on the methodological side, a challenge. A challenge on numerical techniques, a challenge on computing, on software. But of course, if we can address that challenge together, you can make some great progress in some of the science we have. We can try to connect some of the observations we have, especially in nuclear physics, with calculations, with models, with theories. So yes, it is an important program in the realm of fundamental physics.
In fact, I have a short comment to your talk, which was concentrated on the fundamental physics, fundamental issues. And this is right. This is our driver. That's what we are doing. But at the same time, I would like to also underline, you mentioned this, but I would like to underline again that we are not forgetting about the applications, about the knowledge transfer. This is important part of our activities in all three fields. You mentioned, of course, the most visible highlights, like web development at CERN, but this is also part of our everyday life activities. And I think in front of especially representative of founding agencies and also European Commission, I think it's worth to underline.
Thank you, Marek. And I think exactly for that, the next presentations will cover some of the detector challenges we have, some of the computing challenges we have, and they reach out very deep in the society with very clear applications, rightfully. Thank you, Marek.
Okay, I think that provides us an excellent bridge to the next talk, and we should thank Jürgen again for his excellent presentation. Okay, there may just be one moment here while we upload the talk. Just bear with us 1 second. And the next speaker is Ian Shipsy from University of Oxford. And as you heard, we're going to learn now about detector technology challenges to realize these scientific ambitions, which we've just heard about from Jürgen. Okay, thank you.
So thank you very much for this invitation. I would like to talk to you today about building our future together through detector technology challenges to reach the scientific ambitions that Jürgen laid out for you on the last talk. The APEC, NUPEC, and ECFA communities are united in seeking to understand the fundamental nature of the universe, its fundamental constituents, and the forces between them, and to apply that knowledge to understand the birth and the evolution and the ultimate fate of the universe, how the plasma at the beginning of time became the beautiful universe we inhabit today. From the discovery of the electron in 1896 to the discovery of the nucleus in 1911 and to the Higgs boson in 2012, building our current understanding of the universe has taken a century. Our communities have revolutionized human understanding of the universe, its underlying code, its structure, and its evolution. And through the most careful of measurements, observations, and deductions, we have developed remarkably successful theories, the standard models of particle physics and of cosmology, and these have been enabled by instrumentation. Our APEC, ECFA, and NUPEC scope is broad, and we deploy many tools, accelerator, non-accelerator, astrophysical, and cosmological probes, and all have a critical role to play. Our community has detected and measured particles in the universe over an energy range of 24 orders of magnitude from the cosmic microwave background to cosmic rays. And we've done so with a rich spectrum of technologies developed by our communities. The potential now exists to revolutionize our knowledge again. Jürgen outlined many of the problems and the mysteries about the universe for which there are many theoretical explanations. An experiment must decide, experiment must guide the way. As Jürgen said, observations of new physics phenomena and or deviations from the standard models are expected to unlock concrete ways to address these very puzzling unknowns. And so we're very much in a data-driven era. The LHC and LIGO, as two outstanding examples, took decades to realize. And due to the decades-long gestation time for the most ambitious projects of our age to solve the mysteries and problems that Jürgen outlined, we must develop the tools we need to solve these problems now. And that's a very exciting prospect because, as you've seen others say as well, new directions in science are launched by new tools much more often than by new concepts. That's a very profound thing. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. This is why so many of us choose to be experimentalists. And so our job, if history is our guide, is to realize these new tools, that they will open new doors. And so, as Galileo said, we must measure what is measurable and make measurable what is not so. And you can see that that challenge inspires us and inspires these young children at CERN in the control room as well. Now, often when we embark on an experiment with a goal in mind, we find something different to what we expected. On the left are a series of facilities, particle accelerators that have existed, in some cases telescopes, over the last 30 to 40 years. The green is what was expected to be found, and in red is what was actually found: CP violation, the charm quark, the bottom quark, the top quark, the gluon, neutrino oscillations, and dark energy, to name just a few. Precision instruments are a key to the discovery when exploring new territory. If they're not precise and capable instruments, we miss the things we were not expecting. Now, our technologies are synergistic across and broadly applicable across our three communities. The reason for this is that the particles that the technologies detect, whether produced in an accelerator or in a non-accelerator experiment or in a cosmic ray or in space, are generally the ones that we can measure. They're the products of the things that we seek, often photons, for example, or protons or neutrinos. Therefore, the technologies that detect these particles are broadly applicable across our three fields, and they're synergistically developed by our three fields as well. So technologies can be arranged by type. They can be based on gases or noble liquids, or on the solid state, or on photodetectors, or quantum sensors, or calorimeters, or electronics, or the infrastructure that holds things together. I'm going to take one example: the broad reach of photodetectors. Photodetection is truly ubiquitous over many ranges of wavelengths and signal times. And the challenge is to develop large area devices, radio pure, cryogenic stability, high quantum efficiency within appropriate wavelength sensitive windows. And so this is a slide from Andreas Rang yesterday. The APEC flagship research infrastructure and photosensors play a crucial role in enabling the science objectives of each of the ones on this slide. For example, the CTA Cherenkov telescope array uses silicon photomultiplier tubes for photon particle identification. It's a central technology in high-energy gamma ray studies and has become a common requirement also for dark matter searches and for neutrino experiments. Now, silicon photomultipliers are solid-state, single photon sensitive devices implemented on common silicon substrates. And for CTA in the future, upgrades to increase the UV sensitivity of ideally digital SIPMs would be desirable, and it would help them reach and see much more of the universe. IceCube measures high-energy neutrinos detected by the light emitted as they interact with the Antarctic ice, and are measured with photomultipliers, extremely sensitive detectors of light. These detectors multiply the current produced when a photon strikes the photocathode, perhaps by 100 million, thereby rendering sensitivity to individual photons. When the incident flux of light is low, that can make all the difference. So the IceCube goal by 2033 is to increase the rate of observation by a factor of 10 and detect sources 5 times fainter than today. And the first stage in that is to insert an additional 700 photomultiplier tubes called MDOMs and D-eggs into the ice. These are phototubes in the photograph there, descended into the ice in a previous deployment. And this is what they look like. The MDOM has been developed by KM3net and shared with IceCube. The D-egg is now made, and on the right is a drawing for what the detectors might look like for the upgrade in the 2030s. Dark matter generation 3 experiments. The challenge there is the choice of radio pure photosensor technology to avoid giving false positives in these very rare events, and PMT as the baseline, but silicon photomultiplier tube is an option under evaluation as well. AGITER, the Advanced Gamma Ray Tracking Array, is used for nuclear structure studies, and it's a highly segmented, high-purity germanium array of photon detectors. It's a remarkable instrument. The material is a semiconductor like silicon, but more sensitive, better energy resolution. Agate is capable of counting event rates. It can be used with other detectors in synchrony, and it's a new priority. This project timeline is to complete the array in 2030, and this must happen. Next generation cosmic microwave background experiments are used to detect gravitational waves that could be the remnant of the signature of inflation 10 to the minus 36 seconds after the birth of the universe. The technology is the transition edge sensor. A transition edge sensor is a type of cryogenic energy sensor that exploits the strongly temperature-dependent semiconductor phase transition. So what you see here is that over 20 years, we've gone from deploying 330 detectors to 7,000 detectors all on the ground. And now, Lightbird, which is a satellite with very large European participation, plans to deploy 4,500 of them in space. And CMBS-4, which is ground-based, plans to deploy, listen carefully, 500,000 TS barometers operated at 100 millikelvin. That's such a large number that you have to use industry to work with you to build this. This is beyond the abilities of the national lab. A challenge in optical astronomy is red-sensitive CCDs. You can advance astronomy this way because the universe is expanding and things are redshifted. Distant things are very redshifted. So using techniques that were developed for silicon sensors in particle physics, thick silicon, high resistivity silicon, very pure silicon, it's possible to build a thick CCD, and that's been used in the Dark Energy Survey and is now part of the world's biggest digital camera for astronomy, 3.2 gigapixel LSSD cam, which will come online in Chile in the Rubin Observatory in 2024. Now, our community has been an important contributor to broadly applicable innovation that goes beyond our own field to the world. We've heard mention already of the web and MRI. The development of a manufacturing process for BGO crystals for the colorimeter of Lab 3 experiment at Lab some years ago contributed significantly to the advance of PET scanners. And the development of large area hybrid pixel detectors for high energy physics experiments led to the realization of the potential of this new technology to provide noise-hit-free single photon counting, impactful for the development of sophisticated integrated circuits with timing to be used in medical imaging, X-ray science, and much more. The Panda Detector roadmap that I'll be presenting in a few moments in this talk would lead to the development of new technologies that hold the promise to be as broadly applicable and equally transformative. So instrumentation is the great enabler of our science. CMS and Atlas are digital cameras designed to completely surround the collision point, which is at the center of the camera, so that all of the particles that are produced can be imaged. A variety of detector types are used, nested one inside the other, like layers of an onion. And we can see that here. Outermost are muon chambers made of drift tubes. The hadrons are identified by a hadronic calorimeter, and inside that, an electromagnetic calorimeter, highly granular, made of liquid argon and lead absorbers, detects photons and electrons. A tracking system that measures in silicon strip and silicon pixel detectors the trajectories of the particles in the magnetic field. And this is a cartoon of the particles emanating from the center, the muons being the most penetrative and reaching the muon detectors at the outside. Experiments at accelerators are generally comprised of many detector subsystems, at least in LHCb, are further exemplars at CERN. The electron-ion collider at Brookhaven, which will have beams around 2030, is concurrent in operation with the high luminosity LHC, and the physics of the two is deeply synergistic. There's a great many Europeans now members of the electron-ion collider, and the detector that was chosen, ETCHI, if you look at the technologies within it, they are common with the LHC, high luminosity LHC, and with RIC. Silicon, gas, photons, particle identification, and calorimetry. And some of this technology was developed with nuclear physicists and particle physicists working side by side in the same labs, and I saw that directly over the course of many years. Go to FAIR and look at the Panda Detector that will come online in a few years. Now, the geometry is very different. It's asymmetric because the proton beam strikes the interaction point and all the products move forward, and so the detector is in a forward arrangement rather than surrounding the collision point. But the technologies are in common again: silicon, gas, photoparticle identification, calorimetry. And this also applies to the CBM experiment as well up there. And these experiments must come online as soon as possible so that they can do the most important work. Switching completely away from photosensors now, the gravitational waves and their future in Europe is the Einstein Telescope. The technology challenges are in laser power and squeeze states, but also to reduce the seismic Newtonian noise. The interferometer, which is a triangular arrangement, is under the ground, and this means building long tunnels. But to reduce the thermal noise, in the suspension and in the test masses, cryogenics are needed to cool the mirrors. Now, LIGO and Virgo are already CERN-recognized experiments, and there's an MOU between CERN and the Einstein Telescope. Interactions have started on R&D for vacuum instrumentation. And examples of joint R&D on instrumentation include underground construction, CERN's an expert, vacuum beam tube construction, cleaning and baking, out procedures, cryogenics, and remote controls. The particle physics community at CERN has developed incredible experience of governance and implementing big science projects, and ET should build on this. This is the flagship for particle physics. The current flagship is the LHC and the high luminosity LHC, but as Jürgen said, the biggest ambition of our field is to build a 100-kilometer collider that will produce countless Higgs bosons, W particles, top quarks, that we can study and look for deviations from the standard model. And further on, after that, a hadron collider at about 100 TeV. Now, the events at these two types of collider are very different. When electrons collide with positrons, we get simple events. There's no trigger needed. Full event reconstruction is possible, and there's very modest radiation levels, whereas at a hadron collider, the events are very busy, require hardware and software triggers, and high radiation levels are experienced. These are the detectors that you would see at those two machines. At the FCC HH, the detector is very large, it's 50 meters. And the challenge is, amongst many, is radiation hardness. The radiation levels that this will experience, a detector at the center of that detector will not survive, it will not function. Sector R&D is absolutely mandatory. For E plus E minus collisions, the detectors are much more normal size, just a few meters in length. But the challenge of spatial resolution and very low material requires detector R&D. So, the technologies developed by the LHC took over 20 years to research and to develop and build, and these were out of technologies that came before. The technologies for the high luminosity LHC began to be developed around 2008, and they'll be ready by 2029. The technology and R&D for experiments that commence operation in the next decades will not be ready if we do not begin to do the research today. And so, recognizing that, the European Strategy for Particle Physics said that success of particle physics experiments relies on innovative instrumentation and state-of-the-art infrastructure. We must maintain a strong focus on instrumentation. Detector R&D programs and associated infrastructure should be supported at CERN. And the community should define a global detector R&D roadmap, and it should be used to support proposals at the European and national levels. And so ECFA organized a roadmap to be developed like this. So the ECFA detector roadmap Given the future program, identify the main technology R&D that must be met so that detectors are not the limiting factor for the timeline. The context of the detectors were the exploitation of the LHC, long-base neutrino experiments, future high-energy colliders, future muon collider accelerator set up for rare decays and dark matter, experiments for precision QCD, and non-accelerator experiments. The process organized by the panel and 9 task forces with input sessions and open symposia with a total attendance of about 1,359 scientists. The main document is 250 pages long, and there's an 8-page synopsis. Within each task force, the aim was to propose a time-ordered detector R&D program by detector research development theme in terms of capabilities not currently achievable. And so this is far too small for you to read, but I'll increase the magnitude of it in a moment. But the different technologies are represented by the colors, and the detector research and development themes, as a function of time, are matched to the schedule shown below for the possible new facilities. And so if I blow up the first one of those, the detector, the gas detector one, you can see that one of the goals is to improve time and spatial resolution for gaseous detectors with long-term stability. Now, I should say that in these timelines, the faded region indicates the typical time needed between the completion of the R&D phase and the readiness of an experiment at a given facility. Stepping stones, these points, are shown to represent the R&D needs of facilities intermediate in time, for which the same technologies are needed, and so they provide practice and to improve the techniques. And it should be emphasized that the future beyond the end of the hours is simply not yet defined, not that there is an expectation that R&D will be necessary. So in the case of gas detectors, you can look at in the report and find a detector readiness matrix of each task for each chapter. And so for 1.1, which was the radiation hard, improved position resolution, you can look along the timeline and see that here we need, this red means must happen, or the main physics goals will not be met. And this must happen for muon detectors, which is the role of the gas detector in this case. All the roles that are here, all the experiments are here. Now, otherwise we'll not be ready in time. Eco-friendly gases, for example, are also important for the future colliders. And in addition, large area integration is important. Whereas for precision timing, some things are urgent now, for example, for FAIR and CBM and Panda at FAIR. Now, these gas detectors were developed over the course of many, many years. The original wire in a gas, and then putting many wires in a gas, was a brilliant idea and Sharp won the Nobel Prize for it. You can measure X and Y with a device like this, as long as you have 2 of them. If you want to measure the true spatial position of the trajectory, then you need a TPC, and that was invented by Dave Nygren in the 1970s, and you find it today in the ADIS TPC. Gaseous detectors have evolved significantly, and today we achieve the amplification factors not by wires in a gas, but also by microstructures called micropattern gas detectors, of which there are many, many types, and they've become the primary choice for large area coverage with low material budgets. In fact, we've learned how to make them bigger and bigger and bigger. And because we can now do that, they become a key part of the high luminosity LHC upgrades. Now, the current and near-term future addressing the physics drivers for liquid detectors, which are neutrino physics, neutrino astrophysics, neutrino star beta decay, and dark matter, are grouped by detection modality on this plot for both liquid detectors and for solid detectors. And with either one, we can detect light or ionization or heat. So the liquid targets here are in purple, and they are xenon, argon, or helium, which are usually operated as TPCs. Water is operated as a Cherenkov detector. So TPC, in a liquid form, was invented by Rubio in '77. He then built, along with his colleagues, Cygnus, which is Icarus, which is a 670-ton liquid argon TPC, and that took data at the Gran Sasso for many years, and it's now at Fermilab as part of the short baseline neutrino program. To build Dune, we have to first build prototypes. That's done at CERN. The current challenges are to apply high voltage carefully and safely to achieve uniform electric fields, and in the future, increase the charge to light detection. This is an illustration of a microelectronic circuit integrated with a detecting medium as a single monolithic solid-state detector from Alice. In this case, it's silicon. A particle that's passing through ionizes the silicon, electrons and holes drift, and they're collected in the circuitry, which can amplify it, it can store it, and it can ship it off chip. Solid-state detectors, in particular silicon, have evolved immensely over the last 40 years. Every decade, the instrumented area has increased by a factor of 10, while the number of channels in the largest arrays have increased by a factor of 100. They're also more radiation hard than they were, but there's much more work to be done. And they're also using alpha calorimetry and time of flight. Now, the timing abilities are important. This is a picture of an event at CMS around the time of the Higgs discovery. The 10^11 protons colliding with 10^11 protons produced 24 interactions in that one event. With the high luminosity LHC in 2029, it will look like this. Now, this is a simulation, of course. Now, high luminosity, that means a large data set, which is what we want, but it also means large pileup and high radiation dose. And so when we view the collisions in 3 dimensions, it's a fog. But if we can open the time dimension and separate these vertices in time, then it becomes clear, and we can seek and identify new physics. So this is enabled for the high luminosity LHC by new precision timing detectors called LGADs and silicon photomultipliers as well. Experience gains will be crucial for the future high energy hadron colliders that we build. But the LGADs themselves are also very interesting detectors because they will have many applications in space, in synchrotrons, in medical physics, and so on. For photosensors, where do we start? Naturally, the radiation hardness is at the core of the R&D for the next generation of colliders. Silicon photomultipliers are the most active area of research, but there's still a lot of work to be done to improve the near UV and fast timing sensors. Quantum technologies are a rapidly emerging area of technology development to study fundamental physics, and the ability to engineer quantum systems will improve on the measurement capabilities that we have today from these sensors, and it's very exciting. Now, many different sensor technologies are explored, from atomic clocks to superconducting qubits, up to mechanical sensors, atoms, molecules, and ions, and atom interferometry. And what this plot is showing, the x-axis is the mass of the dark matter particle. In blue, you see the ranges which we have searched for dark matter particles. On the right is the WIMP, the heavy particle, and the blue region here is the area that we have searched for axions so far, after 40 years of trying. These green regions here are what's opened up immediately with quantum sensors. And so the probability to find an axion is greatly increased. In electronics, the main challenge, of course, is high granularity, resolution, precision timing. It would imply a cost to processing, however. We have to use high-speed links and microelectronics with very small feature size. It's not a problem to put more transistors on a chip, but we're moving from 65 nanometer to 28 nanometer. We'll have a massive cost increase. And we don't have a solution to this today. We have to find a way to work together with increased coordination around Europe to address this challenge. One of the final task forces was on training, and there's a proposal for a career in physics instrumentation to be a key element, especially given the timescale of the projects. And so that means a specific recommendation to develop an education program for instrumentation, a master's degree that would be pan-European wide. Now, everything needs to be reviewed. And so we have made a proposal for a reviewing scheme. I'm not shown here. So the proposed structure is to establish new detector R&D collaborations at CERN, one for each detector technology, and provide oversight and reviews by ECFA and CERN committees. The next ECFA, this next step then was, ECFA was mandated by Council in December to work out an implementation plan, which is shown on the right. Work is ongoing. First implementation plans have been proposed. There are discussions with CERN Council and funding agencies, discussions as well. Finally, the roadmap made a series of general strategic recommendations, which I will not read out, but it speaks to the importance of supporting test beams, engineering support for ASIC design and advanced mechanics, dedicated support for GEON, for example, and the creation of international R&D collaborations, as we've now proposed. Furthermore, distributed detector laboratories which bring together the relevant expertise of the academies with central national laboratories and optimize the distribution of resources between them. Establish long-term strategic funding so that proof of principle work is not the end of the story, that there's further research funding before you're part of an experiment. Because as you saw in this talk, it takes decades to develop these technologies. And it's not possible to do so if there is not sustained funding. And we must also make sure that there's blue sky funding and work closely with industry and neighboring fields to enable that blue sky funding along with the funding councils themselves. We must attract, nurture, recognize, and sustain the careers of R&D experts, recruiting them and giving them hope such that they can have permanent positions just like we can as professors. We need to increase innovation, so industrial partnerships, open science is important too. And at the moment, that's solved for the APS journals. It's not solved for some of the instrumentation journals, however. And so this is the last but one slide. The roadmap conclusions. We were set up by the European strategy and ECFA. A matrix structure was laid out, displaying synergies between concurrent and subsequent projects. Discussions towards an implementation plan are ongoing, and the roadmap should be updated together with the European strategy at the next call. So Europe is playing a prominent role and a leading role in many areas of our inquiry. In those cases where we're not leading, we're the partner of choice. The effort has gone into creating truly great infrastructures in Europe, and it's not easy to do that in other parts of the world. This is a very special thing Europe has. We must do everything we can to maintain it, and therefore our momentum. So these three children, who I know personally, represent the next generation and the generation after that too. And what they would say to us today, as they stand inside a piece of a spare barrel of the CMS tracker, the greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. How very true that is. If we don't aim high, we will not realize the potential of our field, all three communities. Discovery will be stalled, perhaps for a very long time, and that is a betrayal of ourselves and the generations that come after us. We must keep the momentum. Thank you very much.
Okay, thank you very much, Ian, for this fantastic overview. I see one question there.
Yeah, thank you so much, Ian, for this insightful view of the future developments in detector construction. I would like to make a comment connected to the detailed planned improvements.
Loud. Maybe take the mask. Could you take the mask off?
Yeah, I will take off the mask. Yeah, I would like to make a comment connected to the plans improvements on the various devices for the various applications that you had put in your wish list there. So while the table you showed at some point there includes desirable goals, because, for instance, anybody would concur that it is desirable to improve resolution for a gas device, of course. I think it misses what I have been calling as of late the elephant in the room. That elephant is an artificial intelligence. We all know that we are on a steep slope of a rapid development in our capability of extracting inference from the large and complex data that detectors yield. And we are looking forward to 20 or 30 years from now. And it is absolutely clear to me that we cannot omit to consider what improved methods for the extraction of the inference from those devices will be available when those machines will be commissioned. Because in 20, 30 years from now, we will not be tracking particles with a Kalman filter, which is what we normally do today, and that is a very good way now to do it. But in 20, 30 years, it will be an artificial intelligence tool that will do that for us, with much greater efficacy. So we risk a misalignment. We risk to construct things now and ideate and concoct things that will work in 20, 30 years that will not be appropriate for the tools that will extract the information, okay? So to me, this says that we need to insert in those design procedures the improved capability of future pattern recognition. So I think this has to be kept in mind, and the only way to do this is to plan for a global optimization of these instruments to avert that misalignment. Thank you.
I've not been able to hear well enough to know what the question is, except that it was quite long. Yeah, he's a very interesting person. He's a good friend of mine.
But I can shout. I think
It's okay, there's no need to repeat the question. There's no need to repeat, thank you.
Okay.
So the main gist is that the use of AI in the future
Yes, absolutely. You're supporting that. Yes. So absolutely. I mean, it would be impossible to achieve what we've set out without a global effort in which Europe is playing a leading role. And it's only possible we're working together. Working together was how we got the LHC to happen in the first place. 10,000 people were contributed to making the LHC possible. That was incredible teamwork. And before we even found the Higgs, you remember when Big Bang 2 started and we all went around the world talking about the machine was turning back on after the accident. What the audience would say was they weren't interested, the audience was the public, and they weren't interested in the Higgs boson per se. What they were interested in was the incredible machine that the LHC was and the incredible detectors that had been built. And why they were impressed by it was because it was clear that people from every country in the world you could almost think of were working together. So definitely, working together is the only way to achieve our goals. Is that helping to, is agreeing with him?
Actually, what you said to me was, so he agreed with you, actually, before he gave that answer, he agreed with you that it's essential to develop both together. So, yes.
The role of machine learning. Yeah. The role of machine learning is incredibly important, but I think that's another speaker later, not me. But, put the machine learning as close as possible to the sensor. Put as much intelligence in the sensor, and you will get much better data. And then machine learning to understand the data you've taken is all crucial, I think.
Okay, I think we have to move on now. So thank you, Ian, once again. Okay, our next speaker is Gonzalo Moreno Arevalo. I got that right. And we're going to hear now about, so we've heard very much about our detection systems and the need in the future for high power computing and big data, and that's the subject of the next talk. So please.
Okay, thank you very much. Thanks to the organizing committee for the invitation. I am very excited to be in this symposium. This is mostly because it's a good example of this transdisciplinary conversation, which I think it's crucial for the challenges we have ahead. So I'm going to talk about the challenges in computing and software. I want to start with an outlook pointing, oh, yeah, I don't need this. Thank you. So an outlook pointing to three of the main ideas I'm going to try to convey today. So first of all, that software and data analysis are a first-class citizen in scientific collaborations and scientific institutions. So when designing experiments, it's very important that we take into account the digital infrastructure as part of the detector, of course. There are several places in which there is room for improvement in there, from the incentives to contributions to computing, also to ensure research software engineer is a fully considered career path within our community. Second, it's to acknowledge that this is an extraordinarily dynamic environment. So there are phenomenal investments from industry. So cloud companies and social media companies are investing order of $1 billion per year sustained. So there is a huge innovation with very short cycles. And this also implies that there is a fierce competition for talent. So this is the environment in which all this is happening. And finally, the key message also that this, our experiments are multi-decade, so the sustainability is key, and for that, the collaboration, which again, this community is a great example of that. In this picture, this is just in a graphic view of this main message I want to convey, that it's been tackled in several of the previous talks and also discussion questions, right? So digital infrastructure as an integral part of scientific instrumentation, also in the design process, right? So this is a fundamental concept. So in looking into the challenges ahead, a good example always is the high Lumi LHC. So in this plot, I'm showing the last version of the Atlas, in this case, predictions for resource estimates into the future. We see the resource increase as the LHC, high Lumi LHC will kick in 7 to 8 years, so with an order of magnitude increase in data volumes and complexity. So the blue line, it's the resource increase expected in what's called conservative scenario, in which we assume that we can maintain the current level of effort and expertise in software and computing. The red line depicts what's called an aggressive scenario, in which a higher risk R&D projects could be tackled only in case we manage to get increased effort. The black lines are showing the estimations for resource increase that we expect to get from technology improvements in a flat budget scenario. So the two main takeaways of these sorts of plots to me is that first, this plot is regularly updated. So in the last few years, if you look at previous versions, there has been huge improvements. So there is a lot of activity going on to get those resources back into what we think it will be feasible. So there is an intense program for R&D. And second, that still to get it, to get the numbers back into what we believe it's achievable with flat budgets, we will need increased effort. So just a quick glimpse of what type of R&Ds are going on in the case of the LHC. So a substantial part of the R&D, it goes towards porting code to this graphic accelerators or specialized hardware. So this is happening across many disciplines. So generators, which in some places is up to 20% of the CPU budget. A lot of activities happening to profit from GPUs. Also in simulation with fast simulations. Using machine learning techniques, and also in reconstruction, which for some experiments is a huge part of the CPU budget as well. GPUs will not solve all the problems, of course, so there is an intense R&D program as well in data management. So containing disk needs is a big part of that. Disk is one of the expensive resources, and we need to contain disk to manage the huge volume of data. So things like reduced analysis formats that should be dominant. Most of the analysis should be using those tiny formats. New column data formats, which improve both in size and also access performance by factors already. And finally, also clever orchestration tools that will allow us to use economies of scale and orchestrating different media like tape and disks. So big sites supporting scientific instruments are getting ready to actually scale up on tape technology. So just a quick look on hardware costs. So we were saying, okay, we try to look always at where a flat budget will get us. So these two plots show that the hardware costs as tracked by the CERN Computing Center in the last year. So we see these exponential technology improvements at large scale. The important message here is also the costs are subject to large fluctuations. So these are logarithmic scales, so these fluctuations can have huge impacts. For many components, it's not technology in many cases which drives the prices, but markets and other forces. So the message is that the future cost of computing is almost impossible to predict. Actually, these plots are from several months ago, and probably we know that the current plots will show actually one of these fluctuations. We see that the global supply chain and semiconductor shortages are actually impacting prices currently. So looking still at technology evolution, so this graph shows the processor evolution, in which, okay, we see it from several, in the last decades, we've seen technology improvements based on the number of transistors in a processor has grown exponentially. Since several years, this tendency has changed, and the performance per thread has flattened since we are hitting the Denner scaling limit. And actually, the way to get more performance has been by increasing the number of cores. So we're living in an exponential world, but we realized that since several years ago, the CPU clock is now flat. So the growth will have to happen by parallelization and using distributed resources. So complexity increases. So distributed computing, it's likely to be the future of scientific computing for our large experiments. Mostly, I mean, the people's effort will remain constant as the needs and technology evolves exponentially. So our future looks like, okay, federation of multiple data centers in scientific computing data centers, plus resources like supercomputers or commercial clouds. So quickly, some supercomputers, these are very specialized machines, so some of them will be usable by our communities, some won't. I'll say a little bit more about that later. In terms of commercial clouds, that's definitely a technology that we will be using more and more in the future. Still, a lot of questions remain, and there is also intense activity in the community to try and understand what's the best way for us to use those. The big advantage, of course, is elasticity. So understanding which parts of our workflows are elastic and where we will be using them, and the total cost of ownership. So there are big projects already in the community like LSST, Atlas, and others making large-scale tests in there. In terms of supercomputers, okay, we know that there are big investments. There are big investments in the strategic agendas of most countries. So this is a huge amount of computing that is here to stay, and it's clear that our communities have to make use of those for our exploitation of science. So looking at these big specialized machines in the last years, and currently most of them in the top 500 list have GPUs, special hardware graphic accelerators, and this is a growing trend. So in our community, an important topic is that we need to find the best way to use these machines, and in particular GPUs, for our experiments. So on the one hand, it's okay, leverage this pool of huge resources for the growing need in machine learning analysis, although this is still, in terms of amount of resources, a small fraction of the overall need. Also, supercomputers will play an important role as an opportunity for experiments to access massive amounts of CPU in an opportunistic way, even if it's not, this is not the most efficient architectures for data processing. That's definitely the resources that we'll be using in large quantities. So Still, this is not an easy task, so there are some important barriers to use supercomputers for scientific experiments. Just to name a few of those, so the access policies of these infrastructures are designed for short-lived projects, and our projects are multi-decade, so this is a sociological sometimes and technical barrier. Their networking is not optimized and not planned for massive data in and out, which is what defines our field. And things like typically in many machines there is not even outgoing connectivity from worker nodes, which for distributed environments, distributed computing for like the one we are using, oftentimes is a must. Looking even ahead, I would say that there will be need for using these specialized machines even in near real time or real time. This is already happening partially with the DESI cosmology experiment that is using the NERSC supercomputer in Berkeley for some of its near real time pipelines. Okay, energy efficiency and environmental impact has been mentioned. I definitely wanted to have it to highlight it here. The data centers' footprint in greenhouse gases emissions is a sizable number. It's currently estimated at 2 to 4% and growing. So by the end of the decade, there are some estimates that put it at 10% or maybe more. There are huge uncertainties, but it's definitely a big impact. So I think this is going to be the priority and importance of this topic is going to be greater, and this is something that we definitely need to be prepared for that and start working on that. So we can think of this, or we should think of this from both points of view, from the offer and demand. So from the facilities point of view, higher importance in maximizing cooling efficiency, the use of electricity from renewable sources. So this will be higher and higher in the priority list, I think. From the consumer side, the users and software providers will be thinking more and more in the environmental impact of our software and the algorithms. So when submitting 10,000 jobs or 1 million jobs, people will get used to get back what's the carbon footprint of those algorithms and if there's actually a way to optimize that. So when we think of envelopes, we are used to think of cost envelopes, so we should be thinking as well in carbon envelopes looking forward. So, okay, another way to get more efficient and to get sustainability is to realize that actually many of the large facilities supporting our experiments are shared facilities. So again, this transdisciplinary conversation and common services is going to be key for us to get sustainable. So key points in here, that will help us, technologies that will help us to reduce operational load and to be able to share infrastructure. So it's definitely using open source technology used by many disciplines and even beyond science. Use standards, so we have nice examples of that happening in the last years. So moving to HTTP, OpenID Connect standards, which are actually used in the wider industry, so we can get huge economies of scale. And then as well, middleware to integrate all these heterogeneous resources and to build distributed systems. Just quickly, so I wanted to point to again some example along these lines. So in this year, cloud native technologies are emerging as a standard de facto in industry and in many fields as actually technologies that are enabling a lot of these processes, so that make operating large-scale infrastructure very efficient. So we are in our community, we are definitely looking into using more and more those technologies, and this is operating infrastructure as code more and more, with a central vision of version code and then operating large infrastructures in this way. So sustainability is key. I mean, our scientific programs span decades. So getting our system sustainable is as big of a challenge as actually getting them from the capacity that we need. So the collaboration is mandatory and is the key to get into the sustainability. Just wanted, I mean, I'm pointing again to the strategy, to the update of the European Strategy for Particle Physics, has been mentioned several times these days. So this is just to mention that, okay, this this crucial aspect of collaboration is, especially in software and computing, is pointed to as well in the strategy. So in looking ahead as well at the landscape of scientific computing, the global landscape in Europe in particular, it's very relevant to realize that actually the vision in the European Union for scientific computing, or open science in general, is what's called the European Open Science Cloud, or EOSC. So this is an European Commission-sponsored action, I mean, to implement this vision of an open science cloud data, so a cloud for research data in Europe, in which any researcher would have access, transparent access to data and capabilities to actually share data, etc. So the program to implement this vision is a very relevant one for our field. So I confess I didn't realize there is a talk later on escape, so I will just fly through this information on escape, so you will have many more details afterwards. I just wanted to point to this project, which is because I think it's a great example, particularly in our community. So this is H2020 project, which is now finishing, in which the astronomy and particle physics ESFRIs collaborated to actually prototype some of these technologies with a vision for a shared infrastructure. So this is of huge importance to the future. This will be shown later. So these are the communities in the ESCAPE project. So there is astroparticles, astrophysics, particle physics, and nuclear physics. So this is very much our, let's say, community scientific computing project. Again, you will get details of this later on, I'm sure. Just to mention that, okay, the program of World of Escape is building this prototyping several pieces of several services that then could be used by all of these disciplines for developing their science. And actually, the science use cases that are used to demonstrate and to integrate these resources are actually related to EOIs of this community. So this is all very relevant and important activity. And then just still along these European initiatives, just to point that, okay, on the one hand, next to ESCAPE, there are other 4 large projects, very similar, that agglutinating other disciplines like environmental sciences, social sciences, photon sciences, and life sciences. There is large coordination between all these clusters, the science clusters. So there are position papers that have been published in a coordinated way. And the main message I wanted to convey here, I think, so these communities are organizing to actually have an impact in this implementation of the European Open Science Cloud, to actually highlight the importance of a bottom-up approach in which actually the scientific activities are driving these developments, which is very important. The EOSC, how the EOSC will happen, it's still an open question. So making sure that the science is first and the focus is on the science from our communities is an important activity which will be happening in the next years. So I wanted to finish just going through some challenges as a summary. So just pointing to some of the challenges ahead. So first of all, and has been mentioned, so we are operating in an extremely dynamic environment, and it's basically impossible to make long-term predictions. So I think it will be very important to actually make sure that we have a framework and processes to manage change, so that we are not going to get it right no matter what. So we need to make sure that we have metrics to measure where we are, what's happening around us, and then that we have processes to react to those, and then be ready to change and adopt innovations when needed. There is this massive innovation from industry, and it's very hard for research labs to compete in agility, for instance. But then we need to definitely participate in this landscape First of all, acknowledging that, okay, our big value is our data. So the capacity to generate high quality and high value data, so that's what we bring. And then we definitely need to find the best ways to engage with industry, with this very agile environment, to then integrate and exploit these new technologies in an effective way. So again, along the lines of this dynamic environment, so boundary conditions are changing, are going to change all the time. And then this is a multi-dimensional landscape, so with several trade-offs. The usual, okay, throughput versus cost versus peak performance, but we will be adding as well things like carbon footprint and ease of use, ease of operation. So we will need to operate in this multidimensional landscape, and then optimization in finding the optimal minima. It has been mentioned before. It's going to be a constant activity, let's say. So, and there will be different optimal points, typically for different communities, maybe, or at different points in time. So we'll be definitely, we need to be ready to support hybrid environments. HPC, the engagement with supercomputers, is going to be an important part of the agenda, no question about that. So the engagement with that community, it's a community that historically we haven't had huge ties with. And this is definitely changing, and this has to change more, and the communities have to integrate more and more. So we have to increase the ability for researchers, for us to actually interact with those facilities, to provision services at HPC centers. The architectures on those machines will always be challenging, so we need to be ready to actually make use of them for our software. And then also think about using these specialized machines that come from different time scales to integrate them into our near real-time or real-time processes. So again, distributed computing is going to be key as well. So we'll need effort to study all the issues that we are finding with HPC and commercial clouds, and study the trade-offs. Finally, also long-term data preservation is, of course, very challenging for our projects. So these are multi-decade timescale projects. So the challenge here, and I think it has been mentioned a couple of times in some of the discussion, so it's really an organizational challenge, again, as much of a technical one, which also is true. So we need organizations with sustainable funding models, that are going to be there in 20, 30 years or beyond, which are trusted by the whole community, and with technical expertise on data management and data preservation, which it's a very tricky technical field. You need to preserve not only the data, but also the ability to get information from the data. So this is challenging. There are no obvious candidates or infrastructures in place. We need to think about that and actually make sure those exist. The effort then to support this activity is not increasing, of course, exponentially as the needs are increasing. So we'll need to increase automation to be more efficient. So the complexity of the systems increases, and automation it will be in the focus. So then finally, okay, this is all to acknowledge that the time, the scientist's time is the most precious resource that we have, and we need to reduce the data management burden on them, make sure that this exponential increase in the volume of data and the complexity is not unmanageable for them, so that they can focus on the science. So this is really the focus of all our program. And I think that's all I wanted to tell you.
Okay, thank you very much, Gonzalo. So we've made up a little bit of time now, so I see several questions there.
Yes, I've got two questions. One is that a lot of our efforts is in reconstruction and Monte Carlo generation. And these are typically tasks that are like fixed for a certain amount of time. So I didn't hear anything about casting this, for example, in FPGAs. And that would save at least some power by an order of magnitude or so, but may also make things more efficient and cheaper.
Yeah, definitely. I mean, I didn't mention explicitly FPGAs, but definitely in the R&D programs of several experiments looking at new architectures, FPGAs are a big part of that. Not only GPUs, but actually FPGAs and ASICs. So running specific algorithms in specialized hardware, indeed, that provides huge accelerations in some specific problems. So this is definitely part of the R&D program.
And the other thing is that you say that it's hard to compete with industry on developing new things, which I do not agree on. So the thing that we're doing more and more is machine learning. And we're doing this on von Neumann computer architecture, which is typically very stupid. So developing neuromorphic computing hardware is an edge where we can contribute a lot in development in addition to industry.
Okay. I mean, I agree again. I didn't, when I mentioned that we cannot compete with industry in agility and the rate of innovation, I didn't want to refer that we shouldn't. I mean, there is nothing for us to contribute in that. That's not the idea I wanted to convey. I mean, I wanted to convey the idea that there is this massive innovation coming from industry, and in which that then we need to make sure that we profit from that. But definitely there are places in which I mean, closer to basic R&D, in which I fully agree that research labs and academia are going to be relevant for especially for the vision to be implemented at a longer time scale. So yeah.
Okay, so there's 4 questions I've seen, and I'd like to allow them all. So please be very concise with your question and concise with the response, so we can get moving on, please.
Okay, thank you very much. I will try to be concise. So the question is political. So you have made a very nice overview of the situation of the computing and the evolution for the future. And this is mainly to address the computing need for the future experiment at high energy physics. So we have evolution of the accelerator, more data, and you need to evolve the computing infrastructure and power. Now, to address this problem, all the funding agencies decided to construct the grid infrastructure, now evolving in cloud, now including HPC and so on. But in the next year, some other communities will need a huge amount of computing power to analyze data. For example, Astroparticle. We have SKA, we have CTA, we have Einstein Telescope, and so on. So from a point of view of funding agencies, the question is how this community will integrate, will build up, and will try to have enough computing power to address their needs. Since there are already in place there is already in place a big computing infrastructure for energy physics. So every experiment is aiming to do themselves to build up their own computing infrastructure, or to use the existing one, and then using also the same tool which are already been developed. Because from a funding agency point of view, this is a very important point. Should I funding many different computing infrastructure, or there will be a unique computing infrastructure for all the 3 communities which are now discussing here the future for physics?
Okay, so I'll try to be very brief. I'm not sure if I'll manage to tackle the exact intention of your question. So I think that so we don't. I mean, oftentimes we really see this. We get the idea of the massive scale of computing need for the LHC, etc., on the infrastructure. So I think that a big focus of what's happening, and it's actually also on the software development and actually the development of tools to make use of infrastructure, not as much as the huge scale of the infrastructure. So this is happening, I would say. This is very important part of the activity. and for instance, in the astroparticle or the astrophysics world, to actually developing tools to do multi-messenger analysis, to focus really more on the capabilities, rich capabilities to actually extract and cross-correlate information from different data. This is happening, and I think, yeah, when we think about the challenges and also the priorities for funding, we definitely point also to this software effort for increased capabilities, not only capacity.
Okay, let me sound a very brief but loud warning bell here. Okay, so thank you for your very clear talk. There is a serious and growing concern about the costs of the electricity for this project. Now, number one thing is, please, I say this every time I hear this talk, stop showing the plots of the hardware cost. Nobody cares anymore. At the major labs with a tier 1 center, the cost of the hardware has now been completely dominated by the cost of the electricity. So urgently, we need to start showing those plots with the cost of the electricity on. Second, when you see the plots, and you, I'm sure will agree with me, you will realize that what's being proposed in terms of energy efficiency improvements is completely insufficient. We need a work plan which is going to reduce this by factors, not by 25%.
Thank you. Yeah. Yeah.
This has to be the last one. I'm sorry, I can't. Not this one.
Well, my question was going back to the interaction with industry, because I agree actually that things that were usually done at universities now are done often at this center like DeepMind, etc., like the unfolding of proteins and so on. But one thing that you didn't mention is also about the competition with talent. You know, there is also, you know, how are we going to compete also in this respect?
Yeah. I mean, I briefly mentioned at the beginning as a challenge there, yeah. That's a consequence of this landscape. So there is a huge competition for talent. So it's more and more difficult in our field, in scientific computing, because it's a head-on competition. That's really, really difficult. So from our experience, what I would say is that the tools that, so it's really finding the tools that make our field appealing to. So one thing that we really find a key for us is to exploit to the maximum our deep links to universities. So that's where talent is created or starts. We are typically very, very close to those universities, sometimes embedded in the university. So making sure that process is fully functional, let's say. So the students, as they start in their training, they are fully aware of all these challenges, all these long-term challenges, and our facilities, that they are actually working together with us, so that they are fully aware that, okay, this is a career option in parallel to industry, with which on terms of salaries, we will not be able to compete head-on, but definitely put on the table all the values in terms of basic research, etc. So sometimes I think we are missing opportunities in the sense that, okay, we are very close to these, let's say, talent factories, but we could do better in actually making sure that all the students getting out of the university are fully aware of all this happening there, so that they can actually make the choice. Okay, I can actually have a big impact in these fields where there is and then decide on the trade-off of the type of work with respect to. But yeah, I mean, career path recognition is a big thing in which there is room for improvement, let's say. That's going to be important. Yeah.
Okay, thank you. I'm very sorry I have to cut off the discussion. Very good, and I couldn't allow other questions, but we have to move on. So thank you again. With our funding agencies, and we're very happy to have representatives there. And today, now in our next talk, we're going to hear from the Commission side. So I'm very happy to welcome Patricia Postigo-McLaughlin, who will tell us about the view from the EC's perspective of our infrastructures for fundamental science. Please, welcome.
Hello, good morning. It's an honor for me to be here. It's a little bit humbling to have to follow three very, very inspiring presentations. I enjoyed them very much. and to be given the very uninspiring task of discussing with you how things are financed. I'm actually very jealous that I didn't get the chance of making one of your presentations. I mean, they were wonderful, and I plan to print them and share them with my colleagues. Like scientists in funding agencies, well, I work for the European Commission's Director General for Research and Innovation. So that's the team of people who draft and implement the European Union's research budget. You can address to me all your complaints, although I will not have answers for all of you. More particularly, I work since 2016 at the team that drafts and implements the research infrastructures sub-program. Like scientists, I don't intend to compete with you, but we cannot sit comfortably either on the acquired practice of existing projects that we think have more or less worked. We're perpetually forced to reformulate things and to reimagine what kind of collaborations we should be funding. Of course, this implies, as you well know, trial and error. So there are things that work well, there are things that work less well. And there's always some fear in change and transition. We fear that perhaps when we imagine new instruments, we will lose the engagement of the communities that we had managed to secure. That we perhaps will get worse results. And that's why it's very important that we engage with you. I realize that sometimes we expect you to tell us how to do our work. And we send forms and surveys to you, and we invite you to never-ending workshops. Now they are online workshops, so they're even worse. And I understand it's tiring, but it's very, very important that we understand the trends in your work and what you need, so that we can push you a little bit to do things in a way that works for you, that is perhaps not entirely comfortable because it pushes you out of your comfort zone, but that takes us all in the direction we need and we share, which is to continue capturing that collective imagination and learning more about the world and ultimately about who we are and what we mean in it. I am not very technological, unfortunately, but I think I need to do this now. So my role here is to give you a very general overview of how the European Union research budget supports fundamental science. You know that we don't have thematic programs for fundamental science. The thematic programs are for the classical collaborative projects that are thematic, health, materials, etc. So the programs that fund fundamental science are in the excellence pillar of the program. So there are the collaborative thematic programs, and then there are the excellence programs. And those you know very well, they are the Marie Curie scholarships, the ERC, the European Research Council, which is of course a favorite, and research infrastructures. And the combined budget of these three blocks is 25 billion. Let's not be overjoyed, because the part that corresponds to the research infrastructures sub-program is 2.4 billion. The lion's share, of course, is for the ERC. They have 16 billion. There are 6.6 billion for Marie Curie grantees, and then 2.4 is what is left for research infrastructures. So I know that many of you have been working with the research infrastructures programs more years than I have, and you know it very well, but probably from your scientist perspective. So I wanted to give you, and for some this will be old news, I apologize in advance, but I think it will be useful for others. I wanted to explain to you what the research infrastructures is and why it was created and how it came about. So it started not with the first framework program, but very early in framework program 2. And the first thing that it was created to do was to provide transnational access. And we can look at it, it has been labeled like that by many, as an Erasmus program for big science facilities, for research infrastructures. So basically, if we have a scientific instrument in one member state, it's not a reasonable alternative to have every member state to build every scientific instrument. We know they don't come cheap. So it was clearly a role for the European Union to devise a system whereby an excellent scientist in country A could use a facility in country B when it was not a part of its own national science funding program. So that's how we created the transnational access scheme, and many of you will be familiar with the very annoying forms that you need to fill in. And we devised a system that managed, although it's not very easy because it works in communities and through projects, it's not a stable, permanently open call for access. But we devised systems that will need to be improved in the future, and we will come back to that. We devised systems whereby we could give access to scientists to use facilities in other member states. And I think there's universal agreement this was a necessary thing, and it has transformed the way you do science, and it's useful. That was the beginning of the program, although then afterwards you start thinking, well, if we are doing new upgrades, or if we collectively agree we need a new scientific instrument, how are we going to go about building it? And that's when we created ESFRI, the European Strategic Forum for Research Infrastructures, and you know ESFRI well, and it's a committee that brings together national ministries or agencies engaged with research infrastructures to put together a shared roadmap of what scientific communities will need in the future, and how we can come together to build it and pay for it. The European Union budget doesn't pay for the construction of research infrastructures. You will realize that 2.4 billion over 7 years wouldn't allow for it. But we've created a mechanism, and it's a unique case in the world, and a model for other world regions. We have created a mechanism whereby countries can come together around the table and create subgroups of willing countries that engage in devising a new governance structure for what will be, de facto, an international organization, a research infrastructure providing services and open to scientists coming from different countries. We've created a mechanism to do that. European money doesn't build the infrastructure, but it does give some seed money for the concept study, the design study, for the conceptual report, the technical design report, and for networking activities that create a new governance structure. We have even created a piece of European legislation, which is the ERIC regulation, the European Research Infrastructure Consortium, which is a European legal entity whereby research infrastructures can set themselves up and offers fiscal advantages in terms of providing services internationally and recruiting staff internationally. This is the second part of our work. So there is access, that was the starting point. There was support to ESFRI and the deployment of a shared roadmap, that was the second block. And then the third work has been to group scientists working with research infrastructures in communities and have them create shared roadmaps of what needs to be developed and share the knowledge. I think this is the most fundamental task of our program, because we have really created, and I think it's very special. The European Research Program has internationalized science in Europe to a degree that I think is very easy to forget. But when we look at how science happens in Europe and at how small universities in secondary cities have a significant percentage of the staff engaged in European projects. This is astonishing. This is something we've done over the last 40 years. Of course, science is international elsewhere. The European Union didn't invent it, and it would have happened anyway. But the degree to which we've taken it to the research program, I think it's astonishing, and it's something we should be happy about, because it has created really a new, much more exciting way of doing science together. And meetings such as this one have become a very normal part of our work. And it's fascinating, because I think that in Europe, although we're very fragmented by language and by culture, this diversity brings such an exciting difference of perspectives to meetings such as these, that I think we do these very well together in the Research Infrastructures Program, because from the very beginning, these were very international communities, because big science facilities require to pool resources, not only money, but knowledge and expertise. They were very international communities. They were very open also to working with industry. Okay, yes. So I've done a little bit of archaeology of our grants. And if you've been working on this program as long as I have, you will remember most of these grants. I tried to check with some colleagues whether I had missed one of the projects, and I probably have, because my colleagues have not replied. So you can see here the three communities meeting today. You can see in particle physics accelerators and detectors in accelerators. You can see NSAR, the NSAR Community for Nuclear Physics, and you can see the different communities in astrophysics. You will see that the way we fund these communities is moving from a communities approach to a cross-community approach. And you see that in the lines in red, these are the projects signed recently in Horizon Europe, the latest European research program. And you see there that they're not just for one community. Eurolabs includes nuclear physics and particle physics. And Opticon RadioNet includes optical and radio astrophysics. So there is a paradigm change in how we do things and in the type of projects we finance. And I've been listening to some presentations saying it's very important that we work together, and there was a comment made by Ian about detector technology. And you know, I mean, I've been in meetings where scientists insisted, very passionately, I might add, that, I mean, detectors in these three communities were completely different and that it was impossible to work together. So, I mean, science happens in society and there are trends, and our projects are part of those trends. But you yourselves in your own organization and in the way you do your research absorb those trends, and we all change in the way we devise new collaborations. Because of course science doesn't happen in isolation of society, and now you all have to change your plans because of what's happening in the world, of electricity cost, conflict, very scary conflicts that alter the extent of our collaboration, and how we need to devise our roadmaps in the next 10 years and maybe beyond, let's hope not. And science also happens in society in more subtle ways, in the way technological push determines how we can imagine discovering things. So there have been some recent changes in the European Union research program, and these changes are driven, of course, by what happens in the world. You know that the priorities of the von der Leyen Commission were the Green Deal and the digital transition, and that in a way the EU research program was put at the service of that. And a lot of communities have expressed discomfort at what they thought was a lack of recognition of the role of fundamental science. I think research infrastructure communities are a little bit different because they have always required manufacturing capacity, and they have always had close links with applied science. Of course, the priorities of the Commission have changed a little bit since the end of February, unfortunately, but there is a broad framework that determines how the research program has to adapt to social change, and we all understand that. Then, as regards the specificities of the program, we have been creating a roadmap of communities in Europe, and we have created a lot of ERICs, and now we have over 60 research infrastructure communities, and we face the big problem of sustainability. How are we going to fund all these networks in the future? And I don't have an answer for this. We cannot continue with the budget we have to support each one of these communities separately. So we need to fund ways to cluster you, to create broader collaborations, so as to ensure there's some European leverage money for you to continue working together and sharing expertise. Because the money we have and the people we have in the program have not been increased. And you are familiar with the situation. So we need to, our program, the changes in our program are driven by the multiplication of communities, the sustainability of the S3 roadmap, and also the relaunch of the concept of the European research area. And I know that you're familiar with this concept, which is typically presented in our standard institutional presentations with a set of slides of 20 slides. with very detailed action plans that I find very difficult to understand. So since my objective was not to be boring, if you allow me to simplify, ERA, the relaunched ERA is we have worked over the past 40 years in developing these amazing communities of people for whom it is normal to work with scientists in other countries. Now, in order to increase the impact of the European Union budget, which is, depending on who you talk to, only between the 6 and 10% of the combined investment in science of member states. So we really need to refine and to work very carefully on where is the added value of European money. So we want to create a governance for that program, for that budget. And this is what ERA is about, European Research Area. It's maybe, perhaps I could say, about creating an academy for European level science. And this new initiative for ERA creates new opportunities. There is a research infrastructures working group in the ERA Forum, which is this broad consultation group to discuss what's the future of the European research area. And it's there that you need to make your voice heard regarding the type of collaborations our program should be funding in the future. We have now a method that is based on grant agreements, and the time scale for these grant agreements is typically between 2 and 4 years. So is this stable enough? Could we maybe imagine together a way of working on research infrastructure funding at European level that would be able to offer the timescale of the entire funding program, the 7 years of the framework program? Perhaps we could imagine new grants or framework agreements with some in-between committee refinement discussion of the content. Perhaps we could imagine new type of collaborations that will provide with certainty, stability, better mechanisms for communities to put things in common, but also to work separately when it's needed. And we could perhaps imagine new ways of funding access in a way that doesn't create gaps between grants. So there are a lot of things that I think we can put our imagination to work on together. And I would like to stop here and to hear your views and your ideas, and probably also during the rest of the day and coffee breaks. Thank you.
Okay, thank you very much. I think I might abuse my position as the chair and have a comment myself. So I'm the leader of a small. Sorry, yes.
Thank you.
So I'm the leader of a small accelerator facility, or one of the smaller scale accelerator facilities, and many of the things we've heard about today for the big science that we're doing, the work is actually carried out in much smaller scale facilities, and they're hugely important for the development of everything we've heard about today. So we shouldn't forget the smaller scale facilities, the university laboratories, which are doing an amazing amount of work to contribute to the very big science that we have. And I would say that transnational access is still an extremely important component of the EC funding. And even without these facilities, the ERC grant holders have nowhere to go to do their work. So this we should remember, I think. It's very important. So that's my comment, and can we now move over?
I have a comment to what you've said.
Please.
I don't know how many of you plan to attend ICRI in October, but one of the themes of ICRI is how to create ecosystems of regional, national, and pan-European infrastructures to ensure that there's a clear dynamic for different range of services. So.
Yes, I wanted to ask you, in a science system, at the national level or at the European level, you have the research institutes, and then you have the research infrastructures, which play a peculiar role, and they must have a given weight. So you have shown these numbers in Pillar 1 in Horizon Europe as an example, where the weight of the research infrastructure ingredient in the pie is 1 to 9, yeah? And this is a choice, which may be a reasonable one. I just wanted to ask you, this choice, these ratios, How do they compare, for example, to science policies in other regions, like in the States, Japan? Is it a choice which is deeply thought? Is it a transient thing that moves in a given direction? What do you think about this?
I don't know how familiar you are with negotiations for the EU budget and how they work. This is a very long process and very difficult because you have at the moment 27 governments around the table. The degree of difficulty of reaching an agreement is the very reason why now European budgets are not for 4 years but 7 years. And this has also changed the duration of the research program from 4 years to 7 years to match the life of the European Union broader budget. These negotiations are very difficult. And the negotiations are driven by member states. So it's governments, and in the case of science funding, science ministries who sit around the table. The European Commission makes a proposal, but then the agreement is reached by national governments. I don't think we can compare the European Union Research Infrastructures Program with Japan or the United States because it's not comparable. Because for that, we would have to compare the combined investment in research infrastructures by all member states, plus the European program, which is a very tiny percentage of the total, with the EU budget. Then again, we have a completely different system to agree the budget of research infrastructures because we have ESFRI. And in the US, I don't think it's easier for them because every decision needs to go through Congress. At least we don't require that. But I think it's hugely, hugely difficult to compare. I don't have an answer for that.
First of all, I would like to thank you for your presentation. As somebody who is involved in writing these EU applications, it's always extremely helpful to get a little bit of insight. And I found it also inspiring, so thank you very much. I would like to make a comment, but this comment should not be misunderstood, and it's not so much a comment to you, it's maybe a comment to my NUPEC representative colleagues here in the room. You had a list of all these successful RI projects. There are, I think, 3 or even 4 projects missing from the field of hadron physics, heavy ion physics. They were called Hadron Physics 1, 2, and so on. The present one running is called Strong 2020. And as I mentioned, this is not a comment to you. It's a comment to my NUPEC colleagues, because I think this field is here in this meeting heavily underrepresented.
But was it an integrating activity?
Yes.
Okay, then I missed it.
And a big one, I think, 3 times.
I missed it.
Okay, then I would also like to ask a question. You have heard this morning these talks about these big research infrastructures. You made a comment about the small research infrastructures, which are all important. All suffer at this moment from 2 big problems. Due to pandemic, prices for high technology equipment has skyrocketed. It's very difficult to imagine how we can cope with these problems. We will. There are things going on. The other difficulty we face is that we all depend on electricity. Same thing, prices for electricity are going through the roof, and that hits the small and the big infrastructures. And I just want to ask whether there's some thought about help from the EU for these problems, for the big infrastructures, but also for the small infrastructures.
Well, it's not the first time we're approached with this problem. As you know, the European Commission doesn't set electricity prices. So we have not an easy proposal to make to you there. But of course, this is a problem for everybody, not just for scientists. There are no answers for that. How are we going to handle the big challenges that are planted on our doorstep every day? I mean, there are no answers for that. I mean, it's up to us to imagine every day new solutions. I mean, I would look at you as the experts in generating knowledge to reply to these questions. I mean, how are we going to deal with that? I don't know. When the pandemic started, we said, how are we going to deal with that? We dealt with that probably in suboptimal ways. And we will need to do the same with this problem.
Okay, so please, once more, be very concise with your questions. I'm going to go here, the front row, NASA, and then Marek.
Okay, so it was already mentioned that universities, which are the fundament of what we do, are very powerful in integrating research and education. Now, you talked about the European research area, but there's also a European education area. So what is the plan to connect those?
As you know, we are professionals in creating concepts. That's something we do very well. You should know that at the Commission now, we have new ways of working that have been established across the different Director Generals that require, as we are requiring from you, to work across silos. We accuse ourselves as well of working in silos, in different Director Generals, even in different teams in the same Director General. So we're now having a lot of meetings such as this one, telling each other inside our own organization what we do, and trying to find how we could become more efficient by doing things together. Of course, this is hugely time-consuming, as you very well know, and sometimes you really wonder what you're doing at a meeting. But it is true that sometimes, perhaps not as efficiently or as often as one would wish, we do find ways to create bridges between instruments that make things more efficient and that give birth to new ideas. As regards universities and science, particularly in the Research Infrastructures Program, I don't know if you are familiar with the initiative ATTRACT, which was a call for detecting disruptive innovation in detectors. You would be familiar with that. And they gave lump sums of 100,000 euro to ideas. So typically it was universities or laboratories working with industry. Sometimes industry was not involved, but very often it was. And the ideas that were considered with more potential for new markets, be it inside or outside, have been given a scale-up grant of, in some cases, up to 5 million euro. So this is a very interesting project of how to do things together. But there is a very important part of ATTRACT that is connected to students and training students, because the ATTRACT consortium selects students and gives them a training on entrepreneurship and innovation by putting them to work with selected research projects. And we have found this initiative very inspiring. These students have sometimes helped the project in detecting new applications of their technology that they hadn't thought of, in creating kind of little prototypes. And it's really exciting that we could bring these two streams of work together in a research infrastructures grant. And we're now exploring how to drive this forward, perhaps in the beginning through aeroforum laboratories, a pilot project. So we're still thinking of how improving our work in that intersection, as you said, in perhaps as early as the Future Work Program or perhaps in 2 years' time.
Yes, you mentioned AIDA Innova.
Yeah.
As part of AIDA Innova, we tried really very hard to incorporate more industry in the process, which are fundamental, to create the new detectors that we want for the future. Some of the companies actually drop out in the process because they perceived, especially small companies, the paperwork that they have to do to be too large. I wonder if anything can be done, because obviously, towards, setting these challenges for the future detector, we really need to work together, if something can be done to facilitate that.
I know very well, because I was preparing the signature of that contract, and the SMEs dropped out under my watch. It was very frustrating, because I had to write very long justifications every time. Yesterday I was at CERN at a meeting of IFAST, which is the mirror project for accelerator science. They have 16 companies in the consortium. It's 30%. None of them dropped out. So I struggle to understand what's the difference, because one would think detectors are so connected to industry. I mean, like, come on. I mean, I cannot see the difference between detector science and accelerator science. So perhaps you can tell me why. So I think there is perhaps a human factor, some particular tradition. Perhaps things depend very much on the trust that already exists with some individuals. So I really wonder what will happen with some individuals retire. So I think we really need to reflect hard on that. Because we are approached very often with the request of, think of a new participation model for companies. This is very difficult because we have specific SME-oriented programs, and those have different grant agreements. But the research infrastructure program is very academic. We mostly work with laboratories and universities. We have the modality of letters of intent that companies would, that the consortium would add to the grant agreement to show that companies will collaborate, but outside the consortium. And this is not the same, is it? This is not what we want. It's not easy for us for legal reasons, because of our own financial regulation. And all members of the consortium in a grant agreement need to have the same conditions. So I think you need to work harder on the trust you create with SMEs. And we can discuss that over coffee.
Okay, we're very much eating into the coffee break, so I have to allow the last question from NASA.
Okay, maybe my question is probably on a different grounds and probably also beyond the scope of your talk, but it goes about the vision actually of the European Commission about funding research infrastructures and all these things. If I look at your budget division, you showed that about probably 10% of the money goes to infrastructure, right, from the total. And this actually shows the vision of the Commission, which means that 90% goes to individual and basically competitive things and 10% collective. Now that is a question of a vision, right? So that means the Commission is persuading more competition more than collaboration, if I understand this correctly. And then we come back to this discussion about infrastructures and collaborations. I think the only way to persuade collaborations is to put more money on that and also get less basically on the competition and also relieving also people from this race about submitting proposals after proposals on the individual basis. I wonder what your opinion is on this.
Very brief response, please.
I'm just going to reply to you with a provocative joke. I thought it was you pushing very hard for a massive increase of the ERC budget. Because that's what makes it easy, isn't it? Like individually led research, 100% portability. So we need to think hard of whether what's easy is what's best. And I leave it there because I know that the chairman needs to close the session.
Okay, thank you very much. Very good discussion, and I'm sorry I have to cut stuff. So it's time now for the coffee break, and Mario wants to say something.
Sorry, one announcement. You still see the posters outside. You were all numerous looking at them yesterday, so if you want to choose your favorite among the poster, please write it down in the registration desk. We have a couple of lists. And I guess we come back 11:45. Okay, 15 minutes delay. Let's hope we catch up. Slowly. No, it's on.
Sure. Yeah. Okay, so we need to slowly but surely start the next session. The hard deadline is the group photo, assuming we'll all be smiling on it still. Okay, so we had a very inspiring session so far, including the funding agencies. And now the session that starts now is dealing to a large extent with the computing and software aspects and very different approaches to utilizing it in an optimal manner, also from the perspective of course, optimizing our funding, since this was an important topic. Now, the first talk today is on the precise calculations by Giulia Zanderighi. And of course, I'll just give the word to the speaker.
Okay, thank you very much. It's a pleasure to be here today. So I was asked to talk about precision calculations. And when my friend Laura here looked at the program, she said, what kind of title did they give you here? And in fact, so what I will talk about here is precision calculations for high-energy colliders, really. Now, we know that high-energy colliders are the one tool we have in a controlled laboratory to really explore the highest energies that we have. And we know also that, in general, studying matter in these smallest or largest distance scales always allowed us to improve our understanding of the world. And so to understand why we do precision calculations now at colliders, I would like to discuss an example. So, for instance, in the 19th century, people were studying the motions of planets. They were looking far away as far as they could, and they could, using Kepler's law, compute the orbits of those planets. And at the time, it came as a big surprise when they realized that they could predict very well the orbits for Jupiter and Saturn, but not the one for Uranus. So what happened is that having faith in the Newton's laws, and by combining really very precise measurements of this orbit and precise calculations, they could really predict the existence of a new planet. And really by comparing calculations and measurements, they really knew where to point telescopes to actually see this planet directly. And in a similar way, we are very excited about gravitational waves. We have been very excited in recent years, but really the first evidence for general relativity came again from anomalies in the orbit of Mercury. So precision, in a way, is a tool to see that there is something which you cannot really access yet directly. And this has been successful also already at collider experiments. For instance, if we take LEP, the LEP experiments did not have enough energy to produce a top quark. But by essentially looking at scattering processes like this one, which are sensitive through quantum fluctuations to the top quark, by measuring this precisely and computing these things precisely, they could actually establish the mass of the top quark with quite some good precision, 10 GeV precision here. And this was very useful for the Tevatron experiment. When it then turned on, it had enough energy to produce the top, but they knew where to look for the top quark. And this, I think, is the spirit in which these precision calculations are done. Now, traditionally, we think of E plus E minus machine as precision machines, essentially because it's a clean environment. These are elementary particles that collide, but proton collisions are somehow more messy because the states that collide are bound objects of quarks and gluons, but they are thought more of discovery machines because you can explore higher energies more easily. Essentially because the protons are more heavy, you can accelerate them more easily to higher energies. But as I showed you, I mean, this perspective changed with the Tevatron and really changed a lot now with the LHC, so which I think is, I would say, a hadron collider precision machine. Now, when I talk about precision here, it's not the levels of something like G-2, of course, but you can look at many measurements where you really reach a sub% accuracy. For instance, here I show a few examples. This is a kinematic distribution for a Z boson-Drelian pair. This is a very clean measurement. You have only leptons. And you see that over many orders of magnitude, you have a % precision, really. There are limits also called what we call anomalous couplings, which are ways to look for deviations from what the standard model predicts. And here again, the LHC is producing limits that are better than the lab ones, which was our clean machine plus and minus. We heard in the first day about the Higgs mass measurement, which is also very precise. Now, this is not a very impressive measurement, however, because the Higgs mass, the Higgs decays to 2 photons. So all you have to do is you reconstruct the invariant mass of these two, look for the position of the peak, and this is your mass. But much more difficult is what is shown here. This is the W mass. Now, this is a measurement that has been produced really this month, which has a 9 MeV precision. This is 0.01 precision. This is absolutely amazing for a Hadron Collider machine. And in fact, so the CDF collaboration announced this, and announces in this form that it had tension with the standard model. So this tension, you see it in that plot. And of course, this was picked up very recently by many newspapers, so probably many of you read something about this. And you see, for instance, in Italy, this is called the Rubias W boson. But you see somehow how things can be picked up in somehow here talking about shock results or surprises and so on. Because, of course, this, if taken seriously, this is a very significant deviation from what the standard model would predict. And this can be achieved, of course, only if you have precision. Now, this brings me to the standard model. I want to have this slide. I think everybody has seen this, but I think we really have to keep in mind the standard model is the legacy that we have from 20th century particle physics. It really combines in a beautiful way quantum mechanics, quantum field theory, special relativity, unifies forces in a nice way, and there are these kind of anomalies like the W boson mass now, where there are some tensions, but so far it really reproduced all laboratory data. And so when we test the standard model, the role of precision is really, so what is the role here? And how do we achieve precision? So first, this somehow, a measurement like a W boson mass measurement, or many measurements at the LHC now, this reaching this precision is due to performance of the accelerator machines, the experiments, the detectors, computing, also in terms of analyzing, storing this data. And thanks to this, I really want to say this precision is there, is a reality, it's not a future opportunity. But of course, what's the future is this improvement that is ahead of us. And this precision, in a way, doubles the role of machines like the LHC, because they have been designed as discovery machines to see the Higgs boson, to see new physics. But at the same time, if you see something new with this machine, you can also study the properties of what you see. So this is happening, for instance, for the Higgs boson. And I will spend a little bit of time on talking about the Higgs. But also, really like in the case of Uranus, this precision brings in new possibilities, complementary to direct searches, these so-called indirect searches. And again, I really want to stress that theory here becomes really crucial to enhance sensitivity to maybe small effects. So how do we achieve this precision? Well, we can look at things like cross sections, or simply we can count events, number of Higgs bosons that are produced at the LHC, for instance. At the end of run 2, the machine produced about 7 million of Higgs bosons. And we can compute this number in what we do an expansion, a series expansion. So in the lowest order term, essentially you pick 2 gluons from the protons, they collide, there is an effective interaction, and the Higgs comes out. And this calculation was done in 1977, long time ago. But you see, it's far away from data. Then the next approximation includes one sort of quantum fluctuation. And this, you see, you get a large correction here. This was also computed a long time ago. And the next order was computed at the beginning of 2020, of this century. And in a somehow breakthrough calculation now for this process, we have 3 orders in this expansion. And this is really an astonishing result. So here, I also show you how many integrals you have to compute. You have to compute 70 millions of these really very complicated integrals. So to achieve this required, of course, theoretical advances, really, but of course also a lot of computing power here. And what I want to also stress is that if we would not have these calculations, we could not understand LHC data at all. If we would have only the first two terms in this expansion, we would see a disagreement. We could not understand even how many Higgs bosons are produced, let alone study the couplings and so on. So these calculations are absolutely crucial. Now one can ask, but why do we need so many Higgs bosons? Well, this physics is very complicated, it's very rich. It's rich, I mean, it's a sort of gift of nature that the Higgs boson has a mass of 125 GeV. If it would be slightly lighter, essentially we would not see many decay modes. And the same is true if it would be a little bit heavier, we would only have access to this decay mode. But it really lies in a spot where we can access really very many decay modes. This is something we didn't know and makes this physics very rich, but at the same time, the largest branching of the Higgs is to BB bar, and this is very difficult because also gluons go to BB bar. It's very difficult to see. So the cleanest is something like Higgs to photons. And this, you see, in fact, it's very small. So only 1 out of 500 goes to photons. And that's why you also need so many to produce so many. But that's not only this. It's also that the Higgs, in fact, can be produced in many different ways. And one of the most interesting modes, I want to show it here, this is the so-called TT Higgs, in association with top quarks. We know the Higgs couples strongest to heavier particles. So this, the coupling to the top is very large, and this is a very important mode. It's also very important because it allows you to measure the coupling here of directly the coupling with the top. But now you also see why things get so complicated. It gets so complicated because, okay, the Higgs decays, the top decay. Here I didn't even show the decays of the W bosons, they all decay. So these final states become very complicated. And there are many other processes that have the same final state but don't even involve the Higgs. So when you talk about precision, you don't only have to compute something like this precisely, but all the other processes. And this is kind of shown here. The red that you can barely see is the signal. All the other ones are things that you have to compute and subtract to extract the signal. So that's why things are really very complicated at the end. And however, it was realized really early on that these somehow more complicated final states are very important. And I would like to guide you through a little bit really in 5 minutes through the story of precision calculations. And I think this story starts with, in 1984, with the super collider was discussed, was being proposed. And if you look in this paper here, you see that they were realizing that processes like 2 protons producing essentially 4 jets, which in this language means 2 gluons producing 4 gluons. They realized that they were very, very important, that they needed to be computed, but they also said that it was impossible for them to calculate this at the time. Why is that? Even in this lowest order approximation, where there are not even quantum fluctuations, you have a lot of diagrams. All these diagrams correspond to terms that you have to compute and so on. So at the time, to do this calculation by hand, something like this, which is 220 diagrams, was considered impossible. But 2 theorists took up this challenge, and in 1985 produced a result that a formula for this which would fit in 8 pages. And at the time, they used the most advanced computers they had to do this, and the most advanced theoretical tools. Okay. But then they concluded this paper by saying that, that they were hoping to obtain a simple analytic form, making the result not only an experimentalist, but also a theorist delight. And having now a result for this, a numerical result, they in fact could guess a very simple form for this, at least in one particular case where 2 gluons have a different polarization from the other ones. Rather than 8 pages, they could fit this in one term here. Now this, you don't know what these are, but these are simple complex numbers that depend on the kinematics of these particles. These particles are labeled 1, 2, 3, 4, AB. AB are the one that have a different polarization. And then you see this looks really extremely simple. It's so simple because these 2 are different from all the other ones. If you look at this 1, 2, 2, 3, 3, 4, you can even generalize this to an arbitrary number of gluons. And they could guess this form, and then at the end they could also compute it. So this was the beginning of these perturbative calculations. And after this really breakthrough, I would say, by Park-Taylor, people understood how to compute leading order, so the lowest term that we can compute. But the calculation of the next correction, the one that involves these loops, integrals, really remained a big challenge for a very long time. And you can find many, many papers which essentially the outcome of the result is one calculation. So it was always one calculation for one specific process. There was essentially no automation inside. And then things changed. In the next, I would say, 20, 30 years since really Park-Taylor, there have been a lot of somehow conceptual breakthroughs, and I cannot cover them, but the essence of this was that it was understood how to connect things that involve a quantum loop like this, so a loop. It was understood how to cut it in such a way that you could relate it to lower order amplitudes, which you knew how to compute. So this was then considered a solved problem, conceptually, but also practically, in the sense that people then developed tools, automated tools that allow you to specify a process. This is one of the many tables that one can see in papers. You see, you specify a process, a Higgs with 2Z bosons, or a Higgs with 2 tops and a jets, whatever. And you can get out a number for the cross-section at leading order and at the next to leading order. So this next to leading order is considered solved now. However, as I already showed you in the case of Higgs, also in other cases, we see that this next to leading order is not sufficient. If we look at LHC data, this is another example, for instance, dye boson production, a very clean process. You see that really you need to go one order beyond compared to this next to leading order. And this is somehow one of the challenges now. This is the next challenge. You see the first results appeared here, and now you see again an explosion of results here. This essentially covers now at the LHC all processes where you scatter 2 protons and you have 2 particles coming out. So this is something that we can compute. But something like the process I showed you, T bar and the Higgs boson, something which is 2 to 3, is still really very difficult, and we don't know how to do this yet. But again, all this required theoretical understanding, but also a lot of computational challenges. So this, for instance, now summarizes a little bit recent highlights in this perturbative frontier. So here, essentially, here you see this is number of loops. So these are the orders in your expansion. The more loops, the more precise. And here somehow you get a bit closer to reality, however. So you have more particles in the final state. And these are recent things that were computed. Maybe I don't go into the details. But all these calculations, still, you see the multiplicity is very simple. You have maybe 2 tops in the final state, or a Higgs and a W, and so on. We have also different tools, which are called parton showers, which allow a fully realistic description of the final state. In this case, you give up on computing these loops, but you try to emit radiation to all orders, but in an approximation. And then you can also have realistic models which parameterize the fact that gluons actually then turn into hadrons, and what we observe are hadrons. So we have also these very nice tools, and they essentially enter all studies. And one of the directions, and obviously they are now, is to try to combine somehow these parton showers with including also more loops here. Right? So at the moment, for instance, we can describe processes which have 2 particles in the final state, keeping the best perturbative accuracy, but also this parton shower to have a realistic simulation. So this is a little bit what we can do so far. And now I want to say, what does precision really buy you in this? And here I have to be a little bit technical, but so in essence, we have not seen a new physics yet. So this suggests that new physics is heavy. If new physics is heavy, it can be parameterized in an effective Lagrangian. So we take our standard model Lagrangian and include higher dimension operators, but these effects are suppressed by this heavy scale of new physics. And the advantage of this approach, which is used a lot, is that it's really rather model independent. So you can start with many models, and it gives rise to this type of operator. So it's a model independent way to try to parameterize new physics. Now, if you change your theory, of course, all interactions will change. And so, for instance, if you look at the couplings of the Higgs boson, you will see modifications in these couplings, which is suppressed by this heavy scale. But one of the points that I want to make is that if you can probe these couplings at higher energies, these modifications, in many cases, are enhanced by the energy that you probe. What this means is that there is really a trade-off between precision and energy, meaning if you can explore the TV energy scale, for instance, with 10% accuracy, you can get bounds that are comparable to LEP, which was 100 GeV, but had per mil accuracy. So there is really a scaling of precision like energy squared. And so there are different ways to read it. One way is that if you have precision, you can work at lower energies. Of course, the best is to go to high energy and highest precision. There's no question. And as I said, I would like to finish maybe with also a few words on the Higgs. I mean, we know the Higgs boson was a milestone in particle physics. It's the only scalar fundamental particle we have ever seen, so it's something really completely new. We have never seen something like this. And it also mediates a new interaction, the Higgs boson, what we call the Yukawa interaction. People talk about the fifth force because it mediates a new force which is different from all the gauge interactions. So I think it's clear that this research program has to be very long and very thorough. And what I would like to show here is what have we actually probed of the Higgs interactions. After, the Higgs was discovered now 10 years ago. We are approaching the 10th anniversary. So one can say, okay, what do we know now? And this is summarized a bit here. So what I show in green are the interactions that I say we have established. By established, I mean we have a 5 sigma evidence for that. So of course the precision can improve in these measurements, but certainly the Higgs interacts with the top, the bottom, the tau, and the WZ as predicted in the standard model. And you see, these are what we call the third generation fermions and the gauge bosons. When we go to the second column here, these are the, sorry, this is the third, this is the second generation, and you see that here we know already much, much less. And so we have first evidence, for instance, for Higgs to muon, but to really conclusively establish this will require another 5 to 10 years of data at the LHC. And for CHIME also we are seeing some hints, some evidence, but if things evolve, if you simply scale the luminosity, you will not be able to measure this at LHC, and this really will require a future collider. The same is true for the Higgs interaction, self-interaction of the Higgs. And then when we look at the first generation fermions, unfortunately, I don't see that there is a clear route here, how to really establish this. So this is a bit what we know, but I also want to stress why are we insisting with the Higgs? I mean, so far everything looks a standard model-like. Does it really matter to measure this interaction so precisely and so on? And okay, again here, I want to write one equation. So this is the Higgs Lagrangian. This contains essentially the Higgs potential and the way this particle interacts to everybody else. And the point is that in this Higgs Lagrangian, there are really all the seeds that are needed for new physics. So all the big questions that we have, or not all, but a number of big questions are to be found here. There is a connection here. Okay, so the first term, for instance, relates to this gauge invariant mass generation of gauge bosons. This is something we had not seen before. It's something new. This is the mass term for the Higgs boson. And with the Higgs mass, there is a big problem. The problem is that the Higgs mass is very small, while naturally it wants to be very, very heavy. And it's not about the fact that there are two different numbers, that this can always happen, but the fact that this small number is very unstable. You need to fine-tune it. And so this is what we call this naturalness problem in the Higgs. There is, you find the quartic coupling, and this connects to the shape of the potential. I will come back to that. And questions of stability of this potential. And then These are what I call this fifth force. These are the Yukawa interaction, the interaction of the Higgs with the fermions. And this also connects to the fact that we have three generations with very different masses, and we don't understand why. It connects to the problem of CP violation, which is, of course, very important. So altogether, when we talk about precision measurements, these programs are really much broader than just measuring parameters. What you really want to address when you do this, to address fundamental problems. For instance, is the Higgs boson a portal to dark matter or to something else, to hidden sectors which we don't know? And if there is something, it will leave traces in the couplings of the Higgs boson. So there are really many, many questions that can be studied. And I want to just show two examples where if you have theoretical precision, you get somehow new possibilities. So one has to do with the coupling to the charm quark. I already said this is very, very difficult to measure. But it's very important because, so we typically like to have this plot. This is the mass of the particle and this is the coupling. And in the standard model, this is a line. So this is really the footprint of the standard model Higgs is establishing this line. And you see that, however, when the particles alight, it's very difficult. You have large uncertainties here, because the coupling is small, so it's difficult to probe. So one idea that was proposed is the following. Typically, you look at the decays of the Higgs to charm to measure the coupling of the Higgs to charm, but you can also do something else. So the Higgs, I told you, predominantly is produced by two gluons. There is typically, in fact, a top loop, and the Higgs comes out. And the Higgs gets a transverse momentum if there is also a gluon emitted in that. And then you see that you can have a similar mechanism where you have a charm core as well. So typically when you compute the amplitude squared, there is an interference effect between this top loop and the charm. And interference are particularly nice because they create distortions in distribution. So rather than moving things up and down, this really distorts. And distortions are easier to compute and easier to measure. And these are somehow shown here, the distortions that you get if this coupling is modified. And so this has been then implemented. And this, of course, will require the high luminosity LHC run. But it looks like one can really constrain this coupling much better, using really precision calculations and precision measurements of something that per se has nothing to do with the charm. The last example I want to show is going back to the Higgs potential. I think the Higgs potential has this form, and people maybe have seen this already. Often it's shown as a Mexican hat. Here I showed now the two-dimensional form. So this is our standard model potential. But when we measured the mass, we essentially measured this quadratic term here. That's all we have measured so far. And in fact, the potential could have a different shape. For instance, could have another minimum here. And establishing this is really one of the big answerable questions, one of the guaranteed payoff of a machine like the LHC. Now, once you, after electroweak symmetry breaking, you can write this potential in this form. So as I say, when we saw a Higgs boson, we measured the Higgs mass, and we measured this term here. The potential is connected instead to the coupling of the Higgs to the Higgs itself. So to the, what we call the Higgs self-coupling. And typically, to measure this, you need to produce a Higgs that splits into two Higgs bosons. And this, of course, is very difficult. One, because this is really much more rare than this one. In this case, there are some unfortunate destructive interference. So it's smaller than one would expect, but that's how it is. It is very small. And then, of course, each Higgs boson has to decay, and you pay a price for the branching ratio. Either you have a very small branching ratio and a clean final state, or the final state becomes very messy. So this is, in fact, very difficult. We have bounds on this lambda, but they are about a factor 5 to 10 within the standard model value. So it's something that we cannot say we have actually established. And so one of the ideas to really exploit precision here is that you can actually become sensitive to lambda also in other processes, again, for this kind of loop fluctuations here, loop effects. So if you can compute loop effects very precisely, you can compute processes that then involve only one Higgs boson, and there are in fact many that are sensitive to this, you can also become sensitive to lambda in this way. And this is, for instance, has been implemented already in Atlas. And of course, this will again improve much more with the high luminosity run. Okay, no. So I come to my conclusion. So I think with the discovery of the Higgs boson, I think particle physics has entered now a new era. We have a beautiful theory. We know it works very well, spectacularly at colliders, but we have many indications that this is not the end of the story in particle physics. We have dark matter, we have neutrino masses, which are not accounted for in the standard model. So we know that we have to go beyond. And in the coming years, of course, we will explore this TeV energy scale more and more. And this exploration, I think, has to include this fully fledged Higgs program. I think I convinced you about this. In general, a thorough precision program. I talked more about precision in the Higgs, but of course, one can talk about precision also in many other sectors. In general, these indirect tests of the standard model, null tests, and so on. And also, of course, an exploration program going to higher energies with more luminosities. One can become also sensitive directly to new physics. I think we live in data-driven times. Progress, I think, will not come from theory, but I think will come from experiment. But theory is really crucial to interpret data and to enhance sensitivity to possible anomalies and new physics.
Okay, thank you very much for this very interesting talk. I think we have time for 2 quick questions. Yes.
So, thank you very much for an impressive talk. I mean, we clearly get the idea that you can make the calculations of next to leading order to accuracy. You mentioned 1 per 1,000, but then you have to produce the hadronization. I think that somehow that looks like the ugly duck. I mean, within this theory. So my question is that if you are not so accurate in the hadronization, let us say if you believe your hadronization models up to 1 per 100, then it's not much point in going further. Beyond, if the hadronization is energy dependent somehow, you couldn't make accurately, I mean, this expansion to discover new physics, isn't it?
Yes, so there are a few things, of course. Yes, this is always a problem, but so there are observables that are much less sensitive to hadronization, they're not very sensitive. There is a way to, I mean, we have hadronization models, and of course, I didn't talk about this, but there is also a lot of progress in trying to improve these models. It's true that it's not a calculation from first principle, it's more a modeling, but these models are also tuned to data, so they actually work really very well. But it's true, I mean, so going to this higher precision at some point makes sense only if you can match this precision in the experiment and if you have control on hadronization. If for whatever reason you manage to get rid of these hadronization effects. Take the W mass measurement. They have a lot of super clever tricks on how to circumvent the fact that at the end there are things that we cannot compute at this level, but they can extract it from data then.
Thanks for the nice presentation. At some point you wrote an equation there that said precision goes like energy squared. I have some problems with that because we know that we don't know what's physics beyond the standard model if it exists, but of course we expect it to be unitary. So for sure amplitudes will never grow like energy squared. That means that one has to qualify this sort of statement. For sure it's good going to higher energies, but...
Okay, so first of all, this is not always true. I said there are examples where these higher dimension operators essentially involve derivatives, so involve that grow with the energy. At some point, this picture has to break down. As you say, once you see a real grow in energy, you're hitting these unitarity violations, and then it means your effective theory is not working anymore. Yes. No, but I think, okay, the message is maybe a little bit too strong, I agree. But there is again a trade-off in exploring high energy and higher precision, yeah. But yes, one has to be very careful, yeah.
Okay, I think we need to move on. A lot of interesting discussions can happen during lunch, I'm sure. So thank you again, Julia. Okay. So the next speaker is Philippe Chomaz. I hope I pronounced this approximately correctly.
Fine.
On the quantum computing as another aspect of our involvement.
So first, let me thank you, the organizer, for inviting me. In fact, I'm not completely sure I want to thank you because this gave me a lot of work, because it's a kind of new presentation, because it's a kind of new topic in our field. So let me start with a short introduction about quantum computing, and this started somehow in the 80s with this famous conference by Richard Feynman. And in this conference, he was focusing on simulating physics with computers, and he devoted a full chapter about quantum computing. And in fact, he was saying that nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. And in fact, what is quantum computing is nothing but using quantum mechanics phenomena, such as superposition and entanglement, in order to perform calculation of a completely new type. So let me go through this story, and let me first start with the known quantum revolutions, the well-established quantum revolutions. And let me start with the first one, which is the quantum revolution of physics. And in fact, we know that 1 century ago, we physicists invented quantum mechanics. And in fact, quantum mechanics is nothing but saying that matter, light, and interactions are composed of particles which are governed by wave mechanics. You see, this is a very short summary of quantum mechanics. And this led to an amazing revolution of technology. In fact, it was the source of the digital revolution of our society. And we are all in that today. Let me focus a little more on maybe first, let me go back to stress what is this revolution. This revolution of technology is the fact that we are using macroscopic quantum systems. Of bosons, let's think about lasers. Of fermions, we can think about electron and electronics. We use also the fact that energies are quantized and other quantum numbers. And with those properties, we were able to build a great ensemble of technologies which allowed us to transform all information treatment in our society: computing, sensing, and communication. So if I want to focus first on computing, because this is my title, and I want to start with somehow the history, we can go back to the invention of the transistor in 1947. Then 12 years later, we were able collectively to, the physicists, the scientists, to build the first integrated circuits. And this was the beginning of electronics and the electronic treatment of information, of computers. And so, just to recall, the information can be in those computers, they are just built as elementary information 0 and 1. And then those different information are processed through transistors in order from an input to produce an output with logical gates. And this is nothing but a Turing machine. And this means that you have information at the entrance and you have another processed information at the exit. Keep that in mind because it's very difficult, very different when you discuss quantum computing, because it's not a Turing machine. You have to propagate as a unitary transformation your information, initial information. So it's very different. And what we know is that this was an amazing adventure, an amazing revolution. And we know that computers have been able to develop tremendously and to have this increase of computing power of a factor 2 every 18 months. And this is thanks to this Moore law. And here you have the Moore law with the size of the transistors and the number of atoms in the transistors as a function of time. And two things. First, it was decreasing exponentially during years and years, decades. But today, we are reaching the limits of 1 atom per transistors. This means that we are not reaching it. I mean, we are converging to it. And this means that the exponential decrease is stopped. So the question is it the end of the story? And since I am only 5 minutes in my talk, probably you all understood that it's not the end of the story, and you read my title. And in fact, it might be at the same time the problem and the solution. So this is to move to my second part. Second part is just this new possible quantum revolution, quantum 2.0, and the possible new disruption of the information technologies. And it's, I said, possible because, in fact, we are starting, but it's not yet done, and it may fail. We hope it will not, but it may fail. So just to be sure that you follow me up to this point, I recall quantum 1.0 is using macroscopic quantum systems. This means many quantum degrees of freedom. And with those microscopic systems, you process macroscopically the quantum information. Now, what is a new revolution coming? The quantum 2.0. The idea is to go down to a single quantum degree of freedom, or to be able to master every single degrees of freedom, quantum degrees of freedom, and so to work at the level of individual quantum objects. And maybe then to couple them, but to control always the state of every system, every individual quantum object in your system. So on one side, you may say, well, it's not a big deal, and moreover, it will resemble, because we are discussing quantum degrees of freedom. They are the same on both sides. You can decide to look at one electron, but before we were moving an ensemble of electrons. We call that a current or whatever, and it can be also the spin current, so spintronic. But on one side, you have degrees of freedom, and there are many. On the other, you just have a single one. But so you discuss the same thing. You discuss photons, you discuss electrons, you discuss currents. So it looks like the same. But the fact that we move from macroscopic ensembles, statistical ensemble of quantum system, toward individual states, this is a huge jump in the way you treat information. And in fact, the first huge transformation is the fact that if you control every single state, you access to a huge space of all possible quantum states. So first, to keep in mind, you access a huge space, and it will be 2 to the power the number of objects you are looking at if they have 2 states. So it's a huge space. And the second thing is that at the same time you are accessing this huge space, you access very strange quantum properties which have not been used up to now, or little used. Because superposition is not really used today. Non-locality, you have already some KKD, quantum key distribution available, because in fact this quantum revolution is going on since the 80s. So you can buy systems which are distributing quantum objects which are entangled, and you can use that to do some cryptography. So it's already in the shops. So it's ongoing, but you have superposition, non-locality, and entanglement. And entanglement is a big jump forward. So to go in this discussion, let me just recall in one slide, not more than one slide, superposition and entanglement, to be sure that we are all remembering well and you are adopting my vocabulary. So superposition, you all know. If I take the example of a quantum object with 2 states, the simplest one I can imagine, 2 states, only A and B, and we will call it 0 and 1 to make it the symmetry with classical bits, and we call it even quantum bits and in short, qubits. So we know that in quantum mechanics, since we are wave dynamics, this means that the system can be put in a state which is a mixing of those 2 elementary states. So any kind of superposition and 0 and 1 are possible. And we are used to say that their quantum objects are simultaneously in the 2 states. And this is the very famous Schrödinger cat paradox. Entanglement. Entanglement is the same thing. In fact, entanglement is nothing but superposition, but in the space of quantum system composed of several objects. Let's start with 2. And if we start with 2, I put here the basis, two objects with 2 states. So you have 4 possibilities, 0, 0, 0, 1, 1, 0, and 1, 1. And in fact, you have then 4 possible elementary states of your system. And we know that you can put the quantum system composed of those 2 objects into any kind of superposition of those 4 states. And if I generalize, I put not 2 but n, you will put the state in the superposition of the 2 to the power n elementary states. And this is the huge space of this Hilbert-O-Fock space. And not only it's a huge space, but it is very different than what we think in classical dynamics. And to show that, and if you like my small cubes, you can look at my small cubes. But to show that, let's take just a very simple state with 2 state mixed, 0, 0, and 1, 1. And you can do whatever you want. You cannot factorize this into a well-defined state for the system A, the first qubit, and a well-defined state for the system B. This means that you cannot think the quantum world with objects which are independent. You are forced to think them as coupled in some way, and we call it entangled. So in fact, the coupled quantum objects, because they live in this very large Hilbert space, they can have those very strange mixing, which means that you cannot isolate the property of each object. You are forced to think to the global stuff as a unique quantum system. And this is first very good, because then you access this very large space with 2n dimensions. And quite often when we discuss quantum computing, we discuss speeding up the calculation. But we should first think about the fact that this dimension, as far as information is concerned, will never fit in classical computers. Every time you add a new qubit, you multiply by 2 the memory. In the Moore law, you need to wait 18 months to be able to do this. So you see that if you add 10 or 100 qubits, you will wait millions of years in order to have the memory to put your quantum problem in the computer. So this is the first point. Acceleration will come next. And then the acceleration comes from the fact that when you have these mixed states and you let it evolve through quantum dynamics, all the different elementary states, the basis, is evolving at the same time. So it's a kind of massive parallelism in quantum computing. And of course, this is so strange that you all know the stories that even Einstein was not agreeing with that. And I think I put aside the transparency that you have it because I was thinking I will be too short. So you have the Einstein-Podolsky-Rosen paradox and the Bell inequality in the slides on the Intico. The key point is that through the experiment of Alain Aspect, but also, for example, the experiment in particle physics, like the one by Mittig in '76 for protons, we have demonstrated that entanglement is indeed a real property of physics. This means that we have not a kind of hidden variable somewhere bringing back quantum mechanics to classical mechanics, but those states are really outside the classical world. And those new different possibilities opened by being able to control every individual quantum object is opening a lot of possibilities. The first one is the fact that if you can control individual objects, for example, a single spin, and measure a single spin, you are reaching an ultimate sensitivity. So you are transforming completely the sensing. For example, in Saclay, we just reached the sensitivity to 1 single spin. This means that we're able to measure the elementary magnetic moment of a single spin. It's 1,000 times more sensitive than before. Then, because those objects are entangled in a single quantum object at a distance, you can change communication, and this is everything about quantum communication. And it's not only to be to have some cryptography and which cannot be violated. It's also that you can couple quantum objects at a distance, and you can maybe couple quantum computers at a distance. And the last point is the fact that if you go to many, many degrees of freedom and you're able to master this massive entanglement, then you can have a huge computing power. So those are the promises. But then what are the difficulties? Because if everything would be so simple, we will just buy today quantum computers and they will be working. Because today you can buy quantum computers and they do little. But it's just the beginning. So first, it's not so easy to master single degrees of freedom, quantum degrees of freedom, because you have to master the fabrication. And we should have in mind the transition between the first transistor and the very last processor, from 1 transistor to 54 billion transistors in the chip. So this is a huge effort as far as fabrication is concerned. And it took years and decades. Second, I forgot to recall, but you all know that in fact quantum mechanics is probabilistic. And when you want to know something about what did the quantum computer, you have to measure. And when you measure, things are becoming probabilistic. So you have to deal with a type of calculation which is probabilistic in nature. This means that you have to repeat many times and have statistics, so be clever in such a way that what you measure will give you the answer. So you have to be smart enough to use the computer, which is now probabilistic. And last but not least, and the most important and the most difficult, is that entanglement is very fragile. Any type of coupling with the environment is introducing decoherence. So you are losing superposition. So you go from quantum to classical. You are losing entanglement. You go from quantum to classical. And this is very difficult. And we have solutions on paper, like error corrections. But for example, today we believe that to correct 1 qubit, you will need thousands or 10,000 of other qubits coupled to it in order to protect this qubit against decoherence. This means that you have an overhead factor which is something like 10,000 or more. So you have to have 10,000 qubits, physical qubits, in order to have 1 logical qubit protected. Or some other people, smart people, are looking to more robust qubits, like for example, CATS qubits. But I can elaborate during the question, but not right now. So new ideas, but this is the key point. And this is why, because of the very big promises that it can be a disruption of the world information system we have on Earth. But at the same time, it is so difficult that in fact, different countries are putting billions on the table. And by the way, this is soon more expensive than the FCC. So, I mean, when you say, well, if FCC is expensive, I mean, we should compare. The Webb Space Telescope is very expensive. Quantum computing is very expensive. Today, everything is expensive, you know, even the benzene. So what can we do with quantum computing in nuclear physics, particle physics, and astrophysics? So first, let me introduce the different type of calculation you can do. You have 3 types. The first one, the historical one, the one which came the first, with D-Wave in particular, since more than 10 years, is just to do quantum annealing. This means somehow you do some kind of adiabatic transformation. You rely on tunneling and other effects in order to find where is the ground state. So you do some kind of optimization problem. So it might be good for optimization. It might be difficult, but it might be optimization. The second one is very, very interesting. It is called quantum simulation because, in fact, you prepare a wave function, psi 0, and then you have a quantum, you master the quantum evolution, you master the Hamiltonian dependence in time, so you can have a fixed Hamiltonian or you can have a time-dependent Hamiltonian, and you master the unitary transformation over time. And it's a kind of analogous type of computer. You put something and you measure the end. And the good point, and it's important for us doing quantum mechanics, that in between it's solved by itself quantum mechanics. So it is computing a propagator from an Hamiltonian. And the last one, which is maybe the more versatile one, is to do almost the same thing, except that the you cut the different unitary transformation into small unitary transformation, which are doing very small, very simple matrices exchange, like Pauli matrices, in U space of qubits. This means small unitary transformation, and we call that gates, because they are similar to the gates in the classical computers. And so you do many different evolution of your qubits. They're all unitary, except when you measure something. In between, you can measure something, and then you become probabilistic, and you go out from the unitary transformation. But you have different unitary transformation. And in fact, you have the small drawing below. And if I figure out where is the laser, here, but it's a laser for blind people. So you have here at the entrance the different qubits. And conversely to the Turing machine I showed you before, in which you had information at the beginning and you process it and you have another information at the end, here the qubits are conserved. It's a unitary transformation, except when you do some measurement like this. It's a symbol for a measurement in which it becomes probabilistic. So this one is very versatile. What are the possible technologies? And this is simple. Any kind of quantum degrees of freedom you can imagine. So, of course, for example, currents, like superconducting currents, electron pairs, photons, electrons with, for example, spin, for example, in semiconductors or NV centers, nitrogen vacancy centers in diamond. Or you can have ions in ion traps, atoms or molecules in, for example, optical traps, and many others, including Majorana's particles. And this, I mean, it's a nice bridge, because if we can build a Majorana qubit in solid state, you know that it will be protected by topology. So it can be very difficult to lose coherence. But at this point, no Majorana state, a quasi-particle in solid state, have been observed and measured. But it's one of the possibilities, many possibilities. Then what are the possible algorithms, what you can do with those computers? 4 types. First one, historical one, you use a quantum Fourier transform. It might be an exponential increase of the speed. And the best known is Shor algorithm in order to factorize the numbers. And it's used for cryptography. It can also be a problem for the Bitcoin. So you can see why maybe people are putting money in quantum computing. Second, search algorithm. You have a database, you want to search for a pattern. Or you have an ensemble of graphs, you want to analyze those graphs. So very useful algorithm. Not exponential acceleration, polynomial acceleration. It's already something. Optimization, all types of optimization, including machine learning and optimal paths. So this is opening a huge space of possible applications. Here I put image processing and market evolution just to give 2 of them. But keep in mind optimization and neural, artificial intelligence and neural networks. Exponential acceleration. And the 4th large category is to use a quantum computer, like Feynman was saying, to compute quantum mechanics. And this means that you can do quantum many-body problem. And by extension, because then this means that you can do variational approaches, because the quantum problem can be recasted in a variational approach. So you can do variational approach, and you can extend that to many different problems, like linear and possibly nonlinear algebra, like differential equations, and so on and so forth. And you may have also an exponential growth. I put here weather broadcast and calculation of molecules, quantum chemistry. Then what can we do in our fields? We can use all those different applications. And this is a work in progress. So you can invent your own algorithm. Maybe in 1 year, the next talk will have 5 large categories. Who knows? But today we have 4. And then, of course, you have all the possible use and mix of those categories. Huh? But then we can think about data mining, signal treatment. We can do imaging and data analysis, think about neural networks, and we can do also all kind of theory and simulations. So let me give you a few examples in the last few minutes. The first one I want to put, since I'm a nuclear physicist, is to show you the first calculation of a deuteron. So what they did, they took an Hamiltonian, Pioneer's effective field theory at leading order. They took an ab initio approach, one of the best one we have, and then they use a variational, one of those algorithms, it's called, solving quantum mechanics, it's called variational quantum eigensolver algorithm. And what they did is that they took the best at that time, so either IBM with 5 qubits or Rigetti with 19, but they have used only 2 or 3 of those qubits, because if you put more, then you lose entanglement because of the noise of the errors. So they look at first 2 and then extend to 3, and they were able, with this, I put the unitary operator, which is the variation of the trial wave functions they have used, as a function of an angle theta, which is a kind of mixing of entanglement in your system, of your 2 first level of the deuteron, in the deuteron in an harmonic shell model, and you do the mixing in order to have the wave function. And you see that, in fact, the solid curve is a theory. It's very simple. You can do it by hand, the theory, only 2 levels. And the boxes and different boxes are the 2 calculations with the 2 computers. So, but it's the first, and you see, they were able to publish the deuteron with 2 states in Physical Review Letter. So, you see, instead of doing complex calculation of many-body problem, you go back to the deuteron and you publish in Physical Review Letter because you use some fancy new hardware. Next, and I put some wave to recall you and to wake you up, this is wave dynamics. So, CERN. CERN have launched 2 years ago, a little less than 2 years ago, a big initiative, and this is very nice. If I look at the different topics they want to cover, they are covering, they go from computing, sensing, communication, and theory. And they have, only in 1 year, a lot of good results, and they are building a whole community. And I put here some of the papers. Let me focus on some of them. This is a gauge theory computation on the quantum computer, or how to solve gauge theory on a quantum computer. A simple one, U1, but it's a step in the right direction. The next one, this one, is to use machine learning in order to be able to apply machine learning to high energy physics. So, and you have many others, and you have a website, you can follow what they are doing, and you can join the effort, because they are not only at CERN, it's a world community, international community. You have other initiatives, and I put here on screen 2. The first one is in the Cantera, which is a kind of joint venture between the different funding agencies in Europe in order to fund quantum approaches. A joint venture between Portugal, Italy, and Latvia. And the second one is an initiative at IN2P3 in France. And you notice that I'm from CA and I put forward the IN2P3, so you see that France is evolving. Just kidding. And let me show you one result from the first one. This is a paper looking at track reconstructions and to see how you can speed up or not, how much you can speed up for this elementary problem in particle physics. So you see very concrete examples. Now, to do those calculations, we need platforms, we need computers, and you have a lot of initiatives, not only in US, also in Europe. The first one is a European initiative called connected to Euro HPC, HPC-QS. And this is the idea to have in different HPC centers, high-performance computing centers, quantum computers. And the first one might be because there is a call for tender, might be with some atoms, and maybe 100 or maybe 200 atoms connected, 200 qubits. And it is coming soon, this year, or end of this year, or beginning of next year. And connected, we have in the French plan, we have the fact that we will not only buy a first computer, but we have, in the next 2 years, we will buy 2 other quantum computers and connect them to to HPC center in order to have the very same community capable of doing high-performance computing to also start to look at computers, quantum computers. And just let me show you, because in this work we have 23 million already secured just to do applications. So we do many things. I want to focus on WP4 I am constructing, which is focused just on simulating physical systems. And we will do ab initio calculation for nuclei, for molecules, for solid state, and for phase transitions in different materials. And those are the very same quantum many-body problem. They will have bridges between them. And we will also do partial differential equations. And for the aficionados, I recall that the Euler equation is nothing but the Schrödinger one, so you can go from one to the other easily. And so this is the end of my talk. So the revolution is ongoing. We should think that it's the same transition as going from the blackboard to maybe the computer, but we should not forget that, in fact, we are just at the beginning, and in terms of physical error rate, we are still very bad, and number of qubits, we have still very low, few hundred, maybe 100 or 200, I say, with the Pascal machine, and we have to go all the way to millions. But I mean, we did that for transistors, so why not for quantum computers? Thank you.
Okay, thank you very much for this very interesting talk. We again have time for 2 quick questions. So one is here.
Very nice talk. I just had a quick question about the entanglement. Once we have many qubits, is it well understood? I mean, with 2 qubits, I understand the entanglement, but once you have 10 or 20, will there be many-body interactions between them? Is that well understood?
Yeah, so 2 answers to this. First, I stress the ASPE experiment and what was done with protons, and this is only 2. The Google paper discussing supremacy with 53 qubits, in fact, you can see it as a generalization of the entanglement and like some kind of Bell type of inequality for 53 qubits. But it's a matter of principle, how many qubits can we entangle? But probably I come from statistical physics. And I think what is killing entanglement is statistical physics. This means that coupling to complex system. And computers, we want to interact with them. Otherwise, they will compute by themselves, and we will never know. So from first principle, it will be very complex to be able to interact and not perturb. So how much we will be able to go, I don't know. Some people like Daniel Evsev is telling me, but Philippe, we don't know. Maybe there will be a limit, a maximum number in nature of things you can entangle. But I don't believe that. But it's open, because still, remember, what was the jump forward with the ASPE experiment with only 2? And now we focus on saying we do quantum calculation. But what we really do are physics experiment with many entanglement of many objects. And this is really fantastic. This is why the paper by Google is not because it's supremacy compared to the classical calculation, which is important, because this you can always argue. But the fact that they were able to entangle 53 objects, this is amazing.
Yes, you compared very nicely classical computing to quantum computing at the beginning of your talk. In classical computing, most of us are very familiar, or reasonably familiar, with the concept of a transistor and gates and so on. And then we jump a big leap to programming in Fortran, if you're old enough, or maybe in Python. Yeah. So what about the case of quantum computing? Is there already work going on at some places in some programs in this hidden layering operating system or whatever, or programming languages specific to that? Is there an effort going on for that?
No, it's a big international effort to have, we call it the full stack. This means that you have the hardware, but then you need the control command, you need the computing system in order to master this. Then you need some software, like the languages at a very low level. And then you need all the different levels, including the compilers, and to make it simple. So this whole stack is a big competition at the international level. Because maybe, because first, sometimes it's easier. It's less expensive than doing the real computing chips, quantum computing chips. and it will be used at the end. Maybe the operating system. I mean, for example, Windows. We almost all use Windows, and this is just a layer. So there is a big international effort all over the different levels of this full stack of technologies we should develop in order to have quantum computers. And you have very simple interfaces, for example, with IBM and others, where you can play yourself with quantum computing. And they do all the job in order to then send signals to the chip. You don't have to care about sending signals to the chip or to the atoms in an atomic network.
Okay, thank you very much. The discussions then we defer again to lunch. Okay, so we move on. We're basically in time. So let's see if everything works.
I think it's me, yeah?
Yeah. I'm just waiting to... So now we are going again for the completely different aspect again of the computing with the Giovanni Lamanna.
Okay. Let me thank, first of all, the organizers, the chair of APIC and UPEC for inviting me. As it was in 19, I'm supposed to talk about open data, I will talk about Escape, and this time I will move to open research, new paradigm, challenges and opportunities. Indeed, it was already a positive experience during the first symposium, because it was the time where I had the possibility to propose, and we got support from Jenas about the evolution of our program in Escape with the Open Test Science Project. But anyhow, I will come back on this point. Therefore, I will briefly introduce the science cluster of particle and astrophysics, particle physics, astrophysics. Then I will. There is something more that has happened during this couple of years, namely the European Open Science Cloud Association is established, an evolution of the current European Union research ecosystem that is acknowledging the achievements of the science clusters and their role for the future. Therefore, I will report briefly to all of you about the evolution of the science clusters. And then there is also more to say about the fact that the scientific community belonging to Jenas, but even more, because there is also the astrophysics component, so Jenas++, at large are exploring, we are exploring and positioning ourselves for the challenges in Horizon Europe work program. Therefore, I will try to have a mention to something that Patricia knows as well about the evolution of classes in collaborations, open collaboration, and the work plan for in Horizon Europe. So, in a nutshell, you see the project. You see also that we are almost finishing, because we have a semester before concluding, and the H2020 grant. Everything is built around the listed here S3 research infrastructures, from particle and nuclear physics, accelerator base, as well as astrophysics and astroparticle physics. These 9 projects compose the science clusters and the Escape science cluster. Escape was supported by an ad hoc action from in H2020 from the European Commission, asking for connecting these 3 infrastructures through cluster projects. We have also 4 more clusters, EOS Clive for health science, the ENVI for environment, PANOS for Newton light sources, SHOCK for social science and humanities. Altogether, we cover more than 80% of the S3 arrays. And the goal was at the time to try to bring the communities around the concept of the European Open Science Cloud, in particular working together, building cross-fertilization environment to let's say, progress all together in preparation of the next generation projects for making data and scientific research, more largely speaking, fair, fundable, accessible, interoperable, and usable. How we started this in 2018? We started by discussing together and understanding that was a clear avenue concerning open science and data fairness for the joint astronomy, nuclear, and particle physics communities. We built the initiatives on community complementary excellences, in data stewardship, the virtual observatory astronomy, the expertise from high energy physics and nuclear physics in distributed large data management. We wanted to build on existing synergies. This is an example this community uses to work together. Recognize also that the communities will be exascale data generators, but in the same time, you have seen the wonderful lecture from Philippe. We are also always at pushing the state of the art of technologies. And furthermore, that is important, new generation projects were evolving towards the working function facilities of open observatories. Therefore, there was a global need of implementing the open access to data and long-term curation. And finally, we felt, as a community concerned, by connecting the S3s in construction to ask that, I repeat again, at that time was just a concept. I wanted to show you something that is important. The action of the clusters, which was instructed by DGRTD in Brussels, was specific, was asking, the budget was defined pro rata of the participation of the legal entities of the S3s. Furthermore, although centered around the S3s, the way we built the participation of national institutes was asking each single arise to team up with a few national institutes that participate, and the budget were redistributed correspondingly. Therefore, in the common work program, you have ARISE focusing on some specific activities and the national institutes teaming up with them. And we have, therefore, let's say, the steering or the supervisory action guaranteed by the committee of the directors of directorates of these legal entities, and the chairs of APEC, Astronet, ECFA, NUPEC, plus a representative from ESA are members of our external advisory board. Therefore, we conducted our program by mixing up or by completing the top-down and bottom-up approach. Now, staying still in the description of ESCAPE. The work program is built around these 5 activities, work packages, but there are also 5 main components. First of all, we work together for the very first time in building the data lake, new scalable federated data infrastructures, because we need to guarantee the data infrastructure to have the data accessible and interoperable, whatever is the discipline among our large domain these data are coming from. The other important point was visioning what the new next generation researchers were expecting. They want to interoperate, they want to bring information from different projects. Therefore, we have to deploy scientific platforms that in the work program were tailored on the specific need of CTA, SKO, high luminosity LHC, but in the same time, we built the services in order to have the platform for interoperable data and therefore to host also transversal projects. We were asked also to anticipate the startup of a repository, of a catalog, domain-based catalog of software data sets that are going to be then part of the global ISC architecture. And then we supported also the update of the upgrade of the virtual observatory infrastructure that had to face the large volume of data coming from the next generation facilities, but they also allowed us to have a plan in training for data stewardship standards in which they have expertise. And then what is specific in our cluster compared to the others, that we leverage the experience on citizen science, and we also envisage to make our efforts not only on a science project, but also to open up the data with, let's say, to fellow citizens as a function of their need through a dedicated gateway. All these can be seen in another way, in this graphical way, and represents in our vision our ISC cell. Again, at the time, there was no architecture, there was a concept and political need of implementing from the Commission what was established by the European Union member states. Our community was able to interpret and give the shape to such a concept. So you see here the data lake, that is the horizontal level, which interfaces with hybrid computing, any kind of resources, and the network. On the left-hand side, you have the catalog represented, and then you have the different way you interface the infrastructures. For the following, as I did a couple of years ago, where I presented some preliminary plans, first prototypes, I will highlight, without entering in details, just a few of results that are now really operational components of the escape ISC cell for open science. One is this. I will not enter in details, but just to show you graphically that what we achieved was the first main data lake operating infrastructure. It is based on the partner institutes that you recognize. We have a pilot cluster of centers, and furthermore on top you see the common choice done about services for storage, for middleware, for orchestrator. And this is completely new, bridging sociological barriers. We work together, and when we work together, what I mean is that we, high energy physicists, did not evangelize anybody, but on the contrary, we work together, and you see how we work together. First of all, we had a first dress rehearsal by assessing the first prototype deployed, and then we had recently a data analysis challenge where each S3s participated in performing what they think was crucial for their pipelines, data management, processing, analysis workflows, and we succeeded in this. I don't give the details, but I am really proud to show you how we all worked with and were in the same boat. For instance, let's take nuclear physics fair. In the data challenge, they were able to assess the raw data injection, storage, preservation, and data lake, and then the processing by users by reinjecting then the results in the data lake. If we take the neutrino ChemTreeNet, we had a focus on the offload data from the storage in the Toulon coast buffer to Barcelona and other replica sites, when we had the running on the calibration pipelines and then storing back, to have also, after the workflows, also the scientific ready data products for user consumption inside the data lake. For CTA, gamma ray astronomy, and the precursor magic in La Palma, the focus from the community was on the distributed data reprocessing taken in La Palma Island. From Atlas, we had a focus on a large experiment demonstrating the open data capabilities. In particular, we have the usage in data lakes of the ad hoc open data software. If we take LOFAR, that is also partner of ESCAPE, that have the observation, the data, it was, and I have chosen this one to give you the feeling of what represented this data challenge. We had the possibility through the data lake to have injection of data from the radio observatories, combine data from other wavelengths, retrieve this data from the virtual observatory, using to retrieve and allow the users to play this data from the ad hoc ESAP analysis platform, and then after the recombination of the multi-wavelength analysis, re-put inside the data lake the data. The same with SKO, we have the global test scale from Australia, South Africa, North Hemisphere centers with data management services that are commonly adopted, developed and adopted within this large community. We also have some European participation in ESCAPE focused on the LSST, Vera Rubin Observatory, where there was a simulation of the observation, leveraging the telescope local storage data replication, and also the data management cycles, incorporating also SLAC in this. From CMS, the focus was on the heterogeneous resources interface with data lake, but also with the control access of users for embargo data and then performing the analysis from CMS pipelines. So all this just to give you the taste of such a cooperative work that was done, what I meant when we focused on each of the S3 project, but the solution is unique. The choice is unique, the data lake will be for all. The same second highlight that I want to mention here is the catalog. The software is an important part of the digital objects that we have to open up and that we have to make interoperable and accessible. Therefore, it was extremely important also to anticipate, compared to the original work program, the deployment of the domain-based catalog of resources, data, and software. This is the OSSR that is now available, and this will be part of the EOSC exchange, or let's say the set of the global EOSC tools for our domain-based. Here, again, something that I showed already a couple of years ago, we use the resources that we have on the market, that are used also in the private sector, for maintaining the continuous development of the software, then publishing this in Zenodo, having containers for deployment, and at the same time the Dockerization for the registering, and then the Zenodo coordinates to bring all the information into the EOSC cell and make everything available to the users. Users are all of us, scientists. Concerning software, an important and successful action was conducted around the training. This is the example of a training, a summer school that was organized to support researchers in programming. Was done with the precursor cluster asterisks in astrophysics, and then it was conducted. It was continued now in ESCAPE with extended to particle physics. You see already in these numbers that are mentioned in these slides the enormous success that we have with this school, that we are continuing also this year or next month in June. Now, just a very briefly few highlights concerning the science platform. I said before that the ESFRI is customized the platform, but again with the same approach of using the same services for all. But we also had to perform the structure of a science platform to host other needs, like the test science project that I will explain in a while. But here also we have finally an operating platform that was in this example specifically tuned to radio astronomy, but the services that are listed here are the same for all. The same, I can show you how the platform are also populated with the interface for citizen science projects, with the link to the Universe system, and with the virtual observatory services that are pillars of the ESO portal as well as ESA, but ESO is our partner in ESCAPE. And all of this allows to prospect our project, our community, towards the next challenge in the EOSC context of creating EOSC web of fair data and services for science. Indeed, the EOSC cell allows to do this, to implement this kind of web of fair data and services. And what we used to call now is the virtual search environment. And this, I want to say, it is extremely important, This is a buzzword that we are using, but it is an important word because now it is the system in which we are hosting the Jenas transversal so-called project. It is important because it is the way the scientists sees the escape EOSC cell. And furthermore, it is in the policy at European level, and again, it's not coming from the Commission, it's coming from the European Union member states, asking the Commission to make action in order to do this. Any scientific results cannot be any more limited to a paper published in our journals. We need to publish also to make accessible all digital objects that are behind that. Therefore, the VRE is going to anticipate such a paradigm and will build this based on the requirements of the community. In a few 6 words or 7 words, what we do with VRE, a scientist can explore the analysis which has been published. It can reperform the analysis because it has the data, the software, the workflow, and the platform to run the analysis. Can repeat it, can modify because can decide which subset of data can be used, can implement his own analysis, new analysis algorithms, new workflow, repeat, modify, and therefore upload his or her own analysis, publish new results, because that's the goal of open science, achieving new scientific results on top of the published one. And last but not least, we enriched the VRE with a sort of scientific social network, because we need to guarantee the acknowledgement and the rewarding of all scientists committed in open science, and therefore producing and publishing the results in such an environment. So as I said at least a couple of times, and I repeat again, this is the framework which is going to host the test science project. I said I was happy because at that time, during the first symposium in 2019, presenting ESCAPE said, this is the idea that we had in our proposal, but was a concept like really was neither an achievement, was really just to test the complete EOSC cell with the 2 ideas, the indirect dark matter search with the gamma rays and the combination of gravitational waves and other wavelength for fast radio burst and gamma ray burst. So at the end, what happened that, and we discussed all together with the chairs of our consortia, that the European Commission was, and S3 board was looking for something to enhance the researcher participation. This was the proposal coming from us, and this proposal was adopted also by all other clusters and was part of an ad hoc action from the European Commission, which is the EOSC Future project, one more H20 project, which allowed with the dedicated funding to fund the test science project or science projects conducted by the 5 science clusters working together for the first time, therefore increase the budget of the clusters and update our work program. Although this is a project which is led by DG Connect, that is led by the Pan-European infrastructures that you see on the right side of the slide, and the main goal is to make bridges on developing technologies together independently on the scientific domain we belong to. So what we decided was to support the request from community of focusing on dark matter and the extreme universe science projects that are clearly linked with the EOIs in Jenas. You have seen some posters of postdocs working on these science projects. To summarize very quickly, in the dark matter science project, we have some pilots. So you see in the table that we have some participation from direct detection, but then mostly from ATLAS, Collider, Astrophysics, and direct detection, ChemTriNet, and CTA. We have some specific goals of producing some workflows or producing some exclusion curves or combining all the results. All of this will be done into the EOSC cell. It will be done in our virtual research environment. And we also imply the development of ad hoc artificial intelligence algorithms to reproduce the analysis. This is one of the projects which is in a poster that I mentioned here, just to show how, in the same time, there are postdocs, physicists, and data scientists working together, because from one side there is the goal, the scientific goal of the pilots that are proposed. From the other side is to customize the environment, technically speaking, with all the services that are required to perform all this analysis in open environment. Again, if we consider the Extreme Universe Science Project is a series of pilots that are listed here with different requirements, I will go very quickly to say that in this case, what is interesting is that I mentioned this example of the gravitational waves, where we try to see how the services for open science can be even adopted for low latency analysis, let's say real time or close to detector, close to sensors. From one side, there are again development of machine learning analysis, for instance, in this case, for the Wavefire project for real-time classifiers of gravitational waves, but at the same time, by combining following astrophysics alerts, other messages from other experiments, from other projects. Or we come back to dark matter within the extreme universe, addressing fundamental questions by hosting the simulation studies for the perspective of next generation project like Einstein Telescope. So I go fast. I will take 2 minutes more. One more point is the cooperation among clusters. This has been, you can see there are publications about position statement document of the clusters together about the future. And what we realized is that the clusters are important platforms for domain-based actions around open science, because they conjugate these three actions: the bottom-up approach, the top-down, and the horizontal, because we leverage also university and national institutes. And this, through this positioning, all clusters are moving now towards collaboration, and this is the case of ESCAPE, that is going to become an open collaboration agreements and commit in the next program of the research infrastructure in Horizon Europe. I give you just 2 slides to show you. First, the fact that the work program that was presented in the published document, and it is part of the work plan, and this answers a little bit the presentation of Patricia. From one side, there is the destination actions that are in continuation with our work program. From the other part, we look forward to have an operational role in the European research area. I'll let you read the topics. Those will become work packages, and around all of these work packages, we count to support project in response to clear Horizon Europe lines that are looking for cooperation of clusters together, as well as domain-based dedicated efforts around software, around the technologies which concern particle physics, nuclear physics, and astrophysics. Okay, I will skip just this to tell you that one more goal ahead of us are the European data spaces, the sector data spaces. If you think that global competitiveness and data sovereignty in Europe do not concern us, is really something that we have to rediscuss together, maybe by panel discussion dedicated. But there is a clear societal progress in general which is connected with data, and we can do a lot about this with our disciplines, with our projects. I give you some examples here, but I would like to just probably focus on, I'll let you read what is written here, but I want to focus on something which was the content of a presentation this morning about the detectors. You see, when you show a slide, when you build with the slide all the partners, the historic evolution of one single detector, and then at the end of your talk, you say that we have to take care about next generation. Please consider that there is any landing web page or landing environment where we find all the digital information in order to build this legacy know-how about detectors, and with the generation we need to build this in order to then allow next generation to build FCC or other large infrastructures. I'll let you read here my conclusion that is valid for all the science clusters. Thank you.
Okay, thank you very much. In the time of, so in the spirit of being late, we'll skip the questions to lunch and we go to the last speaker. Thanks. Graham Stewart, who actually was also involved in the Russia project, for example, that was mentioned here. We'll talk about the second part of the convergence and sustainability of our software that was discussed also this morning.
Let's see if I can get this to work. Okay, great. So yes, thanks very much to the organizers for the opportunity to speak about sustainability and future of software frameworks today. I think by the agenda, I have approximately 0 minutes for my talk, so please forgive me for delaying your lunch. Yeah, okay. If only I could make it a quantum presentation and then I could give you all the slides in one go. That would be really great. But anyway, let's go. Let's try and move through relatively quickly. So I want to just give a little caveat that the examples I will give will be from high-energy physics software because that's what I'm familiar with. But the general points that I'm going to make about the challenges that we face, both the technological challenges and the sociological challenges of how we make our software sustainable, I think actually apply to all the fields. So I think there's something here for everybody. So let me start just by talking about the technology concept. These diagrams have already been flashed, but yes, we are still in the era where Moore's law is maybe in hospital, but still alive for now, but we know that this will come to an end at a certain point. There's certainly credible roadmaps out for the next few years, which will increase the transistor density. But as Gonzalo already told us, the problem is that because of the failure of Dennard scaling, we're limited in clock speed, so we're very limited in the amount of throughput that we can get from a single computational thread right now. And so to increase our performance, we have to go more and more parallel. So this is the challenge that we have. And of course, let me emphasize as well, that almost all of the hardware that we use once we move away from the detectors and the experiments is essentially commodity type of hardware. So we don't drive the market, but we have to take the best that we have and make the best of it as well. So what this is driving, of course, is many alternative architectures for doing computations. We move away from this kind of golden era that we had in the 1990s, when to make your software faster, all you had to do was go to the pub and wait, and then it would just get faster. It was great. A lot of drinking was done, I have to say. But now we're in a much more challenging era where the performance is very much flattening off, and we have lots of these alternative architectures. GPUs, as Gonzalo already pointed out, are probably the one that dominate more than anything. It's not to say that there aren't innovations in the CPU realm as well, and we see that coming more and more through into the commodity computing. These are not terribly difficult transitions, but the transition to GPU actually is a challenge, and that's to say nothing of FPGAs, which are very interesting and are becoming a bit more accessible to generic programming and may be an important part of the future. One general point I will make is that we have to really worry about data. You know, we are data-intensive sciences. If you do not get the data flow path right, from the storage system through to the registers on the device which are actually going to do the computation, your performance is dead. So you really have to care a lot about this data flow architecture. And all of this, I will say, feeds into this green computing and reducing the cost. I mean, even if somebody said they would be willing to pay for the number of CPUs that we would need for high luminosity LHC, I think, frankly, it would just be a waste of money, and it would even be immoral to use up that much power for high luminosity LHC computing. So we have to adapt here. Now, let me flash up one slide about sort of other technologies which kind of drive this forward in a generic way. Machine learning, we've heard quite a lot about during the conference. We've been using it for a while. It helps enormously already in maximizing what we can get out of the data that we take. One little point that I would make that maybe points in a direction to the future is that the models which we use compared to things which are happening in industry are very simple right now. So if you take the kind of the bleeding edge of machine learning models, that would be something like GPT-3. which is this autoregressive language generator, which now gets good enough that it can generate text that's almost indistinguishable from what human beings can write. This is 175 billion parameters in it, which is just staggering, okay? So maybe we are scratching the surface in terms of what we can exploit for machine learning. And I also think that auto-differentiation, which we heard about in the context of the detector design yesterday, is going to be a terribly important innovation in the future, because this could actually revolutionize the way that we design our physics analysis, because we can connect both ends together through a differentiable system. Although, as we discussed yesterday, there are technical challenges to overcome. And Philippe told us a lot about quantum computing. It is a super hot topic. I think most of the work which I have seen presented in the field is exploiting the way the industry is using this for neural networks. But the really exciting thing would be actually being able to do direct physics calculations on quantum computers. But can we solve the technical problems in order to get, you know, the qubits that we would need remains an open question. So this certainly could be revolutionary. Okay, I must flash up a little bit about the end-to-end storage and networks, and just to remind people that we talk a lot about the computation, but the data storage is actually more expensive for the LHC, and we are inevitably using hierarchical storage. So we have very slow tapes, but they're cheap to store the data on, and they give us a very high data safety. We move to disks because they're the best for the bulk online storage that we have right now. And of course, everybody's laptop now, it has an SSD in it. Still remains more expensive than a hard drive. That may change in a decade, let's see. But certainly for that last layer of storage, for the very fast access of data, you want to have this at the top of your storage hierarchy. And just to say a word about network capacity, which has grown enormously over the lifetime of the LHC and really changes the way that we think about doing data processing, because actually the closest place for the data might not be the tape system, it might be that other site that's 1,000 kilometers away, because it's much easier to move the data over the network than to do a tape recall. Okay, resource scaling computing, I think Gonzalo covered this extremely well. Let me only make the point really here that we see the introduction of alternative processing architectures are key. And as a high energy physicist, I realize I have to share all of this infrastructure with many other sciences now. I think one thing ESCAPE has done, referring back to Giovanni's talk, is it's really helped us to consolidate what the lower levels of data access infrastructure are actually going to be. And that is a tremendous contribution to the fact that the sites don't have to install different file transfer protocols for astronomy and for nuclear physics and for high energy physics. But really what's driving this, where we are going now, is heterogeneous computing, where we have CPUs, we will have GPUs, maybe you have FPGAs somewhere in the mix as well, and we have to adapt our workloads to that. So this is all, of course, in line with the European strategy, which had very positive things to say about the development of software and computing, but I won't go into the details. I think people are very familiar with that now. Now, in high energy physics, we use software, of course, at every stage of the process, from event generation all the way through to final analysis. Roughly 50 million lines of code, at least, actively used. So this is an incredible legacy and a code base which is spread across all different projects and all different experiments, with new experiments coming online all the time. Now, when you want to optimize this, of course, what you want to do is look at the resource consumption. So you always couple the software to the computing that you're going to do with the software. But of course, some things just come up again and again, like the simulation of electromagnetic calorimeters is very expensive in high energy physics. So this is something where we want to pay attention and we want to really optimize that. So let me move a little bit, just do a quick tour through the software that we use in high energy physics and say what the critical points are. Now, we had a really nice talk on the precision calculations at the start of this session, and you see from the European strategy that actually these red bars here, sometimes it's the theory calculations which are the most painful in terms of evaluating the overall error. So we moved to NLO, we moved to NNLO. The thing which is extremely painful from the experimental side are negative weight events when you do the actual matching to the parton showers, which dilutes the statistical power. And they're really expensive because you don't just generate the event, you have to go all the way through the simulation and then subtract it out of the histogram at the end. Okay? And we see that there is a kind of a mismatch between the incentives for the theory community to advance the calculations which we can do, and for the experiment community, which needs to generate billions of events and to do so efficiently. But we are doing work to try and help bridge this gap, in particular through the HSF and through the SwiftHEP project in the UK. Now, things are improving, of course, in the event generator realm. There are new matching schemes which are available. So this NLO delta actually reduces the fraction of negative weights. One can use machine learning actually to sort of post facto process the events and reduce the amount of CPU which is wasted. And actually, even if the experiments go and they do a sort of very detailed analysis of what's going on inside the event generator, you can improve your productivity with the event generators. That's an extremely nice paper from Atlas that demonstrates how to do that, and you essentially win a factor of 2. Now, porting to alternative architectures is something that's very active in the field as well. And you can see very impressive speed ups. So this sort of 550 compared to a single CPU core. Okay, maybe that's a little bit unfair to compare it to a single CPU core, but you certainly have speed ups which are factors for these calculations, because they are actually very suitable to do inside GPUs, because they're very parallelizable, they're very independent from one another. So there's a lot of good work which is going on there to increase the computational efficiency of the event generators. And I wanted to tell just a little bit of a story as well. I think this is an area where there's still a lot of low-hanging fruit. And one of the things that the SwiftHEP project has contributed to is an extremely impressive speed up of some of the calculations which are done with Sherpa and open loops, where it was noticed that we were wasting a lot of cycles with calls out to LHA PDF that we didn't actually need to do. So they have optimized this, and it's incredible because it started off with this purple here, and actually where it ends up is you can barely even see the purple anymore. So there's clearly a lot of work that can be done quite quickly and positively to improve the calculations. Now, wrong place. Where are we? Oh, yes, machine learning. Okay, and detector simulation. Yes, detector simulation is very expensive for us. We spend a lot of CPU cycles doing it. Machine learning as an alternative way of generating events to particle tracking is extremely interesting. Honestly, I think it's turned out to be quite a lot harder than people thought. It was really easy to get something that kind of looks like a shower. It was very difficult to get something which actually matches the physics of a shower that you would get outside of Géant 4, but we are getting there, and you can see some improved models here, this green curve, which gets the minimum ionizing particle response from the calorimeter dead on, whereas we couldn't get it with the models before. And I think also moving towards things like meta-learning and transfer learning, as we make our networks bigger and more complicated, we don't start from zero again training them. We can actually adapt them extremely quickly to new calorimeter type of layouts. That's very useful as well as we go about designing a next generation of detectors too. And you see the use of hybrid models, so combining traditional parametric simulation with machine learning as well. Now, detector simulation on GPUs, this is also a hot topic. In fact, we have an HSF community meeting on this, which is going on at exactly the same time now. This is a difficult problem because one thing that GPUs hate are stochastic processes and divergence, but we are making progress on this now. The first thing I would say is that you want to make sure that you get the physics right, and we've really done that because the difference between running electromagnetic physics on a GPU and running it on a CPU, the differences are now down to the per mil. There's honestly no point in going fast if you get the wrong answer. The speed of this is about a factor 2 faster between a multi-core CPU and a GPU. So you will never get the kind of speed up that you can have with event generation because it's a different problem, but we can use the hardware now. So we can take advantage of the GPUs that are in the computing clusters. Another interesting area is actually tracking optical photons, which GPUs are super good at, by the way, because it's a ray tracing problem. And there you can get much faster speed ups. I wonder if the next target actually would be doing the neutrons, for instance, on the GPU would be an interesting thing as well. So certainly a lot of progress there. Now, turning to reconstruction, of course, our new detectors are optimized for very high rate data acquisition, and our physics demands very high quality selection, very close to the detector now. So I think our LHCb colleagues also call this drinking from a fire hose, where you have megahertz rates of signal coming out of your experiment. Here, the pressure to break with legacy codes is very high, and the LHC experiments have done a very good job of moving towards these architectures. Alice were really the pioneers here, using GPUs already in Run 2. CMS will introduce GPUs in their trigger as part of Run 3, and LHCb will now actually run their entire HLT1 workflow will run on a GPU. So this is very interesting. They actually integrate the GPUs into the event builder nodes, and they get a huge amount of cost savings by the fact that they reduce the data at this point, and they don't need very expensive networks that go to the rest of the trigger farm. And the physics results are extremely good from it as well. And this allows you to do something that we might call in our field real-time analysis, where you actually can throw away the raw data because you have enough confidence in the reconstruction quality. This allows you to keep more events, and so you can actually do more physics on the same budget. It's a very nice technique. The other thing which I think is very exciting in reconstruction are projects like ACTS. So traditionally, reconstruction software was very detector specific because detectors are kind of specific. But now people think about the way to structure software that they can do things in a generic, rather pluggable way. And what's great about this is it builds a community who can speak a common language with respect of reconstruction. And so the exciting things that happen here are the use of graph neural networks to do tracking. And this came out of a US project called Exatrack, but now it's integrated into ACTS, which becomes the common platform for doing tracking across many experiments. And because ACTS was designed up from the ground up to be thread safe, unlike a lot of the more traditional approaches, you can get very good parallelization with it as well. So new seeding strategies here, which are way faster than the old ones. So this project now gathers momentum. It's used a lot in nuclear physics, in Atlas, and investigated by a lot of other experiments. Okay, for data analysis, I was asked to talk about sustainability. Well, you better make sure you can read your data. That's the first thing to make sure that you keep sustainable. But we need to be able to read the data fast. So the root team are redesigning our data format in order to go faster and to take advantage of modern hardware. And the early results from this are extremely promising, that you can actually read data not only faster than our traditional approach using T-trees, but much faster than anything which comes out of industry. And bonus, it's much smaller on disk as well, so we save on our storage costs as well. So all of this helps push down the cost of computing, but we keep the data format in-house, which guarantees the sustainability of this for the future. Now, it was already touched on by Gonzalo, how much we can also reduce the data volumes by producing reduced formats, and I think the CMS Nano AOD is a perfect example of how to do that. How you quite fit in all of the more exotic analyses is an interesting topic as well, but that is a topic which we will be addressing as well. Now, how analysis is done increases productivity. Maybe as we move to more efficient, more concentrated data centers, you want to give analysts an interface that they can use, which feels like a laptop, but it's got the power of a cluster. And so there's a lot of work which is being done on making the ergonomics, you might say, of analysis a lot easier. And there's various declarative models which are happening. These are very harmonious with columnar storage, where you store the data in a different way, but the analyst doesn't actually have to care about it. And even some nice work done now to take the pain out of doing systematics, which is a major irritation if you're doing analysis. And it scales very well too. So you want to make sure that you build in scaling from the very beginning in this. This also links very nicely to the kind of data analytics work which is going on in Python. And we see a lot of effort now in the field to make bridges between the kind of industrial Pythonic way of doing data analysis and what we do in high energy physics, because not everything works quite out of the box. So a lot of interest there too. For the analysis ecosystem, so this bridge to new clusters, there's work which is going on between IRIS-HEP, but also work that we do at CERN with SWAN and EOS as well. And as I said, we have a workshop which is coming up at the end of the month, which will kind of take the temperature of where this is actually going. Very good. Okay, so what you of course want to do is bind all of this together. So I have to mention that there's certainly some work in making sure that each component of our software does not act independently. And actually, if you're a small experiment and you have to build everything from event generation through to simulation, through reconstruction algorithms, and then to do analysis at the end, this is actually quite some task. And traditionally, it was something that you would give to a postdoc to do. That doesn't really scale anymore. So we want to provide standard, well-tuned software stacks. And one of these efforts is called Key4HEP, which is being supported by AIDA Innova and also by the EP R&D project. And this is a way that you can actually give physicists something that can work pretty much out of the box and make it much easier for them to deploy their full chain processing. But also because it's well supported, it's very good for preservation because you've actually built it in a way that's very reproducible and easy to deploy as well. So this is being used for FCC studies in the linear collider community and the CEPC studies as well. Now, here I go back to something that Giovanni mentioned, because of course, preserving the software isn't quite enough. You need to preserve the entire workflow. So I think the test science projects, which are happening as part of ESCAPE and EOSC, are really important here. So I do indeed point people out towards the posters, which are very nice on this. And it's really an attempt to sort of preserve the entire workflow, including the software and the data access all the way through to the final analysis result. So I think this is very promising in terms of like generalizing these things and making them sustainable in the future. Okay, now let me touch on software sustainability because that was somehow part of the remit that I was given. It's a complicated matter because you have interactions between the funding agencies, between the projects, between the people, between the infrastructure providers, and you have all kinds of the expertise which is needed in terms of software engineering practice as well. And I think some of the key pieces that you have are things like software engineering, making sure that we have people writing good code using best practices. Software, if it's still used, needs to be maintained. Software just can't be kept in a box because compilers will change, platforms will change, libraries will change. It needs to be maintained. You need a community of people involved around the projects. You need to lower barriers of entry, make it easy for people to contribute fixes. These are the successful software projects that we see, ones where new contributions from the outside can be easily integrated. We need to train people to write software in our community. And finally, we need policies to recognize and fund software and make sure that we look after the people who are actually writing the software as well. I think the research software engineer model takes a good step in this direction, but we need to make sure that we link up that software engineering expertise to domain knowledge in our field. Now, sustainability, of course, requires commitment, and this can be a bit of a chicken and egg problem. An experiment might not use software because they don't think that it's going to be sustainable, but then the people who write the software can't get the funds to sustain it because it's not used by the experiments as well. So we need to find a way to break out of these loops, but at the same time, I think finding common software solutions which are usable between multiple experiments helps that process a lot. The projects which really have a long-term commitment to the future, you can see that that is intimately linked to having long-term permanent positions for the people who are writing that software. So Root and Geant 4, the commitment that CERN makes to that is obviously critical to the community. It's a very important part of defining how we use that software, giving the experiments confidence, but also allowing us to build a community around that software as well, because you know that the software isn't going to go away. That's only one aspect of it. Still, we need to innovate. So these projects have to evolve, they have to innovate, they have to adapt to new technologies as well. So we need to allow risks. You know, we know quantum computing is incredibly promising, incredibly risky as well. We need to do that with the other software projects too. And then let me repeat the point about actually making the entire workflow sustainable, not just the software itself. That's very important. Okay, training, we touched on that yesterday, so I don't want to say too much about it, but we do provide training in software. We need to recognize that we have a very wide spectrum of people inside of our sciences who write software. Almost every PhD student and postdoc will do it a bit, but we also need to nurture some experts who will come along and will take care of the core of the experiment software. The curious thing here is that C++ training we actually seem to need to develop ourselves, but we have done so and we have done that very successfully. But we do want this to be, let's say, a complete curriculum for software development. Now, there has been a lot of projects funded in the field since we wrote the community white paper as part of the HEP Software Foundation, and these are already making, I think, quite a big impact in terms of adapting and trialing new ideas for our software. But we need to tackle the problem of how do you take a 4-year project and guarantee that what it produces can actually live on into the future, because otherwise it's just going to sit on GitHub gathering dust. Okay. Now, part of the way that you do that is you build communities. So this is what we do inside the HEP Software Foundation. Our key objective here is to have a community for high energy physics software, and we do like talking to other sciences and other disciplines as well as we do that. Okay, so conclusions that I would draw: we have a huge investment in software. Our science just wouldn't be possible without it. We face a lot of challenges. The great thing is these come actually from more ambitious physics goals, but at the same time we have technological challenges that we have to overcome as well. That's very common to all of the big science disciplines. We've had a lot of software funding in recent years, so that's really great, and in combination with the experiments, things are really moving forward. The HSF is playing a role, although it's largely unfunded. It's something that people recognize and they're willing to contribute some effort to. And I would say, if you really want to solve the problem of software sustainability, don't worry about the ones and zeros, worry about the people, because you need to sustain the people and they will take care of the technical matters for you. But provide good career paths for people who specialize in software, and then the software will live. Thank you.
Fantastic, thank you. So we have time for 2 quick questions. Okay, one is there on this side.
Thank you for the very nice talk. I had a question on this R-N-tuple tool you mentioned. Actually, like 2 very short connected questions. The first one is what the sort of timeline on this is, because it would actually be quite nice to use this for the run-free software that's coming up.
Yeah.
And the second question is, you mentioned specifically the read times and the storage on disk, but not the writing storage. And we've had in the past some problems, for example, with THN's parsers, where reading them and writing them is fine, reading them and having them on disk is fine, but during the writing process, it takes insane amounts of memory. So how does this compare?
Okay, so on the first question on timescale, I think the team are very much targeting run 4, but there is a version of R-N-tuple that you can use now. It's a little bit late, I think, actually for run 3 for the production software, but there will also be facilities to migrate data from T-trees to R-N-tuples as well. In terms of the write time, The objective of our n-tuple is not to be the bottleneck, the format itself, and therefore your write time will basically be dominated by which compression scheme you decide to use. If you use a fast compression scheme, then you will be able to write very quickly. If you use the very highest rates of compression, then of course that's more intensive calculations and it will write more slowly. One thing I will say is that our n-tuple is also being designed to take advantage of object stores as well. So that gives us the possibility of maybe actually parallelizing the writing of our data, which could be exciting depending on just how that comes out at the facilities end.
Yeah, just a quick question, Graham. Thank you very much for this overview. However, it was a little bit high energy physics focused,
Guilty.
of course. So, also, I know the other two communities profit very much from this development and from the power which is given to, and also the resources given to develop these things. Yeah. But are there, looking a little bit in the future, are there any possibilities or idea how to include the other two communities from early on, not only as users, but from early on and helping in the developments and maybe also consider some specific aspects of nuclear physics or astroparticle physics?
Right. I think for nuclear physics, there's probably more relationship than I put in my slides, just because of limited time. In particular, we talked a lot to the EIC community, and in fact, the Kiefer-Hep software stack was adopted by, I think it was actually the Athena detector concept. They took, for instance, things like ACTS, and they helped us to develop it as well. So there is definitely interaction there, and I think it's much easier between high energy physics and nuclear physics. For Astroparticle, of course, we share the lower levels. I mean, ESCAPE has in some ways worked in that area. About the specifics of software, I suspect that the two domains are just a bit too different to do something there, but I don't know. So I think this has to be part of an ongoing conversation that we have. I'm afraid I can't give you any better concrete answer than that, other than that, let's keep talking.
Okay, if I may add my €2, so the HAP Software Foundation, I think, is the correct forum to expand on this collaboration, especially if it gets more funding looking at the European Commission.
Yeah, thanks.
So, because it's a huge success. Experiments started talking through that forum, so it's easily, I think, expandable, just my contribution. So let's thank the speaker again.
Now we go for the photo, so just please go outside and we take the photo. The photograph is waiting for quite some time.
It's on. So, okay, welcome everybody to this last session of today. We will hear about two working groups that were initiated in the Jenas activities. So the first one is on recognition of individual achievements in large collaborations, and Emmanuel Gangler will talk about this.
Okay, so I'm glad to report on this working group about recognition of individuals in large collaborations. So I know that it's a hot summer, so people will slowly join. So I will start to describe a little bit the process which was followed by the working group before going to our main findings and recommendation. And I will try to leave time for questions, because what we have seen is that on this issue, usually people have a lot of opinions. What is more difficult is to find common agreement between everyone. So what is, in a nutshell, what is the issue is that collaborations grow larger and larger. And as the collaboration grows larger, the role of individuals starts to be diluted, or at least this is the perception of a lot of individuals. And this is especially harmful when people try to make a career. They are going to be evaluated. We have lots of ways to be evaluated. But evaluators, if they are not in the same collaboration, or even worse, if they are not in the field, may have sometimes hard time understanding what are the individuals' work. So this issue is not new. So we found an ECFA report dating back 92, where there was expressed the fear that with LHC, it will become very nightmare. So I don't think it's a nightmare, but still ECFA some years ago conducted a community-wide survey, which has still shown some significant unhappiness about this issue. And it was in particular visible amongst the early career scientists. So I guess it's very important for us in our field to have the early career scientists feeling recognized for what they bring to the collaborations. So after the result of this report, so there was a follow-up by a combined APEC, ECFA, and UPEC working group. That's us. So who are we? So two persons from APEC, 3% from ECPA, and 3% from NUPEC. Some are in the room, and of course my colleagues during the question, if you want to add up, I will be really pleased to show that it's really a team effort. So how did we approach this? So we really wanted to work closely with collaborations, and we started by trying to define what a large collaboration. So we set some arbitrary threshold at 40-ish person, and we collected the collaboration list. We approached them, we sent invitation letters, and at the end, 62 collaborations provided feedback. So it's a lot of collaborations. It's also a lot of individuals. It's more than, okay, roughly it's in tens of thousands of individuals which are represented through this kind of exercise. So you have here the numbers. You see that's a lot of people from APEC, big collaborations from ECFA, and for NUPEC too. So given the very large number of collaborations, we started by working in subgroups. So APEC, we're dealing with APEC collaborations, ECFA with ECFA collaboration, and so on. And we started to have some initial discussion. So we asked spokesperson for collaboration representative. We had some live meetings just to make sure we could design a survey with identical questions which were covering most of what is important to address. So in the second step, so when we collected all these questions, so we put everything in common between the working group, and the report that is going to be out soon provides both the joint summary, but during the conversation with the collaboration, there was really a lot of material, so we will also include what I call the raw material, so all ideas that have been expressed as probably being a best practice, even if in our report we sized that down really to target the most meaningful ones. So to give you a rough idea of the timeline, so the installation of the committee was in Ghent in 2019. So last Jenas meeting, we started the work, and we were really full of steam. And of course, you all know that there has been some COVID situation, which slowed down a little bit the process. At that time, we felt that senior collaboration leaders had a lot of priorities to handle, so we slowed down a little bit the pace, but here we are, after a few years, the draft report is done. It has been sent last March to the Jenas chairs, which say that it's okay to be presented today. And it's what I'm going to present. The next step will be to have some feedback from you. So maybe what you are here for is the findings, recommendation from this working group. So I will spend now the next minutes on this. So what is the main finding? An interesting thing that show up is that the concerns, the global concerns, were almost the same, were at least similar for each sub-community. What seemed to be the main driver on the issue of recommendations is not whether you do hadronic physics or cosmology, it was more the size of the collaboration itself. And of course, it's not a hard threshold, it's like subjective assessment, but it seems that past 100, 150 members, this is where the issue starts really to be more important. On the other hand, it means that smaller collaborations, for them, the issue are easier to mitigate. Which means that in all what I will say, all best practices really have to be adapted to the size of the collaborations. Not all collaborations have the same needs in terms of recognition. On the other hand, the good surprise, and we all know this, is that the very large collaborations have a particular awareness of the issue. And there is already a lot of thoughts that were expressed, a lot which is being placed. And just by comparing what other collaborators are doing, we collected a lot of information. So it's maybe a small recommendation, but I guess that's still our main recommendation. We don't expect us to come up with completely new ideas, but I guess it's an important recommendation is please do consider what other people do. Check for applicability in your collaborations. Maybe there are just some good ideas you haven't thought of, and just look to what other people have done. A very important point is that, of course, it's the collaborations which are responsible for any kind of implementations. There was the fear expressed at some point that we were going to do strong recommendations. No, our recommendations is please consider what others have to do, see for applicability. So we'll provide a catalog of promising best practices. And remember, there is no one size fits all. There's a lot of diversity between collaboration in analysis phase, in preparation phase, large, small, collaborations with a lot of physical results, collaborations which target only a few significant results. So everything has to be adapted to the local situation. So I spoke already a little bit of one is probably the most troublesome issue is for people to build a CV. The problem is that usually the relevant information is internal to the collaboration. So how to expose this to a panel outside the field? Also, that the time scale of analysis is usually much, much longer than the time scale of a usual PhD of postdoc. And I guess this is one of the issues for the CV. Also, another issue that showed up, and you know, it's what is felt as a lack of recognition for all what is preparatory work. Preparatory work is it's a large word. It can be hardware, software, technical, data preparation. Data creation takes more and more things. And there is the feeling that only people publishing or presenting the last final physical results get rewarded. People tend to think that it's difficult to take part or have a voice in the decision-making process, and that there is overall, in very large collaboration, limited room for creativity. Scientific creativity, you have to follow the same analysis step as generations of PhD have done before you. And also there was some discontent expressed about when presenting results at conference, a lack of freedom which was expressed. So what I'm going to describe is the categories of best practices that we did address. So publications, talk and conference, analysis procedures, providing information, which is important, promoting juniors, which is very important, recognition, everything is important, recognition of technical software work, governance, decision-making, and awards. Let's start with publications. So in the realm of publication, the good news is that all collaborations really place a lot of effort in devising policies that suits them. And when we ask the collaboration, even if there are variants, every collaboration is very happy with their own publication policy. So I guess there is no matter reopening the Pandora box of should we revise our policy, unless there is a need. And when there is criticism about publication policy, is usually only a minority within a collaboration. Yet there are variants, so you all know that the strict alphabetical order is the dominant policy of the collaboration. But sometimes there is a corresponding author which represents an analysis team. It can be used to put forward some individuals who have, or a group of individuals who have put the team. The publication board, I guess it's important that they may be able to provide statement of what were the key contributions within the paper. There are also some collaborations which are specialized, for instance, technical papers, detector papers with shorter author lists, which improve the visibility of the people having done the job. And we always also think that referencing PhD thesis in collaboration paper is a very great way to expose the work of the student. Talks and conferences. So you all know that conferences are an important venue for the exposure of individuals. One important thing is the fairness in assigning talks. That's a very important one. Of course, in smaller collaborations, it's usually much easier to assign a talk to someone who has done the job. For larger collaborations, what we have seen is that they usually have some ranking method. It's a good practice when the criteria are fair, which assign a talk to, with respect to the people contributions and usually a lot of other criteria. In some collaborations, some individuals can also proactively volunteer for giving talks. Then, to address the discontent about the freedom of the talk. So I guess a speaker can be given the more freedom in the content of their talk. So there is one issue with the standardized talk, is that it's harmful for the audience. The second, the third, the fourth time you have listened to the same talk, you don't pay the same attention, I guess. And also for the speaker who really cannot really put forward what their view of the field. So, of course, it's easier for smaller collaboration to give more freedom to their talk, but sometimes some flexibility can be given to explain the physics analysis and methods. One side remark here is that collaborations have policies, but conference organizers are an important player of this ecosystem of individual recognition. And I guess they have a role to play if conference say, okay, please provide in addition to the standardized talks with more freedom. That is, I guess, an interesting venue to explore. So, information. Of course, if external referee wants to know what individuals have done, it's important that the information is available in some form. So more and more often, the public website mentions, for instance, who is convener of which working group. And we've seen this as a good practice. I guess it's also good when the spokesperson or the relevant seniors have all the tools at hand to write, for instance, letter of recommendation. And one interesting thing we have seen is that there is a collaboration, namely Atlas, who has an extensive database of contribution from individuals. So people from within the collaboration can really assess when they are going to write recommendation letters, all what they know about the contribution. And another thing is that some collaboration allow job applicants to share internal documentation with the recruiting committee. Because usually the internal documentation, this is where they have most of their personal work. So analysis procedures. So I mentioned it already, the time planning for analysis is critical for the juniors. So some collaborations reported that they shape their analysis to fit the time scale of PhD and postdoc. I know that it's not always possible, but I guess it's an important thing to consider when designing a subject for juniors. There are also some collaborations which allow unpublished results to be included in theses. In some cases, they also allowed some unpublished results to be presented at local university or national meetings. So, promoting juniors. So, juniors are really an important workforce of the collaborations. You have seen there is probably one of the key things we have to address. We want the juniors to be interested in our field, to feel recognized. So the recognition is, of course, important for their future career. So collaborations have many tools actually to promote the juniors. One of them is to have junior convenership. So this has to be planned carefully because we do not want to overburden the juniors with all what comes with the convenerships. It seems important that when there are juniors in convenership positions, there is also some seniors involved somehow. For instance, juniors may have to face some situations where they are not probably the best person to handle. If there are, for instance, some important discussion to have or to choose between analyses. So it's very important that they are backed up by seniors, and also that the senior could witness the performance and to help the junior grow. A very interesting thing we have seen is that more and more collaborations have early scientist career panels, and in some cases, some collaborations also have early career representative in the governance bodies. And I guess it's an interesting lead to promote juniors. Of course, healthy governance, I guess, is very important for the success of an experiment, and the governance is really the central place where the recognition of individuals can be addressed and discussed. And in some collaborations, there are forums dedicated to the discussion of this issue, and I think we can encourage keeping this discussion going on within the collaboration. Very importantly, but I guess this will be addressed by next talk, is fostering a friendly, inclusive, diverse environment is very important, especially to make sure that every voice is heard. And another very important point is to have clear procedures to appoint individuals at leadership positions, so that there are no, okay, you see what I mean, that when procedures are clear, it's really a healthier way. People know how to apply, how things are done, and they feel that they can really participate out of fair principle. So regarding technical and software work now. So how to address this? First, let me state that the needs are different between the career paths. So academic or technical careers do not have the same needs. So collaborations probably should pay attention to that when recognizing the technical and software work. There are some best reported practices. So I mentioned already technical or software paper with shorter author list. Sometimes there are dedicated prizes. I will come back to that for technical or software work. And an interesting idea would be to try to incentivize conference organizers to give more room to this kind of work presented by the specialists, that is the ones who really know what is behind. So, awards and rewards. So during the discussion, I guess it's not always a clear distinction, but it appeared to us that there are actually two slightly different categories, but which means very different things on recognizing individuals. So what we call rewards is some level of recognition which can be achieved by any individual of the collaboration, provided they have met a certain commitment threshold. So there is some examples. So, for instance, being part of the author list, you have done, for instance, your service tax. So now you are an author. Being scheduled for conference is an obvious one. But there are also other things that are applied by some collaborations who have some specific status, like a builder status, or key scientist status, or staff status, or infrastructure staff status. There are many variants in the names, but who allow people who have done ground infrastructure to be recognized by the collaboration bodies. In the contrary to rewards, awards aim at selecting outstanding individuals. So, is it a good idea to have awards? Well, opinion differs on this. It's not always seen as good practice because sometimes it can introduce unnecessary competition within a purely collaborative environment. What we have seen is that they are generally well accepted when there has care been given that to have transparent procedures so that people know what is behind. Some popular categories is the PhD prize, the Young Scientist Prize, Technical Award, I discussed already. And we noticed, okay, an interesting idea is one collaboration reported to have the reverse senior prize, that is the junior panel who is awarding one of their seniors a prize. And I guess that's, okay, interesting idea. Of course, not all discussions come up with consensus, at least in what can be considered. So, and there were some controversial items. So we still present them because I guess it's important to state what is behind. And one of the discussions we had between the working group was about the internal documentation. So opening, should we open internal documentation? So it may be desirable because internal documentation, this is where there is all the details about the analysis, their reproducibility, the tracer of individual works. This goes in the direction of the open science. But opening internal documentation comes also with major drawbacks. And one of them is the quality assurance, which makes them difficult to expose as material. Not all collaboration would feel comfortable just displaying internal things. They might fear to be scooped by other collaborations. So this is one of the things. And the other thing is that if you want to have a publication in the terms of even if just on a website material, it comes from an extra burden of quality control, which can be put to better use, for instance, doing actual publication. So for the conference talks, I already covered this, but we think that it would be interesting to have sessions dedicated to young scientists to increase their visibility. And why not exploring new format of talks, like work based on data from the XXX experiments with more freedom, or exploratory talk on the measurements of Y. And we tend to notice that local, national, university talks are usually given more freedom. So what's next? So the final version of the document will come after this Jenas meeting, so we still have in the fact-checking. We think that gathering the feedback from this recommendation is important, and we feel that the discussion shall not be over, so we really are eager to hand over, and we hope that the chairs will appoint a new working group, a follow-up working group, so that they can collect the feedback, measure progress, assess what the collaboration thinks of all of this. And we think that it will be useful to monitor the effect of this study by conducting a further survey, and this time fully included NUPEC and APEC in this survey. So as a conclusion, I just repeat this. So we encourage the community, and in particular the management of the larger collaboration, to carefully consider best practices that are in use elsewhere in the field. And at the same time, we also encourage the community, and we know that it's a long run, when confronted with external evaluation, to keep explaining what are the tracers of recognition within our own community. So, read the report when it is ready, and let's open the time for questions if you have. Thank you.
Thank you. Other questions?
Yes, thank you very much for your talk and all the insights. Was mentoring considered as one of the ingredients in positioning young scientists?
So this is an interesting point. It was, okay, mentoring was raised, I guess, by some collaborations. It didn't make through the final report, but okay, I more or less cover this by senior mentoring to the juniors in convenership positions. But what I've seen, and it's something that I've seen happening in the collaboration over the last 3 years. So maybe it's also that the things has moved since we have collected the data, that more and more collaborations are implementing mentoring. So myself, I see mentoring as a good practice, but we didn't have enough feedback at the time from the collaboration to fully include it in the report. It's a very fair point.
Further questions, comments?
concerning the three communities, you said that first they were studied independently and then you put the points together. Were all similar points in the three communities? Because you make a very nice summary, but they were, I guess there were points in common and points that were not at all.
Okay. There were minor differences, but the feeling we had is that it was, between sub-communities within one community. For instance, if I take a NUPEC, whether you are in hadronic physics or not, I don't know enough, of nuclear physics, but I guess the structure, for instance, there was a lot of internal diversity between the communities, which didn't make really clear the difference between the communities. Okay, for instance, particle physics, there are much, much larger collaborations, so I guess all what is about database of individuals, there is a longer tradition of exploring this, but also a higher issue which are raised. So that is one of the points. I don't know, yes, okay.
Yes, what we noticed actually is it really goes with the size, right? I mean, we noticed that even in the nuclear physics community where the size was traditionally smaller, but now they are getting larger, that they are also sort of signaling the same problems as already observed in the high energy collaborations or particle physics collaborations. So it really goes with the size. In fact, the ones which are like just above 40, they don't even have a problem because it just seems to be good enough to recognize everybody. And when it goes around 100, 120 or 30, as you mentioned, then it goes really obvious.
So maybe one follow-up on the follow-up. So regarding the author list, there are also some difference. In particle physics, there is a very, very strong opinion. It should be alphabetical with everyone included each time, and this is the message we receive. While, for instance, in astroparticle physics, the tradition is much more mixed, like sometimes there is a single author or a single person writing a paper. There are also shorter paper and, well, key papers, standard papers, different categories of people with papers. So we've seen more variability within this community than from, for instance, particle physics. And once again, I don't know enough for nuclear physics.
So related to this, in some collaborations, there have been, sorry, here.
Sorry.
In some collaborations, there is a discussion that is starting now to add to the papers a statement about the contributions of the different authors to the paper. I wonder whether this came up in your analysis. So saying, you know, these guys led the analysis, these guys provided simulations, these guys did this, that, these guys contributed to the commenting, and so on and so forth. This has happened already in some collaborations, and it's being discussed in other, in particular in cosmology, which is where I do.
Yeah, we have seen this that this practice is going more and more. Actually, okay, I couldn't present everything in the detail, but it was covered in one of the small bullets to say that publication board or similar bodies should be able to know what are the key contributions for it. So the thing is that we are not imposing any kind of implementation of this. So how to know who has done what in a paper? We think it's important that the collaboration knows and that people can gather the collaboration together. How to do this, I guess, should be completely left to the collaboration. And I hope that in 5 years from now, when these things go more forward, we'll see both the pros and cons, what has worked well, what are the caveats of expressing this kind of things.
Yeah, I had a related comment. For example, in Nature, it is compulsory. PRL also has it, but usually it is not used. So is there a good reason? Because if you take particle physics, for example, there are too many people. So anyway, the author list takes 3 pages. So is it a problem to add another page with this?
So I think it would probably be a trouble for the editors to include a individual contribution of 3,000 people within the paper itself. So that's why, it's very interesting, your remark, because you see the kind of work we have done within this report. And this is why we do not go towards an implementation. So when there is only 40 people, you can have it as an appendix. If there are 3,000 people, maybe a database from the collaborations will better do the job. For individuals, then, it's really the question, how can an evaluator know what is in this database? So to us, it's probably recommendation letters. Okay, let's the collaboration keeps thinking about the best way of doing this.
So maybe a comment also related to this topic, because some of the big collaborations like Atlas, and I guess Siemens does the same thing also, we have a internal database with the information on what people contributed to analysis, for instance, specifically, that and this kind of information can be provided, for instance, by a young researcher in case he or she is applying to a position or these kind of things. It's not public by default, but could be made available. So I guess this is one way of implementing it without having to write publicly the full list of authors.
And actually, we took this as one of the examples. So this is why we would encourage this practice to be more spread, of course, if the collaboration sees that it's a good thing to do.
Yes. Maybe one should add, I mean, this question of mentoring came up, which we didn't put in the report directly, but it is a task, I think, and the duty of all the senior people to raise the awareness at their departments, wherever they are working, about the criteria which are normally used, one of which being the publication with 3,000 people on it, that this should not be a criterion for hiring junior people and things like this, and then teach them basically what else to look at when they are really going to this hiring process. Otherwise, we are hurting the junior, scientists in that respect.
So, I guess one comment on the thing you mentioned about the scaling with the number. I think that's not surprising to me. So there is something called the Dunbar's number. It's essentially a limit on the strong relationship that you can have. It's a cognitive limit. So I don't think it's a coincidence that you see this sharp change at 150. It's pretty well known in other fields of cognitive science. About the actual topic, so I'm a member of the Virgo collaboration. So the way in which works...
Please, can you remove
sorry.
okay.
Yeah, sorry. I'm a member of the Virgo collaboration. And so the way in which for us it's very effective for young scientists to be recognized is through short authors papers. But that depends strongly on many things. So for example, it depends strongly on the collaboration defining the science scope of the collaboration itself. So Virgo says, we are going to investigate these topics, and all other topics are free for all. So you're free to publish whatever results you want on short authors papers. And that's how, historically, I would say, young scientists are recognized, because we know that there's a whole area of topics and we can directly contribute on those. Because when you go to an employer which is outside your collaboration, the person doesn't care about which analysis you did or which automation you did and stuff like that, because it's very technical. So if you go to stay in the collaboration, that's useful. But if you want to go outside the scope, it's really not. So I think it's easier to be recognized on the scientific contributions, on novelties, but that imposes to the collaboration to clearly define what other people can do with those data. And also, last brief comment, it also implies that the supervisors have to leave enough time for these people to develop their own ideas and develop their own analysis. If you give to a postdoc a project which really can be completed barely in 3 years, of course you never have enough time to. So there's a mix of things. I don't think it's all on the collaboration side. It also depends on how you handle the time of these people. Yeah.
So thank you very much for all these remarks. So we have discussed part of them within our committee, working group work. So this model that you described, actually there are other collaborations, especially within APEC, which do that. So that is analysis made by a smaller group of people. So they take the data from the collaboration and are allowed for certain categories of paper, not key papers, but to bring their own ideas. So that, I guess it's a very interesting model that works for this sub-community. But here we were speaking on behalf of the joint community, and with our discussion with particle physics, with nuclear physics, it didn't seem a model that we could push forward. Even if it could be interesting for this very large experiment to see, can we have, for instance, method paper for analysis to be by a smaller list of authors. It raised a lot of issues. For instance, Monte Carlo is already a big collaboration effort, so if you are using Monte Carlo, you should draw a lot of traction behind you. And another thing that, related to the size that we wanted to explore, but it didn't make through the, so we abandoned this idea, is to say, is it possible to consider large collaborations as a collection of smaller groups, like there are analysis groups or detector groups? But we didn't go very far from this, and there was the idea that collaborations, especially particle physics, it's important that they are recognized as a single group work. So we didn't push this through. This is an idea that you won't even see in the report, but just to show you that we considered a lot of possible options, and we really tried to draw something that we think all the sub-communities could try to draw from, even if there are particulars from each community.
Okay, so I think we should stop now, and thanks to Emmanuel. And the next speaker is Patricia Condemuño, and she will talk report on the survey on diversity.
Okay, so I'm going to talk about diversity in APEC, ECFA, and NUPEC on behalf of the Diversity Working Group. And I will start with first a bit of history to let you know what this is that we are doing. So there was a group jointly formed by APEC, ECFA, and NUPEC, a working group to deliver a charter, a diversity charter adequate for the three communities, with a sign-up plan and also a follow-up plan, and that includes also monitoring. So you see here in this slide the members of the diversity task force from APEC, ECFA, and NUPEC. So there has been some rotation, but in APEC, and ex officio we have also the chairs of NUPEC and ECFA. Previously also Jorgen, who was a previous ECFA chair. And the chairs of APEC, that was Teresa and now Andreas, were always part of the working group. So to start with, I would like to first talk about what we understand by diversity, and that is the base of the charter. Basically, this is a very wide definition of acknowledgement, respect, and appreciation that people differ in many different visible or invisible ways, such as age, gender, sexual orientation, ethnic origin, civil status, familiar situation, economic background, religion convictions, political ideas, etc. Okay, and the Diversity Charter wants basically to promote diversity as a motor to boost productivity and innovation, and also fight prejudice and discrimination. Our initial focus was on collaborations, conferences, and organizations within the three fields, APEC, ECFA, and NUPEC. And if you look later at the slides, you have here a link, and you can check in our webpage all the information about this, okay? And you have also in the page a list of the signatories of this diversity charter. The signatories, once they agree to support this charter, they basically commit to a series of ideas. So the first one is endorsing an enabling environment for the understanding, respect, and promotion of diversity, all these diversity items, at all levels of the entity, okay? From at all different management levels, including also top management. Balancing composition of the bodies, management bodies, committees, leadership positions, for instance, in case of conferences, organizing and advisory committees also. So also developing an organizational culture based in respect, recognition and appreciation of individual differences and in talents. And as I just mentioned, they also commit to monitoring, analyzing, evaluating, and sharing this monitoring information, okay? And this is the point that brings me here, that has to do with the monitoring of diversity, in this case in scientific collaborations, okay? So for our first approach, we decided to, we have classified the monitoring variables in different categories. There are some variables that we consider non-monitorable, such as sexual orientation, physical ability, race, ethnicity, and we have concentrated, therefore, in some variables that smaller, reduced number, but that are monitorable, such as age, gender, career level, working country, and citizenship. And in order to collect the monitoring information, we prepared a survey that was distributed for the moment in collaborations and conferences to help them provide the monitoring information that is not available normally in there. So to give you an idea of the timeline we have here, so the group, Diversity Working Group, was formed in September 2018. And in March 2019, we prepared the first draft of the Diversity Charter, and also we prepared a monitoring survey. And the first one was used in Jenas, the Jenas seminar meeting in 2019. We collected some feedback from there and then improved it for distribution to collaborations in summer 2020. Also after a bit break due to COVID. So when we distributed to the collaborations, there were some concerns raised, particularly with data privacy issues. And therefore, we had to address them, and we reorganized the survey and the information available to address these issues properly. So it was distributed again in 2021, and we have been basically collecting answers from different collaborations. So these are the first results we have collected, okay? So in the case of the questionnaire for collaborations, the questions we asked concern a gender, age group, and we have divided in bins, tenure position, such as tenure, not tenure, or tenure track, responsibility within the collaboration, a member of the collaboration without a managerial role, or level 0 management position that can be, for instance, a spokesperson, a steering board, or something at that level. Level 1 management position would be an activity coordinator, a project leader, for instance, physics coordinator, or a detector project leader. Level 2 management position would be something like analysis group coordinator, or so someone below the project leader. And then there are also possibilities of official non-managerial roles, okay? So we also ask for country of origin and country of work, with the idea that we can try to study, for instance, if the coordination positions are distributed evenly within the collaboration, taking into account, for instance, gender or origin or place of work. So you see here an overview of the answers we collected from the different collaborations. Surveys were distributed, and the collaborations encouraged to answer to that. Overall, we got about 5 to 10% of the collaborations members responding the survey. So this is, okay, it's a small fraction, but okay, one might consider, okay, if it is sufficiently representative or not, and I will come back to this question at the end, okay? In terms of demographics, you see here that around 30% of female, so in this pie chart, for instance, 30% of, 28% of female were female, and 68% men. Then in terms of age, we got overall an even distribution basically in all the bins. And in terms of tenure, okay, there are two big groups and another one that is smaller, that is tenure track, because it considers a smaller fraction of years. So in order to compare, for instance, management positions, we have to take into account the populations, so and the fraction of for instance, women that are in the collaborations and so on. So we have normalized the data by, for instance, if we want to study management positions, we have normalized it for women and for men and calculated percentages. And the same for countries, okay? For country of origin, country of work, okay? And also, in what follows, you will see integrated plots for ECFA and NUPEC. And you see here the collaboration, sorry, wrong button. The collaborations that are grouped mainly and have mainly contributed to this survey, okay. So I will start with gender. Okay, I would like to focus on this plot on the upper side. So in the way we calculate it, percentages are directly comparable. So if we look, for instance, so there are very few level 1, level 0 management positions, but let's look at level 2, okay? Okay, you see here first two big wings that, so in terms of gender, we ask, okay, we propose the option diverse or don't want to answer, and these two wings, you look here, this is a plot, so this is percentage, and this is the plot in absolute numbers, and you see that there are very few people, so please concentrate on yellow and red that are female and male, and we can compare directly the percentages, okay? So, for instance, you see here, in general, okay, we have error bars, statistical error bars, and you see that, okay, they are compatible, the fractions within the error bar. Down here you can see in absolute number the gender distribution for, okay, sorry, the age distribution for the female and male populations that answer this survey. Okay. Here this is the equivalent plots for NUPEC. And okay, in this case, probably there are a smaller number of management positions, but the conclusions we draw from this sample is that, okay, we still get compatible numbers. Sometimes one being is higher than the other, but they are within the statistical uncertainties. Okay, and the populations are a bit different in this case. I move to country of origin. So in this case, we have a lot of possible countries. Country of origin or country of work. So we have grouped categories in order to first ensure anonymity of the survey, that it is very important because of the data protection issues, and also to have statistical some significance, okay? So we have divided in Northern, Central, Eastern, and Southern Europe bins, where we have sufficient statistics, USA, and other countries that basically join all the other ones. And CERN, in the case of place of work, is treated as a different, as if it were a different country, because CERN is very specific, and this is in order to avoid possible biases, okay? So, and we use the same categories both for NUPEC and APEC. Here we see the country of origin distributions for ECFA. Please concentrate again on this upper left plot with percentage per country of origin, and we see we can compare percentages within the same bins. And if we look, okay, again, we have very few level 0, level 1 management positions, but let's look, for instance, at level 2. And in this case, okay, despite the large error bars and maybe not extremely statistically significant, but we do see that there seems that some countries have a smaller fraction of level 2 management position with respect to the others. And this corresponds to Eastern Europe, Northern Europe, and other countries, okay, in comparison, for instance, with Southern Europe or other. So, however, if you look at the age distribution per country, in this case it is percentage, okay, so the shapes are directly comparable. You see that in, for instance, in some countries we got, this is Eastern Europe, we got much larger fraction of answers from younger members than older ones. You see here the beans in age, okay? And, okay, maybe not so obvious in Northern Europe, but very obvious also in other countries. So there is a correlation with age. In our case, the statistics were not great, so doing more final, more refined binning, it's probably not going to give us a much better conclusion than this. So for NUPEC, we have done the same thing, and we have here the plots. Okay, if we look, for instance, again at level 2 management positions, for instance, okay, in this case it is not so obvious, but it does seem that, for instance, Eastern countries are a bit lower, and however, in this case, the age distributions do not look so different, let's say, country to, region to region. So moving to country of work. In this case, we added CERN also as a possible country. And when we look here, okay, this is this is again ECFA. And let's look, okay, we can compare again level 2, and we see again the same picture we saw before. This is most likely also due to the fact that there is a strong correlation of country of work and country of origin in most cases, so probably this is correlated. And the populations are also, let's say more biased towards the younger generation in these 3 bins that we have here. So in case of NUPEC, we have here the plot, and we see again, okay, now here we have much larger error bars, and it is not so obvious. And also the population are more evenly distributed, so it's a bit difficult to say if we actually see any bias or not. So we have here also collected some comments we received from the members of this, the people who answer, and there were few but encouraging comments thanking us for this initiative. And there were many concerns raised. One of them, for instance, was the representativity of the survey. Okay, and indeed we have seen that we have between 5 and 10% of the collaborations responded. So, and we have seen also that there are some biases in age in some countries that most likely are correlated with the level of interest or concern on the topic. So younger generation might be more worried about this than the older one. So it would be ideal to, to enlarge this fraction, sampling fraction. So we got issues related to gender versus sex and how this could be biasing or not our results. But okay, in this case, it's not very easy to have a definition that satisfies everybody, but might be improved in the future. So there were people who considered this is not useful at all. There were concerns about privacy, and these ones I want to answer them specifically because in the working group we have treated all the data according to the laws on data protection, and we have. So although the data was not private, this was clearly specified in the survey, and we have ensured anonymity of the published results. So the anonymity of people is safe. There were also questions concerning so that we could use a larger variety of definition of variables to monitor. That okay, might not be very easy. Some of them is not very easy to define. What do you mean? In a completely general way, for instance, economic background. But okay, this can be thought for a future iteration, and also we have focused in Europe, while we could have also distributed it towards other collaborations, and this is also outside Europe, and this is also some next steps we have to consider. So to conclude, we have distributed a survey to study diversity in international collaborations in the fields of APEC, ECFA, and NUPEC. Overall, we got around 5 to 10% of the collaboration members responding to these surveys. And in some countries, we observe biases in terms of age of the respondents that may suggest also that this topic is more of a concern for some maybe younger generation. Within the statistics collected, the management positions within the collaborations do not appear to be biased by gender. That means that the fraction reflects the population. However, there might be biases with respect to country of work or country of origin. And we encourage collaborations to further look into this issue with full statistics, since many of them already have databases, at least for some variables such as country of work. They are able to get this information, and we have started getting already some information from them also on this. On our side, we believe that to bring this effort into the future, I mean, the next step clearly has to be enlarging the sampling fraction and getting a more representative results. And we believe this can be done in collaboration with the diversity and inclusion offices in the collaborations. The big collaborations already have them, and this could also be a way to encourage other collaborations to establish their own diversity and inclusion offices and discuss this within the collaboration. So thank you. If you have questions.
Thank you.
Thank you for the wonderful work all you guys have done. So I probably missed it. I did not see APEC.
APEC, we have not collected significant, let's say, we have smaller statistics, and we decided not yet to publish them. I mean, we will pursue this in future. I mean, we will try to get higher statistics.
So is there an issue? Because you point out, age and things like that. So is it related to one of the things about subject? Or you have some other reason? Maybe somebody from APEC can answer.
Okay, I think Andreas is not here because there is a parallel room with the funding agencies. So basically, okay, you need, it requires quite a lot of follow-up, encouraging not only on our side, but also on the spokespersons to distribute the information and so on. So, okay, this will come, but was not ready right now.
And I just had a minor question. Can you just go back to your last slide, please? I think it's you.
No, it's not me. Can you put my slides back, please? Okay, here.
Yeah, so I'm sorry, I missed the point about they might be biased with respect to country of origin of work. Sorry, I didn't get that from your graph.
For instance, this is country of work versus management position. This is for ECFA, okay? And okay, you see here, so that so these are grouped distributions, and we have, let's say, Central Europe, Eastern Europe, and Northern Europe are yellow, green, and red, and you see that these beans are lower than the other ones. The statistics is not great, so it's not completely significant when you look at that. However, this pattern is repeated also when we look at individual collaborations that we have not shown here, and in addition to that. But as I said, this also might be correlated with the age profile of the people who is answering it. So if we have a larger fraction of young people, of course, they have a smaller number of coordination positions. However, we think this is important to, it's an important point that should be followed up, probably by the collaborations. In the case of country of work, collaborations do have the databases with the information on this, I mean, at least big collaborations.
Hi. Thank you for the work that you have done. However, you pointed out in the last transparency the two things that makes this survey, I would say, but it's my opinion, completely useless. The point is that statistics is a science, and when you conduct a poll, you have to follow the rules that tells how to remove the bias, if possible, from the things. I mean, with a poll like that, where I take 2,000 phone numbers, and I phone to people, say, who are going to vote the next election, I will get essentially a completely random result.
No.
So, but this is not the, I mean, so you understand, you have written, so that is not my problem. Now the question is, the issue of representation, of gender balance, these are extremely important in our field, that are becoming noticed from other people. And so we should treat this in the most likely efficient way. As you said, the collaborations have all this data. And there is no question of privacy, because you can do a completely blind things where names doesn't appear, things do not appear. If the collaboration do not understand the importance of these things, we have a serious problem. If they do understand, then these things can be done in the next year, say, and publish a book which say everything about the way in our science we treat this problem.
So a couple of comments to your point. So collaborations have some data. Country of work, they do have. They don't have normally country of origin, for instance. They don't have age. No, they don't, because when you no. This data is in a different database, and the law of data protection forbids you to study these correlations unless we get the approval of the people who have. Of all the people who have their data in those. For instance, Atlas. The Atlas collaboration cannot correlate with a certain database, because when people agreed to provide their data for this database, it was with a specific purpose and not this one, for instance. So.
Our study was delayed by 6 months
because of this issue.
I also consider this stupid, but there are really
Yeah.
agencies which really stop the procedure for 6 months.
Yeah.
Because they claim that the way of doing this for 5 parameters is already violated.
Yeah. Even for these ones, we had huge discussions. Addition to that, for instance, there is another one that is not included in the. So gender is not included in the database, not even at CERN. Not even in the CERN database. Gender is inferred in, for instance, when collaborations such as Atlas or CMS or LHCb do these kind of plots, because we do them. Gender is inferred from the names used in some databases. But in that case, you have only a binary option. You don't have any other possibility. So this is also limiting. You cannot study really minority groups, for instance, in this case.
Yeah, so I think this is very good work, albeit that there are limitations and we understand why, and it is important that people have privacy as well and that they opt into this. One thing that I think is important in terms of extending this work is, one, tracking it over time. We know we have a long way to go in our field in terms of proper diverse representation. We want to be able to see whether it's getting better, or whether, we recruit lots of, let's say, female students and then we just lose them afterwards for other reasons. That's important. The other one is, maybe when we are organizing conferences, sometimes we ask questions like this. It's very difficult to correlate answers between different conferences because everybody decides different age bands and different questions, different employment categories. It would be quite nice if we could have some kind of standard which would make it easier to compare places where we are able to gather the data.
Yeah, we have collected already data from some big conferences. We are analyzing it. It's a bit it's more complex because it's much more diverse and a bit more difficult to study, but we are working on that too. So we have data on the conferences. In that case, it's related to kind of presentations or role within the conference. Yeah.
Yeah. So about your country of work columns, so maybe you said it, I didn't follow, sorry. But when you say CERN, you mean people paid by CERN or based at CERN? Because you might be conflating...
No, who work at CERN, employed by CERN.
Okay, fine, thanks.
Well,
Okay, so thank you for the very nice talk. And so my question is, imagine, okay, let's say we have a very good database, very good statistic. Then how can we change things without creating, let's say, discrimination? Saying, okay, I want to promote women, I want to...
Okay, this reminds me, okay, I'll go back to the question of Graham that I didn't answer. So, and then I'll come back to yours. So we will, our objective is not to stop this and forget about it, but continue. So this, we kind of thought of this as cycles where we do some monitoring every fixed amount of period of time. We have not yet discussed the kind of measures we need to implement, because this depends if we observe or we do not observe, let's say, biases. However, yeah, if we observe, so the first thing is that if you observe something, then it's a motivation for people to work on it. And okay, there are all these issues of recognition. This is also related to that. So I guess the collaborations will need to start working on that. But then if we have data for different collaborations, I hope also they want to compete to be more fair within each other. But we will consider, I mean, if we confirm that there are biases, of course, I mean, this, we will, let's say, work out on how to, what is the next step towards achieving a better balance without, as you say, other kind of discrimination.
Yes. Okay, but I think the conclusion which probably should be taken seriously is that this sort of statistics will repeat itself if you do it 2 years from now. Mm-hmm. And this was 5 to 10%, and you can also see from the age profile, for instance, this is completely biased. So it doesn't mean much in terms of statistical analysis. The better way of doing this is that really emphasize that collaborations, especially large ones, appoint a diversity officer, basically, and then make a working group within these three communities of the diversity officers, because there they have a good knowledge of their collaboration, and then they can sort of come up with this questionnaire, which has the same questions, so they can then integrate and all these things, and then come up with better statistics. Because the way we have done it, I think the conclusion is very clear, and we insisted, we sent it around 2 times, and this is what we got.
Yeah, and diversity, let's say, within a collaboration, they may also kind of get the agreement of the collaboration members to do correlations with the CERN database that we, ECFAPEC, NUPEC cannot do, for instance. And this point could be an improvement too. However, as I said, the CERN database do not have all these variables we do.
So, last question.
Sorry to ask this rather a question which we cannot derive. If 5 to 10% of the collaboration members answered, if I remember, this didn't take more than 4 minutes to answer this this thing. So that means there is no problem. It was very short to fill it.
It was really short. It doesn't take 4 minutes. It takes,
no, I'm saying I don't remember. It was certainly not about
2
5.
minutes.
2 minutes. So if people didn't answer, it seems, does it mean that there's no problem? So they don't care?
I'll answer to you in 2 different ways. The first is that even surveys that are really important for the life of the collaboration, organization, issues, problems, they get 10 to 15% of the answers of the collaboration. So then okay, this topic is kind of controversial, and some people may be worried about that or whatever. I don't know, or they are not worried, or I guess. So the biases using age, for instance, or the fraction of women that answer the survey is probably larger than the fraction of women within the collaboration. So we got 28% of women answering. I think in most countries it's around 15 to 20%. The younger members also, in some, particularly in some countries, answer more than in others, than older members of the collaboration. So this might be correlated with the level of interest of people in this topic, and there are groups maybe that are not so interested, or they don't not worried, or they I don't know.
Navin, directly to your question, what we are trying to do is that NUPEC is supporting conferences, and so we ask now all the conferences we support to encourage their participants to fill in the survey. This has not made sense in the last 2 years because of the limited number of conferences. But now that it starts again, we will see what's coming out.
No, we do encourage, but then, okay, we send information, they have to encourage the people to participate. In some conferences we got 10 to 15% of the attendees answering, for instance.
I think Emmanuel showed the number for the last ECFA survey, which was 1,300 people, right? Or something like that, where you showed the number of respondents. Right? And then this is when this was in the at the ECFA level. If you add all the numbers that we got, is less than 500 from ECFA, APA, and NUPEC. So there seems to be a trend that maybe the management of the collaborations have insisted that the other one gets filled, and it took about half an hour, I know that for a fact, more than half an hour to fill the other one. And this was only 2 minutes, and still we got 500 responses.
Can you go back to transparency? I don't know if it was 7 or 8. With the plots, my question was that suddenly I saw no women in one of the plots. Maybe there was young people.
Women is
young people. Yeah. I could see there.
The age distribution. This is probably because diverse.
Okay.
I mean, there are beings.
No, I mean,
by category or.
But this is normalized, no? Can you go back
in
to
this
that
case, okay, in this case I show the absolute number, but...
So when you put the female distribution, is normalized to all the women? Or
exactly. So
and the men is normalized to men? Okay, so it's not relative.
Collaboration member, level 0 management, level 1, level 2, and official non-managerial role, they add up to 100% for women, and they add up to 100% for men, such that you can compare directly the percentages.
Okay, because I have a question. Maybe I can hear from other countries. I think Rocío is aware. In Spain, we are experiencing that we are getting less women doing physics. Is this the same in the other countries? I mean, students that do the degree in physics is decreasing.
Is decreasing?
Is decreasing.
Oh, no. I would say this probably depends strongly on countries. For instance, we were visiting Germany 1 month ago, and the fraction of women have increased in Germany from considerably. I think in 10 years from 15 to 25% or something like that. So quite a lot. And across all career levels in that case. I cannot, so we do not have statistics per country, and so I cannot answer you in a general way to that, but it's not a general trend, let's say, right now.
In Spain, we start from a better number of people matriculated in the grade, because they were but they have been from 40 to 25. So
40 to 25, wow.
So it's going
overall,
down.
I mean, is this
in physics.
general also?
Yeah, at the university level.
Here.
At bachelor.
in Madrid.
It has been going down really rapidly also. But I have also a question in this plot, because you said it's normalized, right, to the number of women. So I know that the statistic is really bad. We know all the statistic, but there's a trend that we have more women in that plot, but then at the management of level 1, level 2, we are less women. So you said there is no bias, but there is at least a trend that we are less represented in the management.
Okay, in level 0, and there are more women than men. Level 1 and level 2,
but
maybe not official non-managerial role, maybe the other way around. Yes, you are right, there might be.
Yeah, there might be.
We cannot conclude that.
Very interesting discussion, but there's still one last. Okay.
No, I just wanted to add the comment that, for example, in the UK, where I'm based now, I mean, the level of the women, for example, entering the university, that they've done the A-level in physics in the UK has been constant for, I don't know, 30, 25 years, and very low, actually. And despite the amazing effort to try to change these numbers, I mean, I think it's around 20%, and, no effect of any initiatives.
I would say, okay, we can discuss some possible ideas.
The institute have this data already. For example, the question that you said before for Germany. I mean, if you ask INFN, we have annually statistics of how many women Astroparticle, how many, what is the percent here, there, and everywhere. We included this in the report to the International Evaluation Committee. So if you go through the agencies, you get already a lot of data.
Yeah, what I mean is that sometimes the data is not coherent across countries. When we go, ECFA, for instance, visits countries, but we could collect data from institutions or from countries. Most of the countries do have some data, at least okay, but this affects only one variable of diversity, that is gender. It's well, in principle, institutions could also have a country of origin, because normally they have passport information or whatever. So, correlations at gender level, they can be done. Other variables, such as, for instance, other nationalities, but probably they can do at least other nationalities versus the country of origin. I mean, the country where the institution is based, yes.
Maybe I think this should be emphasized. There was one of the parameters which was the working country and where you come from. I mean, this is no one agency. Besides this, we know. What do you mean? Correlation-wise. We cannot find this correlation. I mean, countries, the data are known where you come from, or where you had, and then compare to your age and your
we have it here.
But I think the problem is always, even if they have it, they're not allowed to give it to the public or to us.
We haven't yet gone through the institutions, because we wanted to start by maybe the easiest ones, but this is the next step. And okay, if institutions are willing to collaborate, of course we need to go one step further.
Okay.
I'm not sure personally it's a question of accessing this data, because if you see the ERC statistics, usually they used to publish the country where the ERC grants are hosted and the nationalities.
Yeah.
So we have this, and this we have, as Nando was saying, this we have in our own institutes. So if we want to make a step forward, I understand that you want to do this at the level of institutes, but I would say this is exactly the same things as the behavior, the code of behavior. First of all, we have to verify what's the situation in our own institutes, in our own countries, and try to develop something in order to have a common approach. And then we see if this is reflected within an international collaboration.
Yes.
Because I'm wondering also about the fact that if you consider the nationality, in a collaboration, there is a country participating more than another. So there is sort of bias like this.
But collaborations do have these big collaborations, do monitor this, because this is a very important issue for the healthy life of the collaborations. And Atlas has actually published in conferences results on this kind of correlations of, are the management positions fairly distributed, taking into account, but you should always take into account the fraction of people coming from that country, of course, either if it is nationality or country of work. But this is very, very important for big collaborations. Maybe more even, well, maybe not more. It's always important also from institutions to ensure that people who come from abroad have the same chances as the people in your country, and vice versa too. So, but these are important questions, and some collaborations have started to address some of these, others maybe not.
Okay, so I think we have to stop now, and I would like to thank the speakers again, and also all the people that contribute to the working groups, and hopefully they will continue their work in the future. Thanks.